as far as the GATE biomedical paper is concerned, what I discussed kind of specific to, the marks distribution is specific to biomedical paper. If you look at GATE BM paper, you have general aptitude. This is general aptitude and math together. This makes 15 plus roughly 12. That is 25, 27 marks. Okay? So rest of the 73 marks, we have core biomedical subjects like biomechanics, biomaterials, medical imaging, bioinstrumentation, anatomy and physiology, core BM. Okay, they're subjects. And then we also have core as in like, again, not G and math. We have non-BM subjects, electrical circuits, signals and systems, measurements, controls, and analog and digital electronics. Typically, the marks distribution here is core BM questions have a higher weightage. Okay. So out of the, roughly, let's say 75 marks is left, 40 to 45 over here, 40 to, even I would say sometimes, 40 months, 40 plus marks, 45, approximately 45 marks in this side. And here you have approximately, 30 marks. These two are approximately all three add up to 100. Okay. So you can get a single digit all India rank. Notice around 50, 60 and all that, you're a single digit topper, right? You're on 45, you're a topper. If you focus on this, do well. This is, you can excel in the GATE biomedical paper. Get even a single digit rank. By that, typically get a seat of your choice. But there are also some easy questions here that biomedical students, can get an advantage or can get a lead, right? Can get an edge if they manage to get a couple of marks here. Anywhere from 10 to 15 marks, if they manage to grab here, that's a very, very big advantage. And typically, there are 10 to 15 marks worth of easy questions in this thing. That is one reason to learn this. And another reason to learn this is, hey, you're not a biomedical student. You're from a different branch, instrumentation or electronics student. Okay. Again, notice if you're very, very strong in this non-BM course, non-BM subjects, try to score as much as possible. Then you have to be reasonably good at GA and math. Learn basics of biomedical as much as you can, at least bioinstrumentation, medical imaging, and all that. Then again, you can put up a very good fight. If you also manage to learn advanced things over here, you are a candidate for even all India rank less than 5, something like that. So this is the reason to look at this non-BM subjects, electrical circuits being one of them. Having said that, at this stage, we are like October, right? So we still have about 3 months till the GATE examination. Most of us will start putting more emphasis on practice, revision, mock tests at this stage, certainly by December, right? You may not have all the time to learn everything in electrical circuits. Okay? But that is where, notice, if you look at, the GATE syllabus, this is, let's say, GATE BM syllabus, there is a small subset here. Approximately 20%, where 20% of concepts, where 80% of questions show. So a small subset of the concepts in the syllabus is where typically most of the questions are concentrated. Typically, okay. This applies to GA, math, core biomedical, non-biomedical, most of it. And every year questions don't repeat, but these concepts keep repeating. So if you learn the PYQs in and out, okay, you need to know them in and out so that, if you understand the underlying concepts, related concepts, you are likely to do very well in the upcoming GATE exam. Okay, most of these concepts will repeat, and if you are kind of thorough with them, you are likely to perform well. Again, if you at least the easy moderate questions, it's very, very easy to do. That is the reason we are going to start looking at the PYQs from GATE biomedical papers. Okay. So far, notice we have 4 or 5 years of PYQs, right? This is 2020, 21, 22, 23. 4-year question papers we'll look at it. We'll use a 4th year paper, 5th year paper, 2024 as a mock test. Okay. We'll see where we stand. We'll use it for that. And again, my suggestion is typically, if you look at, even the PYQs, there are easy, moderate, and hard questions. It makes good sense to actually put your focus here. It's most efficient in that sense, okay? Else again, you seem to be forgetting what you learned in bioinstrumentation 2 weeks back, right? Cramming more and more things is not productive. Typically, it's counterproductive. Okay. So some bare minimum things that we want to learn in circuits, that is what we are going to learn. And the reason being, of course, the concepts don't repeat. I mean, concepts typically repeat. Okay? But if you look at the questions, PYQs, they don't repeat. But even as we look at the list of PYQs, I have kind of clustered them into different sets. We kind of recognize, hey, the concepts keep repeating again and again. We'll make sure that all the easy, moderate concepts, all the questions will learn very, very. Okay. That is the objective. That is what we'll be doing this month. We'll go one subject at a time. We'll go circuits, then we'll do measurements, signals and systems, controls, then electronics. Okay. Now let's get started with resistances. So circuits that only has resistances. I want to know where that class stands. Okay. Let's do a quick poll. So check all that up, right? So let's make it a multiple choice. One is to do equivalent resistances, series parallel resistance. Right? Familiar with equivalent resistance. Say familiar with them. Let's simplify it. Let's be more specific. Check all that you are familiar or comfortable with. Okay? I'm going to say familiar. One is series parallel resistances. This is specifically concerning resistance, circuits with resistances. And then can you do Norton and Thevenin conversion with independent sources, no dependent sources? If you know, you kind of follow and simple Norton Thevenin conversions. Next would be, can you do, let's say, what do we have here? Basic power, related variables, basic variables like power, energy calculations. Can you calculate what is a power dissipator? What is the total energy dissipator? What is the rate at which power is dissipated? Can you make some basic calculations? And every year there is also a question from a specific type of circuit that only has resistance. Okay, and this is known as a Wheatstone bridge. This shows up in high school physics. Are you familiar with that? Kind of aware of what is this bridge balance? Okay, let's do this poll. I just want to know where you stand. Based on that, I will kind of tune this. So I'm starting to get answers. So most of you are saying you could do series parallel resistances. Fair. If you have to add one trick, in your hat, that would be delta star conversion. Okay. Why delta? No, delta star conversion would be one thing that I answer. Fine. So most of series parallel, you could do other things only like half the class kind of is aware of, right? Fine. I presume that is also the case with voltage division, current division. But that's fine. Okay. Yeah, there is a couple of voltage law. Fine. So equivalent resistances, all of you in kind of know this is you have series, parallel, some moderate level questions will also ask you delta star or delta Y conversion. This is where you have resistances like this. Three terminal. You have three terminals. 1, 2, 3. You can convert that into an equivalent three terminal this way. Or if we keep the terminals as such, or three terminals, you could convert this into three resistances this way where there is a load over. You can make this conversion. This is, some moderate questions kind of ask this. If you know this, that is very, very okay. So I'll explain, at least I'll introduce you what Norton Thevenin is. Basic power calculation. You all know this, right? So power dissipated is I square on, right? Notice power is in a DC circuit is fairly simple. This is just I square. And then again, Wheatstone bridge, I'll kind of explain what this is. You have to know few other things. That is basic voltage law, Kirchhoff's voltage law, Kirchhoff's current law. Okay. This is KVL as this, right? In a closed circuit, right? In a closed loop. Increases and decreases in voltage are up to zero, right? KCL, if you take if you take a part of a circuit, the current entering and exiting, net current is zero, right? What enters this boundary should be what exits. Let's say current enters at two places. What exits should be equal to what enters. Provided, nothing is kind of stored. As far as this boundary is concerned, what enters typically equals what exits. This is KCL. We'll also look at examples on the Kirchhoff's current law and then Kirchhoff's voltage law. You have the rises in potential. There are a couple of places where voltage increases, and then there are a couple of places where voltage drops. They'll be the drops and raises kind of equal. This is one thing you want to know. In addition to that, you also want to know division laws. You have basically two divisions. Okay, one is a voltage division, and then you also have current. So typically, notice. Let me just strike this one now for a time. Typically, there is a question from this the list that I have shown here. It's fairly very simple. On top of that, every year, almost every year, there is a question from Wheatstone. If you are lucky, there are two questions from Wheatstone bridge, one from DC, one from AC. Okay. So we'll cover most of this. Let's look at this question. Okay. Gate BM 2020, the nearest value of power dissipated and 3 ohm resistance in the circuit. Okay. We'll go ahead and answer this. Before you kind of answer that, can you all tell me your approach to solve this? You could answer that in the chat. What is your approach to solve this? This question again can be solved in many ways. Find current and I square R. So you want, okay, so now, okay, the suggestion is find I. How do you find I? Right, you find I, then the I square R is the power dissipated. Fair. How do you find that I? Current divider law. You have to be little more, specific, okay? Because current division directly is not applicable, but so we have to do a couple of changes here. See, those who are thinking current division and all that, there is a one more voltage source here. There is a current source here. There is a voltage source here. It's not like this 2 amp is going to split in this way, right? You have to account for this voltage. You have to take care of that. Yeah, now I'm starting to get, many of you are starting to improve your answers. Convert voltage source. See, there are two sources. And can you deal with them? Can you make it like similar sources? Source transformation and all that. If you do source transformation, perhaps things get easier. Okay. And then another thing is, hey, can you simplify the circuit with minimum resistance as possible? Yeah, again, you are kind of doing a source transformation. Girish is saying, hey, can you do nodal analysis? Okay. Notice this is a reasonably, this is a moderate level question, not like they are not spoon feeding you with the answer. Okay. This is a moderate level question. This is fairly easy. Now we can do this in a couple of means. One is apply KVL, KC. No, solve KVL and KCL. You can solve that. Okay. Another thing is, hey, there are too many sources. Can you do source transformation and simplify? Okay. Now you could, can we do, there are a couple of other ways, but I think these two typically kind of will give you the answer very, very fast. Can you do superposition? Yeah, but it's much easier to do some of this. So two sources are kind of hinting at me this. There is something else in the circuit that is hinting at me to use this. Presence of two different independent sources, a current and a voltage, is suggesting me, hey, try source transformation and simplifying. There is another detail in the circuit that is suggesting me you could also solve this quickly using KVL KCL. Okay. So first, let's learn this. What is a source transformation? We'll solve that. And then perhaps that involves a couple of, probably involves a couple of details. Let's do this one at a time. So we have source transformation. Source transformation. Typically any linear circuit, okay, just voltage resistance circuits. Let's say even independent voltage current sources. Let's not even bother about dependent voltage current sources. Okay. There are some complicated circuits. Okay. Notice. So again, if you have to give you an analogy, notice all of you know if there are two resistances in parallel, equivalently simplify this to one equivalent resistance. Now, what the source transformation is saying that you have a circuit with many voltage sources, many resistances. Okay, let's say there is a current source. Typically, in the source, there is in applications there is a load kind of thing across which you put your primary application. Typically, it's a resistance. So load is connected to two terminals. This is referred to as the load, typically a resistance. Okay, or yeah. What this transformation law says is you can take this circuit, okay, any linear circuit, you can take this chunk and simplify that. Okay. So across these two terminals, the rest of the circuit. Now notice this one resistance or equivalent. This is equivalent to these two, right? Essentially, wherever this is, you can replace that with the single resistance. Like that, wherever the circuit is, you can equivalently replace that with, okay, Interestingly, a single voltage source and a single resistance. If I had to complete the circuit, we can connect the load and this is working. So the circuit that I have circled is equivalent to this. This transformation is referred to as Thevenin, and this voltage, equivalent voltage for this entire circuit is VTH, and this one resistance for this entire circuit is referred to as RTH. Okay, so this is VTH, and this is known as the Thevenin equivalent. We also have a Norton equivalent, where again this entire circuit could be equivalently written as this. You have a current source, okay, in parallel with a resistor. You have this current source value is this is INO, this is RN. This is referred to as a Norton A. So circuit, this big circuit, any circuit can be written as either in the Thevenin form or in the Norton form. And they are all equal. So you can also go back and forth between this side and this. So the question is, now we have two questions. How do you go from here to here, right? How do you go from here to here? Then how do you go back and forth from here? There is a question one, then there is a question, how do you do this conversion? Question two is fairly easy. Question two, right? So your notice. So given Thevenin Norton is fairly simple, can anyone say what this I Norton is? Just from the V Thevenin, take the Thevenin voltage divided by Thevenin resistance. And one thing that really makes your life easy is the resistance doesn't change. So this happens to be R Thevenin, and this happens to be R Norton. So given R Thevenin, you can directly write R Norton. Given R Norton, you can directly write R Thevenin. So I Norton is this much. Say Norton circuit is given. How do you find the Thevenin voltage? V Thevenin is just IR. Take the Norton current. Norton, there is, R Norton is R Thevenin. Just take this resistance, multiply that. So this is how you deal with two. Let's kind of color code this. This is how you deal with, you can go back and forth. Then there is a question, how do you do one? We'll come back and answer that. Okay. But right now, let's go back to that question. Hey, there are two different sources. So use source transformation and simplify. If you know the current, it kind of simplifies, right? We could do it either way. But I am going to do, let's say, I'm going to convert this to Norton. So notice, these two can be easily clubbed together, no issue. So I'm going to draw a couple of conversions. Your task is to tell me which conversion is correct, where the values are. We have a 2 here, 2 amps. We have a 3 ohm here. Okay. We have a 4 here. We have a 4 here. This current will be 0.5. Option 1, option 2. So what I am doing is trying to replace this chunk, if you're wondering. So I am trying to convert, it's a Thevenin circuit, that bit across these two terminals, right? I'm trying to replace that with a Norton equivalent. So this is one option. Let's continue in this. Yeah, this is one option where we have values, let's say 4.5. Let's make that 2. Let's make this 2. This is 0.5 and this ohm is 3. Okay. Third option is, let's say, we have a 3, we have a 2.5, and then we have a 2. We have a 3, we have a 2.5, we have 2. So right now, task is pick equivalent circuit. Pick equivalent circuit. You have 3 options. It's an MSQ. Option 1 is this. Option 1. Option 2. Option. So all are equivalent. Someone says option 1. General says 1, 2, 3. Again, 1, 2, 3. So I have to give credit to everyone. Option 1 is correct. If you take that yellow chunk, if you replace that, option 1 is correct. In fact, let me color code this where you have, I'm going to write on the same impulse. Okay? So this is 0.5 and 4. In fact, again, if you have to write this in, from the Thevenin Norton resistance is the same, 4. Norton current is 2 by 4, that is 0.5. Okay. This is where I also notice these are connected, there isn't any resistances. These are all the same potential. These are all at the same potential. Same potential. Essentially, they all behave as one single point in the node. Let me repeat that. Okay. Notice, if I look at this point in the circuit, this point in the circuit, the potential is essentially the same. They are connected by wires with no resistance, negligible resistance. Same goes with all these are at the same point. For the same reason, all this behave as a single point. For that reason, if you change the order here, it doesn't matter. All the points here are essentially there is one point in the top, there is one point in the bottom. Okay. If you were to write this in a different order, it's essentially the same set. Thus, this is essentially the same set. So we have a 4 here, we have a 0.5. I can change the order. If you want me to slightly, notice, I clubbed these two resistances into this bit that stays here. You call this whether you call this yellow glow doesn't matter, but that chunk went here. Okay, so 1, 2. Do you agree with this? 1 and 2 are essentially the same. We'll go to 2 in a moment, but 1 and 2 are essentially this. Anyone has questions? Because essentially there is one point in the top, one point in the bottom. If I change the order, it doesn't matter. Now what I have done is same thing. I have clubbed this to this 2. Then I have clubbed here's blue already. Then I clubbed this to this. These two 4 and 4 in parallel make 2. Current source of 2, current source of 0.5. Notice net outflow from the 2 to this node is 2.5. This to this rose node. Net outflow here is 2.5. Net inflow here at the bottom is 2.5. They are in parallel. They get the two currents get added up. I've done that conversion over there. For that reason, 3 is also the same. So pick equivalent circuits 1, 2, and 3. All 3. And directly writing down 3 may not work, but typically you will have to either write down. Typically you write down 1, and then from 1 you write 3. Just to highlight, this order and all that doesn't matter. I introduced 2, okay, and to also explain this. How it looks and how it functions sometimes is, confusing in circuits. You need to get used to it. The looks as such are deceiving. You have to go by the functionality, equipotential points and all that. So typically you do step 1, then 1 you simplify that to step 3, and at step 3 you have the answer. Okay, so 2.5. How much of this will get split in 2? How much of this will go into this 2 ohm resistor? Does anyone know that? So I have 2 methods for this. 2 easy methods. Let's look at this method 1 or method 2. Okay. Given circuit becomes circuit 1, that becomes circuit 3. At 3 we can answer. Given circuit becomes 1, that becomes 3. At 3 we can answer. Can anyone say how to answer this at step 3? If this is not somewhat visible, let me also find out that. Let me, if you're later on reading this, which that means current division rule. All right. So notice. So whether you write it this way or you, again, it's one node at the top, right? Whether you write it this way or this way doesn't matter. You can change the order of the resistance because at the top you have one node essentially. At the bottom you have one node. You have a 2 and 3. Now the question is how does this current split between 2 and 3? You could answer it at this stage. Okay. So ideally you are coming from 1 to 3. Okay, at 3 you can answer. So you have current division and voltage division rules. Voltage division and current division. This is a circuit like this. You have 2 resistances in series. Let's say this is grounded. Grounded, you are using that as 0 potential. Let's say you are measuring potential with respect to that. If I have a source voltage V here, right? Essentially, I have, let's say, at the top, the voltage that I have here is V. And these 2 resistances are R1, R2. Question is, typically, we measure the voltage somewhere here. What is this voltage? This voltage. Sometimes, typically, we refer to this as the input voltage. Say, as in a potentiometer, we refer to this as the out. It says output voltage. It's a fraction of input voltage. It's a fraction. It cannot be greater than input voltage. Somewhere between 0 to 1 times input voltage. That fraction happens to be R2. The bigger this resistance, higher this voltage drop. So you have R2 by R1. Notice this is a fraction. This is essentially a fraction. Output is a fraction of this is known as voltage division. And when can you say that? In this, as far as this, this edge is concerned, this part is concerned, there is no current going out, no current exiting. Somewhere in the middle. As far as that is the case, you can apply this. No current exits in the middle. but the circuit that we had is slightly different. No, we had a circuit like this. You have a current source. That current gets divided between two resistance. That is, there is a net current entering and exiting this. Notice current I enters this, it should exit this. And again, we have resistances R1, R2. Question is, what is I1? Current in this resistance R1, current in this resistance R. Again, I1 is a fraction of the input current, total current entering. It gets split between these two. So it's a fraction of that. But how does it get split? Smaller this resistance, more current flows through it. Okay. So it's a fraction. Again, the term that you're going to have here is R1 plus R2 in the denominator. But bigger the resistance, lesser the current. Bigger R1, smaller is I1. Okay, more resistance to current flow. So what flows through I1, what flows through R1 depends on proportional to R. You could also, of course, compare this I2. Notice again, this is a fraction. Notice this the fraction of what is in here. I2 happens to be R1 by R1 plus R2 into what is entering. No confusions. With fraction. That is your current division. So in our given circuit, 2.5 amps is entering. How does it get split? Okay, easy. Let's go back. That question essentially notice there is a 2.5. There is a resistance of 213. How much goes into 3? At this stage, I can erase 4. Okay, I don't have to bother 4. 2.5. How does it get split divided between 2 and 3? That's fairly easy. So your current through R3 equals the total current entering, that is 2.5. Fraction of that depends on, it's proportional to the other resistance too. Denominator of which 2. So this is 2 by 5, this is 5 by 2. I suppose this equals 1. And your answer is in power dissipated. Power equals I square. R3 is a subscript in R. That is 3 watt. This is in amps. Everything is in ohm SI. So ampere square into ohm, that should give you watt. V equals, RA. Voltage equals, right? Volt equals ampere into ohm. Ohm ampere. That into ampere gives you power. So your answer here is 3. And want to just discuss this method. There are many other methods, but you can, if you're comfortable with this, you can fairly, get this. Yeah, do this transformation. Then, problem is 2 sources, transformation. Hey, this is actually simple. Couple of resistors in parallel. How does the current get split, right? Total current is 2.5 at that stage. Get split. So this is method 2. Any questions? Method 1, KVL and KCL. KVL and KCL. But how do they apply Kirchhoff voltage law, current law? There is actually something suggesting me, hey, actually even method work will give you answer very, very quickly. Can someone spot it? And I have given you some clues. I have already given you some clues. Can someone spot? It's actually fairly easy to find them. You can get the answer, no transformations, but you can write one equation and get the answer. And there is a very specific reason for that. So sometimes gate, I say, hey, this is a 2 scenario gate question, right? Scenario 1 to scenario 2, the typically you divide or something like that. Some common terms get cancelled. Simple algebra gets cancelled, right? Things are displayed in proper. Like that, this is a specific type of circuits problem. Very common type of circuits problem. Just in case on the day of the exam, which conversion to do, you are not clear. Okay. Somehow, that day you get confused with how do I go from, some of these things. Should I do Thevenin? Sometimes a confusion happens. Because is it a single variable problem? It is a single variable problem. So my claim is in that this is a single variable problem. There is only one unknown, finding which you can pretty much find everything in the circuit. Can someone spot that one single unknown? There was one unknown, finding which you can find pretty much anything in the circuit. So to find that one unknown, you have to write one equation. Source transformation, then on. So we already did source transformation. Fine. Source transformation, then no. Even before source transformation, there is only one unknown. So just in case you are confused, it doesn't hurt to ask this one question. Current in branch, fine. So how do you find that current in branch with a 2 ohm resistor? How is that? If you know that, how do you know everything else? Okay. Voltage across 3 ohm. General things, voltage across 3 ohm. Fair. it helps to ground one of this, a reference voltage. You ground this. If I put the ground here, or if I put the ground here, does it matter? Whether I put it here or there, it's all, it's all zero. Notice. This is all zero. Where I put the ground, that doesn't really matter. This is all of the same voltage. They're connected by wires with negligible resistance as far as the circuit is concerned, rest of the circuit is concerned. Where you put the ground is immaterial at the bottom. It's all one point. For that same reason, if you look at the voltage across 3 ohm, the same voltage here is the same voltage here. So it's all at the same voltage. See, again, so Girish, if you are taking that route, again, you're like, when you're presuming 0.5, you're likely doing source transformation. Okay. So we did it, we solved the problem, but it's just right now nodes. In fact, this is what I was trying to explain here. Hey, this is all, the whole top thing is at the same voltage. The whole bottom thing is at the same voltage. Essentially, it's the same point. Electrically, it's at one, essentially, it's a 1 point. Electrically, it's a single point. Electrically, it's same potential. It's a single point. It's a single point. So if that voltage is an unknown, okay, current entering that point is 2 amps. Current exiting that, let's say, yes, a current here, a current here, and a current here. We can all write that, all of that in terms of V. Okay. 2 amps equals the 3 currents. The 3 currents are V by 4 plus V minus 2 by 4 plus V by I1, I2, I1, I2, I. So net current entering that as 2 amps, exiting that node as I1 plus I2 plus I. Can you quickly solve for V here? I think that's fairly easy, right? So what this is, V equals dash volt. The current through that is 1. So V should be, I think, V is IR. V should be 1. Hey, V should be 1 by 3, I suppose. Yeah, not 1 by 8, 1 by 3. V is 1. This is current is V by 8. I suppose this is 1. Okay. That implies your current 3, that is current through R3 ohm, okay, equals, you don't have, technically you don't have to do this. Power in the 3 ohm, V square R. I don't think this is 1. If you solve it, I think it should get 3. And just someone confirm that. You should get 3 volts. So if you multiply by 12, you have 24 equals 3V plus 3V minus 6 plus 4V. All of us are getting different answers. 30 by 10 equals 3. So Janelle did 24 minus 6, 18 by 10 isn't. I suppose Janelle said 1.8. No. I suppose he did that. Yeah, 3 volt. So 3 volt, and then you get this power to be 3 volts. The answer is. Yeah, be careful about it. Of course, you could also do at this stage. This implies IR3 is 1 amp. From that, you can get powers. But also, you have V, I, given 2, you can find the other. I prefer writing this as V, I, or given any 2, you can find the other. Given any 2 in the set, V, I, or you can easily find the other. Fairly easy. And then you have power equals I square R equals V squared by R. You also need to know a couple of things. Variable SI unit. This is current. You have amps, resistance. You have voltage. You have volt. Okay. Notice. So you have voltage actually technically equals ampere dimensionally. In fact, SI, if you're calling SI, 1 volt equals 1 amp into ohm. And then you have your power. This is in watts. In fact, 1 watts happens to be equal to, you can either say ampere square ohm, or better is VA, V into voltage into ohm. VI is power. So in this question here, what is the power dissipated in a 3 ohm resistance? Equivalently, they could have asked you what is the current in the 3 ohm resistor, what is the potential in the 3 ohm resistor, right? So based on the same concept, okay, they could have equivalently asked, they as in the gate committee, equivalently, they could have asked IR3, VR3 ohm, simple modification. We tend to forget this. I'm going to do a quick poll. We call that apply. One as recognize where source transformation is potentially useful. Potentially not electrical, potentially useful. It's like possibly, probably useful, potentially useful. One thing. Second is apply voltage and current division. Third is, KVL, KCL, against, KVL, KCL. Do Norton, basic Norton, do basic Norton Thevenin conversion. One is to recognize, one is to apply Thevenin conversion. One more thing that we learned is look for single variable problem in circuits. Let's do a quick poll just to recall what we learned. You consolidate that before moving. Say before this, we may not have known voltage and current division. We half the class order. That was understandable. But I explained you. Two resistances, how does current get split? It's a fraction, right? Again, two resistances in series. How does the voltage get split? Again, it's a fraction. Just look for it. Look for if in the top. Is it all one? If it's the same wire, okay. If it's all wires at the top, probably the single variable. Wires at the top and wires at the bottom is a short sign of a single variable problem. So to this mix of sources, mix of potentials and amperes, it is hinting you, probably source transformation. There's one long wire at the top, one long wire at the bottom. Okay, the one long, green wire at the top. You likely there's one variable. If I solve for it, I'm done. Great. So most of you, okay, fair. Source transformation is by voltage current division is fair. Okay, we are kind of struggling, but we go over this once or twice, we'll get it. Not on the one and fine thing. This is fairly easy. Look for single variable problem. I don't really agree with it. Fine. Okay. So what I'm going to do is, you can solve this in a couple of ways. Solve this as a single variable problem. That's your task. Tell me what is that one variable, knowing which you know pretty much everything in the set. You have to name that one variable here, knowing which you know pretty much everything else. It's like one equation, you can solve this. Right? So your task is to not solve this problem. Your task is to identify that one variable using which you pretty much know everything. Or fine, yeah, I can see, or Thevenin is not the one variable here. Not yet. You can solve it with the Thevenin transformation. That's a different thing. But it's much faster to recognize there is one unknown there. Look for long patches of wire in the top and bottom. In the bottom, make it ground. In the top, make it an unknown. Where is the long patch of wire? So method one, is there a single unknown? This is a one variable, single variable. I'm just asking this question right now. Okay, not so long, but notice this is essentially one limb. Three things are in parallel. Okay, this is one of the parallel limbs. This voltage is same as this voltage. This voltage is same as this voltage. You might as well ground it. And notice VA is your only unknown. In terms of current, there is a current in 10 ohm. There is a current in the other loop. I1, I2. There are two currents. Voltage, there is only one voltage. The answer is yes. That one variable to begin with is VA. That is what I mean is you can directly solve for that one variable. No 2-3 equations. One equation you can solve for that. Yeah, 24 equals 12 minus 68. Probably you're doing some sort of source transformation. Okay, I will also do that, but notice here current entering is 1.2. Let's kind of draw this 20, 20, 10, 24. 1 point. My claim is there is one unknown voltage here. It is all at the same. It's a wire, right? Piece of wire, same potential, same voltage. Let's ground this. Whether you ground it here or whether you ground it here, it's all one and the same. It's the same point, I think. All three are one and the same. There is a current. Let's say I1, if there is a current I2. Notice what is entering is 1.2 equals I1. You don't have to write it I1, but this is essentially VA by 10 plus I2. It happens to be VA minus 24 by 14. To be consistent, this is VA by 10. What I have here is, I have I1 here, I have I2. VA is only unknown. You can solve one equation, one unknown, you can solve for it. See, other terms typically will have two equations or not. This can equally solve for it. This is 20 and 30, right? So this is 30, so this happens to be 50. Hey, can someone now solve for VA? What is the value of VA? So your VA happens to be multiplied by 50. 1.2 into 50 is 60. And you have 5 VA. There you have VA minus 24. And we have to be careful. Notice this is given to be this direction I30. That is what at the end of the day we want. Oh, that's not what. Right? 60 minus 24, 36. 6 by 6. 5 volts or 6 volts? One of that. Can someone just confirm that? 60 plus 24 equals 6, 14. 84 by 6. I'm going to go ahead and write this, okay? If I multiply this by 60, I get 60 equals 5VE plus VA minus 24. VA happens to be. Okay. So where is this 5 volts coming from? I'm puzzled by that. Even I'm getting VA happens to be 84 by 6. Happens, I suppose, is 14. Okay. This is 14 volts. That implies current will be, or what do we need? The voltage across the terminal, right? This is at 14. This is at 24. There is a drop. VA minus VB is at 24. Which means we can actually answer this. From 14, it goes to 24, right? So notice VB equals 24. VA minus VB, that would be minus 10. And this truth I can answer. Yeah, I can answer. Minus 10. Where was this 5 volts coming from? Just wondering, like, that one equation, I did solve it in mind. I got like 12 by, I thought 72 by 6. I thought 12. Okay, then it's not 70. Actually 84 by 12. Fine. 14 I understood, but why was this 5 volt? Where was this coming from? Again, you did 60 minus 24 by 6. Even that should give you 6 volts, right? 1.2 into 50 is 6. Okay, fine. This week is in fact, I really don't do this in the mind. Okay, we have a gate calculator, right? Every class I use a calculator. So use it. Right now, I don't have a calculator, which is why I am kind of, at least, while waiting for the answer, I'm doing that in the mind. But use a calculator, okay? Avoid it. But fine. In fact, what I'm noticing is this is one equation. We have trouble solving that one equation. Fine. We'll keep that as a last resort. Let's also go back to our first resort. This is typically that, silly mistake proof. Here also, of course, silly mistakes are possible, but, this is typically better. Method, did I call it method 1 or method 2, right? This is method. There isn't a mix of, again, mix of sources. There is a mix of sources. Do source transformation and do it conveniently. That is hinting that consider source. Am I audible now? Yeah. So there is a power cut, but we'll continue. Okay. The system that I have works with. Okay. So there is a mix of sources that was hinting that consider source transformation. So, hey, if I transform this, I'm going to get one single loop. Okay. So notice if I transform that, so I have the rest of the circuit 20, 30. This, that part of the circuit, I'm going to do a Thevenin. Why there is just one loop, you can, now you can just write it down. The one equation at the answer. See, only difference here is, here you wrote one equation directly, you didn't do any transformation. Here, after the transformation, one equation you can quickly get. Okay, so what we have, let's fill out the easy ones first. 20, 30, I'm not writing the units because fairly obvious. 24. So this 10 remains a 10, and this is just 12 volts. Fairly easy. Okay. From here, it's just, one equation, one. You can find the current here. You can find current, right? What you have here is 12 minus 24 by 60 equals I. This implies your I suppose, is 12 by 60. How much is it? Minus 12 by 60. So this is a negative number, minus 2 by 60, suppose. 2 by 10. 1 by 5. Okay, minus 1 by 5. Minus 1 by 5 amps. Okay, and then from there on, you have the AB equals I times 50. That equals minus 1 by 5 into 50. So your answer is minus 10. Again, be careful about the sign. This is minus 10. Current flow doesn't flow this way, but it is flowing the other way around. And while writing this equation, notice you're writing KVL, Kirchhoff voltage law. Okay. While writing this equation, sum of currents is 1.2. We wrote Kirchhoff current law. Okay. Although we didn't explicitly see that, right? We are kind of starting to apply that. Okay, fairly easy. Let's move on. Power consumed by the 3 ohm resistor is 12 watts in the given circuit. Value of the resistor R in the circuit. Okay, strategies for this. Strategies. If you want me to enlarge this, what is there in the 3 ohm circuit is 12. What we want to find is this R. Hey, while I am waiting for a response, notice some trivial things. Okay, many things. It's very hard to improve performance. Okay, acutely, suddenly you just do this magically improve your performance. There are not many things, but to spoil your performance, there are many simple things, many easy things you could do that can easily spoil your performance. Right? Dehydration is one thing because I'm where dehydration is one thing. Typically, Saturday classes, I used to fast. Because intermittent fasting typically Saturdays, one day a week, it's good for the body. Based on physiology, I used to fast. But so it's actually very hard for me to take Saturdays classes. So I have decided not to do that on a Saturday, but do it on some other day. So yeah, there may not be a superfood to improve your performance on the examination day. But if you skip the meal, okay, your sugar levels are going to go down, hypoglycemia, your brain is not going to work the way you want it. Basic, a decent meal, average size meal, again, too much, it's going to, your digestive system is going to imbalance, put your brain in imbalance. And then, too little, again, your brain will be in imbalance. So, average amount of food is essential. If not, you can easily spoil your performance. Proper dehydration, that is a must. Okay. Normal ones just carry a water bottle. I suppose that is allowed. Or even otherwise, there should be drinking water available. Feel free to go every half an hour or something like that. Go, feel free to have a cup of water. And so during classes, don't get to this habit of during your classes, don't get to this habit of having a snack, because notice you are controlling your glucose levels in the blood. Okay, by that you are also controlling the fuel that is available to the brain. You may not be able to do that during the examination. You may not be allowed to snack during the examination. So how you perform? 3 hours I can easily manage. I can do mental exercise. That's what you might be thinking. But on the examination day, because you are not allowed to snack, it can actually hamper your performance. And ideally, most examination halls are air conditioned. So if you are not used to, this cold room, okay, don't drink lots of water, else you are like running to the restroom every 30 minutes. Drinking water is like 2 minutes. Restroom, it takes like 10-15 minutes, right? So be aware of this. Very hard to acutely, that is on the examination day, you cannot do something to drastically boost your performance. But on the examination day, you can do something silly to actually drastically decrease your performance. Be careful about it. Food, hydration, ventilation, or the environment, your posture. Okay, don't take that for granted. Whatever you do in the examination hall, try to start recreating that. Okay, with that, the current here is on. Yes. So I suppose the strategy is from that we get the current. We get the current in the 3 ohm. Yeah. See, if you get the current in the 3 ohm, you don't know the current, right? You know the 3 ohm current. What can you do with it? See, this is an unknown. It's not a single variable problem. It's not a mix of sources. But this is like right? It's not a mix of sources. Mix of sources. Let me get the scale correct. I'll zoom in one in. Is it a mix of sources to consider source transformation? No. Is it a one variable problem? No. Are there stretches of I try to draw this here? By the time I draw, there is a jump here, and we kind of know, right? Even if you were to ground it here, notice, okay, this is a 10. This is one variable, but again, you run into this issue of what is this current here, right? You cannot solve for this voltage because you don't know this resistance. You cannot really solve for. Again, that trick doesn't work. And this is what I call. Can someone complete that? I want to write a word, but I have written like partially. Can anyone complete that? Hey, this meeting is still on, right? Let us confirm that. Yes. Can someone complete the word now? Seriously? Yeah, this is what I'm going to refer to as the Sudoku network. Sudoku problem. It's like you start filling in details. Wherever you are responsible to fill, you kind of fill and quickly realize, hey, all details is fillable. It's actually a very rare problem, but the moment you identify it, you can easily solve it. Okay, so I gave it a special name. This is 12 volts. So I know the current. Current is I square R is 12. So I suppose that as 2, I is 2. Agree? That is my step 1. My step 2, I know the voltage across. I'm not short circuiting it. I'm trying to find the voltage across that. I know that. This is voltage there as just IR 6 volts. Let's zoom this a bit at this stage. I know this voltage 6 volts. This is step 2. So this is at a higher potential. Current flows this way. It's not like, current flow direction is the same. It's not like R is 13 ohm. Yeah, we'll come to that. Okay. So at this stage, I know the voltage drop, but I do not know the current. At this stage, I cannot answer. I need more information. I need somehow the current. I need to look at the rest of the circuit for that. I need to know the currents here, right? But quickly, I just solve this. This is 6 volts. Step 2. This is 10. This is 6 volt drop. That means this drop is 4 volts. That is step 3. There is a 10 rise. There is a 6 drop. It has to be drops, okay? It cannot be, current cannot be in different directions in this resistor. They are all parallel. Only the values can, magnitudes change. Direction remains the same. Higher potential in the left-hand side, lower at right-hand side. Current flows from this side to this side. Current goes from this side to this side. There is no question about it. Okay, so there is a 4 volt drop here. Hey, I know this resistance, so I can quickly find out the current. I know this. I know the voltage drop, so I know the current. This current is 4 amps. This current is 2. This is 2 amps. That is my step 4. Hey, I'm essentially, I'm doing what we will do in a Sudoku. 4 amp, 2 amp. Is that correct? Potential of 4, and then there is a 4. Okay. I know 4 amp, 4 amp. So this is 6 amps. Call that step 1. 6 amps. That is step 5. And I know this resistance. So if this potential I know is like 6 volts. I kind of know this current. I can fairly write it at step 1 itself. And I'm going to do that here. This current, how much is that current? That is 3 amps. How do I know that? 3 times 2 is 6, the drop that I want. So total current is 6. 2 goes here, 3 goes here, 1 goes here. That is the last step, and I think you can kind of get the answer there. So again, to be careful about the units, this is 2 amps. That is of course, my first step. That is in blue. My last step, the current. Steps 1, 2, 3, 4, 5, then we'll do 6. IR equals 1 amp. What is the resistance? Let's see, each step, there is no equation, no solving and all. I just use V is IR everywhere. But I kind of traversed it, essentially what we do in a Sudoku, I did. Why I did that? Hey, gate problems has to be solved in 2, 3, 4 minutes. Except there are 1 or 2 questions deliberately implanted to waste your time. Okay, to make the uninitiated waste time, crucial time during examination. The committee inserts 1 or 2 time wasting questions here and there. You stood for 2 days, we cannot solve it. They deliberately inserted. So is the student smart to avoid it? That's what they want to check. They don't want to check if the student smart to solve it. They want to check if the student smart to avoid it. There are always 1 or 2 questions. So typically, if you are 1 page derivation, if it's going beyond that, I would skip that question. Any question. That 1 or 2 marks is not worth it. So here, notice I haven't done one or 2 page derivation. My known tricks, a simple resistance circuit. Is it a mix of sources? It's a single variable problem. No. Then special case, say Sudoku, can I do this solve it just like that? Yes, this happens to be 6. Okay, so this is 3:30. We'll likely give 4:30. Okay, yesterday itself we finished kind of early. Okay, so let's summarize. We have done KVL, KCL, equivalent, series, parallel, and delta Y also. Let's say okay, it is there in the recorded videos, there in the notes. So in some assignment problems, this is a KVL, KCL. Then what else? All basic power calculations. V, I, R kind of problem, and then P is I square. These are the kind of problems that, and here we used. So far, specifically, again, you have to list the sources, then single variable. Single variable is typically single voltage, okay? Single variable. We have also seen miscellaneous Sudoku, miscellaneous. And they can do few more things with the Wheatstone branch. Yes, this is all 1 semester's worth of electrical circuits, okay? We are doing that in a couple of hours, maximum couple of weeks. Okay? So, lot of condensation, evaporation, all of that is happening. Information is getting condensed as well as it is getting evaporated. There is this memory retention problem. So They can ask you a few more things with resistance, but fortunately, they are also fairly easy. One is called the max. There is a power theorem. There is this. What should be the resistance value so that the power dissipated in it is maximum? Then there is a Wheatstone, which in fact, I should put it this way. Typically, they ask you this. One question from here, one question from here. You get two questions from what we are learning today. If you are fortunate, Wheatstone bridge, sometimes 3 questions, but yeah, you need some AC bridge concepts. So yeah, typically, you get 2 questions from what we do today. Okay, so now let's look at max. In the circuit given below, what should be the value of resistance R for maximum dissipation of power in R? Concisely, can you tell me, how do you find R? Concisely, as concise as possible. Sir, that resistance should be equal to this. You can state it equal to this. You can state it in 2-3 words. I don't want to say you do this series parallel conversion, pi delta conversion. There is a pi network, sir. You can do that. You can do the y, or then there is a delta. You can convert to y. None of that I'm asking. Single variable source conversion, none of that. R has to be this. Two or 3 words. R equals dash. Not a number. Couple of words can fill that. In other words, when they say what should be the value of resistance R for maximum power dissipation in R, that they're asking a slightly different question, equivalent question. In the circuit given below, this whole sentence you can replace it with one word. You treat this as a load, vs RL, RL. No, RL, yeah, that is RL. No, R load doesn't really help. You have to look at the circuit. You have to get something from the circuit. In fact, so you can answer in 3 letters. So, Janil, which question are you referring to? Is it's time consuming, but we can do just trial and error. No. This again is an easy question. If you know what they are asking, it's a very easy question. It's not time consuming. Chanakyan is fairly close. He said 2 letters, RL. I think the answer is 3 letters. R is one of them. You have to, there are 2 more letters you have to fit in. For max power dissipation. Or transfer theorem, 3 words. I should give credit, okay? If not 3 letters, I should give credit for this. For the questions or the conditions stated, R equals 3 letters or Thevenin. Is power transfer theorem. Power transfer from this part of the circuit. Notice it's a linear circuit. You can essentially put a Thevenin equivalent there. From that to the load is maximum when the circuit's Thevenin resistance is same as the load. This is a circuit. The load here. And write this as load. You can see this as a load. Now, if we quickly notice this part of the circuit, let's keep RL that way in the 2 terminals. Let's draw this. This entire circuit can be replaced with 1 voltage source, 1 resistance. This happens to be Thevenin. This happens to be R. For maximum power dissipation in the load, RL has to be equal to R Thevenin. That is power transfer. This goes by the name power transfer theorem. So what are they asking? What are they asking? They are asking you to find R Thevenin, right? So the whole question in other terms can be stated as find R Thevenin, which is what they have stated this way. What should be the value of resistance R for maximum power maximum dissipation of power in R? In simple terms, find R Thevenin on this. Okay, is this question clear? We'll go, sir, how do you find R Thevenin? I haven't really explained that. So we'll have to. Hey, there was a minor connection issue. Hey, can someone tell me what is the last thing you heard? There was a minor connection issue. I just tried to change the connection. Power is back on. I put it in that fiber. Hello. Am I audible? Hello. Okay. I didn't get response for the power transfer theorem. So I said the question essentially says find R Thevenin. That comes from power transfer theorem. Are you all with me on that? Because the theorem says for maximum dissipation, load resistance equals circuit's Thevenin resistance. So now the problem is, the question is essentially find R Thevenin. That is what power transfer theorem says. That Kirtana answered that. Now the question is, sir, how do you find R Thevenin? We know how to go back and forth from Thevenin to Norton. But from circuit to Thevenin, how do you do that? Is what I was about to do. Norton to Thevenin, right? This step we did. But how do you go from any circuit to Thevenin? Once you go to Thevenin, you can go to Norton. But how do you go to Thevenin? That's what we are going to do now. Circuit to Thevenin equivalent. So to find R Thevenin, remove all sources. In fact, remove all sources. Let me be more explicit. Remove, that is, you're either going to short or open. Short or open all sources. That is, sources as in voltage. If it's a voltage source, you're going to short it. If it's a current source, you're going to open it. Okay. To remove all sources and find our equivalence. That's it. Remove all sources. How do you do that? Voltages you have to short, current you have to open. What do we mean by that? Let's look at an example. Let me redraw the circuit. So how many sources do we have here? I have one source, one voltage source. How do we remove that? Should I open or short circuit that? I should short it. This is shorter. Essentially, I can remove that voltage. This is short. By that, I can remove this. What is left is only resistances. I can find R equivalent. R Thevenin equals R equivalent here after all removing all sources. Can someone quickly tell me what is the equivalent resistance here? No. This is 2 and 3 in parallel, that in series with 1, 2, 3, 1, all okay. Okay, notice here. R Thevenin equals R equivalent here. That corresponds to 2 parallel to 3 plus 1 kilo. 2 and 3 in parallel, that is 6 by 5, 1.2. That equals 2 point. That is your notice. So Thevenin is for the rest of the circuit. So I didn't put that RL here. Don't put RL and find, sir, there is RL in parallel with 2 and 3. This one in series with 2 and 3. And there is also RL. Don't put that RL there. It's like across the terminal, what is the rest of the circuit? That is what we are looking at. Be careful about. Let's also find VThevenin. Sometimes we are required to do. To find VThevenin is essentially voltage across RL, across a load, voltage across a load resistance. And we slightly improve this across voltage across open terminal or voltage across open terminal. You're removing RL and then what is the voltage there? You're not finding voltage with RL. So you're removing RL open terminal or because again, this is for the rest of the circuit. This is not pertaining to load. You can put any load, right? Let's also go ahead and do that. Moreover, I have solved the problem. Moreover, to find VThevenin, not required for problem, and let me take not required for given problem, not required for given problem, just in case they ask a given problem. Again, remember you have a load. Hey, when is this Diwali, by the way? I am starting to hear some crackers being burst. You can put a little more. I suppose my neighbors are bursting crackers. So rain, storm, Diwali, we will conduct this class. Rain or shine, we conduct it. Yeah, I remove the load, open terminal. What is this voltage? Okay. So notice the moment I remove that load, this is essentially 1 point because no current goes there. It's open terminal. If I were to ground this, okay. If this is V in or this is, let's say, VR. In fact, this happens to be VThevenin because current here is 0. This is open terminal by definition. To find VThevenin, you have to open terminal across load. So we have opened it. Current there is nothing. It's not connected. Current cannot flow. For that reason, this is also VThevenin. These two are one and the same. And this VThevenin is fairly easy to find. You have 10, you have 2, you have 3. Can someone tell me what is VThevenin? Hey, time is 4. We'll finish at 4:30. Okay, some 15 more minutes. I have to do Wheatstone branch. Oh, perhaps let's finish with this problem. I told you Wheatstone is a different. Let's just look at an example of finding VThevenin and we'll wind up. How do you find VThevenin at this stage? Fairly easy. I hope someone answers this. Notice the voltage across this terminal. If I ground it, these two are the same, right? These two are the same. No current flows in that resistance. So what is the voltage here? That's what we want. You can write it down. VThevenin is a voltage here. If you do not follow, at least you should raise an issue. Or is finding VTH somehow difficult in the circuit? I also said, see, that problem is solved. One RL has supposed to, for maximum power transfer, power dissipation, RL has to be RThevenin. Found RThevenin, we solve that problem. I'm just telling you how to find VThevenin. For instance, how to find VThevenin, I'm showing you an example. Nothing more. I'm not solving this problem anymore. Let's in fact erase this. Here, like, sir, what will be? It's all what is happening here, right? Let's erase this. Let's erase all of this. Just how do you find VThevenin? I'm giving you an example. Or do you have doubts, sir? Why is the red VThevenin same as the gray VThevenin? Is that your question? I said VThevenin is this voltage. Okay, let's say this point is grounded. It's all the same point at the bottom. It's all the same. It's all the same, right? And I said, this is VThevenin. Why? This is VThevenin. Why is this? Where are you stuck? where are you? You stuck. Let's Pritijat. Purna. Okay, Pritijat is kind of answering it. Fine. So I suppose none of you are stuck. Guru, Karthik. The current here is 0. 10 gets, total voltage here is 10. Across 3 is just a fraction of 10. What fraction? You know that. Voltage division. And why do we put a equal to the nodules? V7 equals a fraction of 10. What fraction? 3 by 2 plus. Okay, fine. Let's do a quick poll and then we'll wind up, okay? So 2 months in the semester is over. KVL, KCL, basic equivalent circuits, Norton Thevenin conversion. Between Norton and Thevenin, you can convert. From a circuit also, you can convert. Power calculations you can do voltage current application. What you have done is Wheatstone bridge. Last bit that we did here is, how do you find RThevenin? Remove one sources. If the voltage shorted, if the current source, open it. Then find equivalent resistance across the load. Find VThevenin, voltage across open terminal or that's it. Okay. Okay. So I think most of you kind of will come back with Wheatstone notice. What we'll do in the next class? Wheatstone, there is a question every year. And then first order circuits. We'll move on to first order circuits. Again, first order circuits. What does a capacitor do? What does an inductor do? That's fairly easy. RC circuit, a lower R circuit, energy conservation, impedance, transient response. So you can say this is fairly easy. Okay. The question so far has been, most questions has been very, very easy. So we'll do that and then there is second order circuits. So we are doing PYQs in a concept wise. And so far we have seen all those. Resistance based circuits where we do, it's a one variable question where voltage at the top is an unknown. And then we have seen questions where there is a mix of sources or using source transformation kind of simplifies your life. And then this particular question we noticed circuit given below, what should be the value of resistance R for maximum power dissipation. So we know this is power transfer theorem. And here what we have to do is to convert this, if you treat this as a load, right? You have to convert this as into equivalent Thevenin form. And then there is maximum power dissipation or transfer when you have RL equals. So this is R Thevenin. And then here you have R, this, this load resistance. Typically, this is referred to as load. And this is V2. Yeah. So far, we know how to go from some circuit. We can go from circuit, to this. In fact, first is we can do this. Thevenin, Norton, we can do, right? For the typical circuits where there isn't any dependent thing, right? What is dependency? This is independent. Simple voltage source, simple current source that that is an independent current source. At least for simple circuits, you know how to do this, right? At least for, let's say, simple, that is circuits without any independent things. And here you have maximum power transfer, maximum power dissipation. This happens when your R Thevenin equals RL. Right? This is a condition for this. This also we have seen. So we have seen this. We can also, for example, application of this is in maximum power transfer theorem. So power transfer. What we have to do now is the Wheatstone bridge. So the Wheatstone branch, let me draw this. Typically you put a sensor inside the bridge and the bridge gets imbalanced. Did we discuss quarter bridge, half bridge and all that? Have we not discussed? When we did bioinstrumentation, when we discussed resistive sensors, did we mention quarter bridge, half bridge, the gauge factor and all that? We have done that. Anyways, at least I will recall that again when we do measurements. But so most of us know what a bridge circuit is, right? Now let's look at a simple bridge, okay? Notice you can draw the bridge in a couple of ways, right? We are used to looking at the bridge this way. So typically you have a voltage source here, and then you have, you try to take off info here. So typically this is referred to as V input. You try to take this output here across this. Okay. So for a balanced bridge, first let's look at the scenario. We have R1, R2, R3, okay, where let's say this bridge we refer to as a balanced bridge. What is a balanced condition? When we say balanced, what do we mean by that? And what is a balanced condition? Balanced bridge. We refer to something as balanced bridge. And then what is this balanced condition? Let me just write this as Wheatstone bridge while I wait for an answer. Wheatstone bridge. What do we refer to as a balanced bridge? And then what do we refer to as what is a balance condition? When will this balance be? I think this we have seen in high school. Some of you could recall it. Yes, in R3 is equal to R1 open R. Okay, fine. So this balance condition is R1 by R3. This by this equals this by this, right? You could also write it the other way around, right? Technically, this by this equals this by this. Notice you take R2 here and then R3 here, right? You get R1 by R2 equals R3 by R. Things in the ratio in the same sense. Sorry. Okay, this is a balance condition, but what do we mean? What do you mean by balance here? Can someone also say that? This also implies 1 by R2 equals R3. No voltage generated. Balance bridge essentially says V out is 0. How do you come from here from here? Now there is no voltage generated, and we also presume if we were to connect this, right, there is no current here. I equals 0. There isn't current any flowing in this bridge. Okay. And then you also have resistant current in the bridge. I bridge is 0. Okay. I bridge is 0. And you could use something like voltage division to actually arrive at this balance. You can find the voltage here is in voltage division in the upper arm, voltage division in the lower arm. You can easily arrive at this. You can use voltage. Now, easiest ways. You could also use some other circuit law drawing. Now, you could also redraw this in a couple of slightly different looking, but the same way. Okay? I mean, same bridge. You could equivalently, similarly, you could also have a bridge like this, where you could be connecting the power source here, right? And then you could be measuring things here. Take the output here. You can have the power source input source. It is also a bit notice. This point and this point, you can, it's a 1 point, right? You can also slightly do some aesthetic changes here. You can have, this is essentially same as this circuit. Here, there is one yellow wire, right? And then from here, there is one rose. There is a single point, right? There is no voltage drop across a wire. It's negligible compared to other resistances here. So we are having one resistance, okay, and then one more resistance. Then we have one more resistance here, and then one more resistance. We try to take the output. All I have done is to make some aesthetic changes. The same circuit, okay. Even this, I have just rotated the circuit, so it's essentially the same circuit. Now, technically, to measure this voltage, you'll have to put some device over there, right? So, you can run into one interesting issue. Let's just read this question. Okay, you need to understand something before we can solve this question. Let's zoom this. The circuit shown below, Vs is 100 volt, S is 100 volt, R1 is 30, R2 is 60, R3 is 90, R4 is 45, R5 is 30. What they want is the current flowing through resistor R3. Quickly, if you look at, is the bridge balanced? Is the bridge, is it balanced? Question number one. Try some of the things that you right. The ratio, this R1 by R4, it's not equal to R2 by R3. The answer is no. Roughly R1 by R4 not equals R2 by R5. But that's not the only issue here. There is also a bigger issue. A finite bridge or an infinite bridge. If you look at the bridge resistance, the second detail that we need to do here is bridge resistance. It can be of two types. It can be finite or infinite. Which of the two scenarios is this one? Is the resistance in the bridge here, right? This R3, is it finite or is it infinite? This is finite here. Okay. Interestingly, if you make things, okay, notice in this case, your I equals 0. Easy to handle. Okay. Infinite bridge is easy to handle. Okay. Notice infinite bridge, I equal to 0. This is an easy case, easy problem. Why you can apply voltage division, for example. But in this finite bridge, it's actually hard. So what do we mean by this? Let's look at this easy problem. Okay. What do you mean by this? This case is easy. This particular case is easy. Case, the finite case, what is given in the question is relatively harder. Let's do the same thing. Okay. Notice, let's call these 2 points A, B for reference. This is A, this is B. Okay. We have V5 here. Quickly, let's look at this easy problem. Let's say this resistance is infinite, that is not connected. Okay. Easy problem. And someone tell me what is VA, VAB, that is VA minus B. If you want the numbers, let me just give this, and this voltage is 100. This resistance is, I suppose, 30, 45. We have 60, 100. Can you tell me what is VEB? Notice the currents here are 0. It's easy problem. Specifically, it's not connected. This R bridge is infinite, right? Easy problem. That is, bridge resistance is infinite. Bridge resistance is infinite. In this case, can you tell me VAB equals VA minus VB? Okay. VA is a fraction of 100. It happens to be 45 by 75. And AB is a fraction of 100. It happens to be 30. And this happens to be, I'm considering a alternate problem. How we consider as infinite, it is an easy problem. I'm not solving this problem right now. I'm solving an easier question. We'll solve this and then we'll go back to the hard problem. How we consider as infinite, let's say they give you this question, they ask you to find V. I'm just telling you this is easy. What I have done here is I have applied voltage division. Why can I do that? Notice the current, I know bridge resistance is infinite, so current is zero. And can you tell me what this value is? I suppose this is correct. 26.674. Okay, how can you find as a bridge finite or infinite? You look at the values, right? For example, in this question, it's not connected by a wire. So what is the resistance between them? It's infinite. No current can flow through it, right? In this case, question, this is given, right? R3 is 90 ohms. R3 is given to be a finite value, 90 ohms. If R3 is infinite, we are looking at this question. This is, notice, R3 equals infinite. Okay, so this is 26.67, and the current here is it. And IAB, I bridge is 0. Is it label here? Notice. IAB equals I bridge. You know both the currents and you know, okay. See, R3 is infinite, implies IAB equals I bridge equals 0. In fact, which is why we kind of applied this voltage division, right? We could apply this. Take this, given problem. Can you apply voltage division? So label the same points. Call this A. Call this B. Can you find VAB? We find the notice. To find the current in R3, the current flowing through the resistor R3, we have to find VAB because current, the resistance, you find the voltage, you can find the current, right? Even here, the question boils down to what is VAB, and this is what I refer to as the hard problem. The bridge resistance is finite, so this is hard problem. How do you know that? Let me say R3 is R3 in this case is T. You cannot apply voltage division as we did here. So what do you do? Just notice IAB is VAB by RAB, R3. Okay. So now our question is, what is VA? From what we have learned so far, can someone tell me, say, how to solve this? Find VAB, we are done. But it's not as straightforward as if R3 is infinite. What do you do? And let me also tell you one more thing. This is a problem that we can solve with what we have learned so far, with the tools that we have learned so far in circuits. All source transformations, all series parallel, one variable source transformation series parallel, we can kind of do this. But can someone clearly and concisely state how to find this VAB, or in fact how to solve this problem? So if you had to point this out, notice IAB equals VAB by R3. But now the question is, what is VAB? This is finding this is related. You can't apply voltage division. Come on, with whatever we have learned. So what do we what so what are the things that techniques that we have learned so far? 26.67 divided by 90. No, you derive 26.67 without that resistance. If you put that resistance, the VAB will be different. No? Here it's a pair gas. Here VAB you can find it because you can apply current is 0, voltage is 26.97, 26.67. But the moment you put a resistor there, current will need not be 0. We already saw this is unbalanced. Current is not 0. In fact, that's what they are asking you for. Hopefully one of these four values. VAB doesn't remain the same. So what to do? Quick answer. You do source transformation. You do equivalent. In fact, you do a circuit transformation. R3 connected at 2 points A and B. You have to find an equivalent circuit. You have to do Thevenin equivalent. Right? Rest of the circuit. AB is here. You have point A, point B. Rest of the circuit that you approximate. It's Thevenin. So you have BT, you have RT, and this remains by definition. This remains. So now the question is, how do you go from this to this? You go from this to this. You already know the two things. Find VThevenin, you have to do certain things. Find RThevenin, you have to do certain things. To find VThevenin, all sources. I mean, VThevenin is just this in the original circuit, open circuit voltage across the load. RThevenin, remove all the sources, find equivalent resistance. To find VThevenin, let's find RThevenin. Remove the load in the circuit. Technically, what I am doing is I am shorting the source. I'm shorting this. I'm removing the source. Short. And what I have to do is to find R equivalent across these 2 points. I have point A. I have point B. So now I have made AB open circuit. By definition, I'm removing the load. For the rest of the circuit, so remove the sources, find RE, R2, 4. So this is RS or equivalent below. That is, we'll come to that in a moment. Okay. Now we have to find RThevenin, you have to find VThevenin. The moment you have it, it's a simple circuit. No, you can actually find the current. No big deal. You can find the current through R. Step 1, you need this. Step 2, you also need VThevenin. How do you find VThevenin? This is what I have done. Remove the load, right? Voltage across the load terminals. Notice this by definition, AB here is essentially VThevenin. All I have done is remove the load, find the voltage across the two load terminals. Is by definition VThevenin. So to find what I have done is to find VThevenin. We did this. We already did this. See? We already found the VThevenin of the circuit. It's a simpler problem. So you remove the load or the load resistance is infinite. What is the voltage across the two terminals? You can find. So let me mark that. Your VThevenin is in fact, let's get a fresh page. VThevenin, we found this to be 26.6. You have to find R. How do you find RThevenin? Can someone again concisely tell me RThevenin is essentially there is a equivalent resistance here between A to B. Is this series parallel in terms of R1, R2, R4, R5? Okay, you are telling me numerical value, but some of them might be lagging. And what I need is rather that in terms of series parallel, can you tell me, is it a series parallel thing? In fact, let me give you two options, okay? Option 1, option 2. We have R1 parallel R2 in series with R4 parallel R4. Another option is R1 parallel R4 plus R2 parallel R5. I'm trying to write down R equivalent here. Tanasi is option 2. Is there anyone who thinks it's option 1, or can someone explain why option 2? Not this option, it is this option. The simplest way to look at that again is essentially the same point connected by a wire. It's all the same point connected by a wire. It's all the same point connected by a wire. You have A, you have B, and then you have voltage source is shorted. This is shorted. That's the procedure for it. Now you could call this point C. I have point A. Okay. I have point B. And then I have point C. Point A. I have point B. What I notice is from A, resistance going to R1 going to point C, R4 going to point C. Is all the same point. Why is that the case? It's the same wire, no resistance. Equipotential. From A, there are two resistance going to point C. We have one of them is R1, another one is R4. B, there are two resistance going to point C. So C to B, there are two resistances. These are R2 and R5. Notice, so R1 is parallel to R4. That is in series with R2 plus R5. Can we do R1 plus R2 parallel R4? No, R2 is not parallel to R4 because R4 is going from A to C. From B to C. A and B are two different points. No, you cannot do that. 4 is between A and C. R2 is between B and C. You cannot do that. General fair question, but you cannot do that. There is like only one equivalent, correct equivalent thing here, and that is the option 2 that I gave. But explanation makes sense because this is a place where students get slightly confused, and that is understandable. That's why I try to somewhat color code and explain. Then did you get it?
Yes, sir.
Get that very well. Fine. So okay, the others. No. Can you tell me what this R Thevenin is? I think you can turn off your mic whenever you want to use it. You could turn it off. Yeah, what is this R1 parallel R? Wait, that is simple. No, R1 R3. Do you want the values? Fine. Let me write them here. What we want is R1 parallel R4 plus R2 plus R5. This values happens to be R2 is 60, R3 finite resistance, bridge resistance that we know fine. This is 60. R4 is 45 and this is 30. So we have 30 parallel with 45, 60 parallel with 30. How much is this? Everyone's sake, I will also write it down, but I'll erase it. Okay. This 30 parallel 45 plus 60 parallel. Give me one number. 30 parallel 45 is 30 into 45 by 75. By 30 plus 45. That is 75. 60 parallel 30 is 60 into 30 by 60 plus 30, that is 90. R1, R2. So Kirtana, I think long back answered 38. Fine. Others, Kirtana went to the next step. So current is 0.208. Suppose that is correct. It's 0.2. What to erase this happens to be 38 ohms. We need this number, 38 ohms. Okay. And now if we go complete the problem, so we know Thevenin, R Thevenin, it's a simple one loop circuit. We can answer that, right? This is 38 ohms. This we know as R3 happens to be how much? I suppose this is 60. Right? Make sure that it's 60. R3 is 90. 90. And now there is point A, point B, across which we found B. Now there is a load that the rest of the circuit is simplified. It. What we want is what is the current through this? A parallel, very, very simple. I is just P Thevenin, right? These two are in series. R Thevenin plus R3. Notice, long time back, someone asked me, sir, is it 26.67 by 90? Notice, we missed this R Thevenin factor. This is 26.67 by, you have R Thevenin 38 plus 90. 38 plus 90, right? This is how you deal with this. Finite bridge resistance. What is the thing? So do source transformation or find the Thevenin equivalent, then you have one loop and so on. Okay, this happens to be, I suppose, 0.208 amps, and this is your amps. And you could go here, this is your amps. Option B, that is option B. This is amps, this is not A, B, option A, option. This is option B, that is 0.28 amps. So that completes the next important thing that I wanted to discuss about Wheatstone bridges. Let me recap. See, to find maximum power transfer, you have to do this Thevenin and R Thevenin business. This bridge resistance is finite. That is, if a current can flow through it, again you have to do a Thevenin and R Thevenin transformation. No. Current is not negligible, right? Zero is, current being zero is different from current is negligible, right? Even this is like 0.02 is like finite. So technically, so the infinite is essentially zero current. Close to zero, no. In fact, close to zero matters. See, the resistance is kind of finite. The current is too small. But that would really depend on how balance or imbalance the bridges are. In fact, the given scenario, they have made a diagonal change, right? Let's say all three are 30, 30, 30, 30. They have increased this side by 45. They have increased this side by 60. They have created an imbalance, right? 30 plus 15 here, 30 plus 30 there. There is an imbalance. Because of which, there is a current flow. So, notice they are creating an imbalance at diagonally opposite sides, right? So that there is imbalance. So, negligible and zero are different. Okay, let us, and the direction of the current, plus 0.21, right? The AB we marked it, we have to hold on to that. Actually, these two resistors are telling whether VA is higher or lower compared to VB. In this case, VA is higher than VB. So, direction of flow of current, I suppose that is shown. Okay, one of the details we have to be careful about is the current flowing through resistor R3. Okay, they have shown a direction there. They have put an arrow from A to B, current is flowing. If they have given a different direction, the answer is different. Okay, be careful about the arrow because we know this VA is higher than VB or the Thevenin voltage, right? VA is positive. VA is at a higher voltage. Be careful about that detail also. Okay, to summarize, we have already done this. Last time we did lots of Thevenin to Norton conversions, but we also learned circuit to Thevenin conversion, right? This is useful both in case of the maximum power transfer theorem questions like this one, where you have to replace a circuit like this here, or it's also useful in case of a finite bridge, which finite resistance, which don't. Infinite resistance is fairly easy to answer. In fact, it shows up as a sub problem. This is fairly easy, and in fact, it shows up while finding the finite bridge is fairly, relatively harder. It involves you have to find R Thevenin, you have to find V Thevenin. Once you do that, that's it. You can easily get it. Right? Be careful. Students make a mistake while finding R Thevenin because they typically write option 1. Okay? You have to see where the equipotential points are. Connected equipotential points will behave as 1 point. If all the blue thing behaves as 1 point. It's all resistances. Those are wires. Okay, this compared to this, isn't there a negligible potential drop in the wires? Compared to this, the changes are happening in 6th or 7th decimal place. Right here, that is the difference. When is it negligible? It would be a fair question, sir. Wires are having at the end of the day has some finite resistance, right? There is current through the wire. There is a potential drop. It is happening 6th or 7th decimal place. Now, what I have here is, let's summarize. Okay, max power transfer. We have infinite bridge resistance. Let's kind of write it in a slightly different order. You have two bridges. You have finite bridge resistance stone bridge, and then you have infinite bridge resistance Wheatstone bridge. And you would, for both this, you will have to do circuit to Thevenin form, both that. And this is a relatively harder. This is the easy version. And often this is a sub problem and this conversion. Okay, now comes, so we are done with circuits that have resistance. Okay. These are what I refer to as, these are typically zeroth order. Only resistances. Changes are instantaneous. You could also always, is due to then RC or LR. And then we have R, L, and C. Okay. So this is what we have done so far. Only resistances. What we are going to look at now is this. And what this is referred to as typically, instantaneous, right? This is referred to as zeroth order. This is referred to as, zeroth order. That is instantaneous. Okay. Zeroth order circuit. This is what we have done. This is known as first order circuit. And then we have second order. Typically, when you have RLC, you have a second order. For these two things, okay, it can do if you understand. There is something called impedance. This was there in the short playlist that I told. Hey, there is this playlist I gave you a couple of weeks back, and I gave you a couple of weeks back, right? So, if you follow that playlist, whatever you need to know here, that one major trick is this impedance. And with that, you could, okay. Notice whatever we did till here with resistances could do all of that with impedances. So if you understand how to work with impedances, okay, so whatever so far you could do with a zeroth order circuit, that is circuits involving only resistances, you can apply all of that to first and second order circuits. So impedance plays a role of resistances in a zeroth order circuit. Is there a max power transfer theorem? Yes. Can you start analyzing Wheatstone bridge? Yes. Okay. Can you do voltage division, current division? Yes. Okay. Can you do equivalent resistances, equivalent impedances? Yes. Series parallel? Yes. Delta, star delta? Yes. Or we have learned so far, okay, we could actually use the same thing. That is, if you are following till now, okay, and if you understand this one thing called impedances, you could actually solve most of the first order, second order problems. And that is kind of discussed in the playlist that I share. Okay. If I remember correct, this playlist is also available publicly. Okay. If you want to learn this, but I think this one playlist, short playlist kind of available publicly. So I'll put a reminder, but I'll see whatever I had rehash right now, I'll do that and we'll proceed. First, let's look at the first question or concept that shows. Okay. The following circuit, the switch S is open for t less than 0, closed for t greater than or equal to 0. What is the steady state voltage across the capacitor when the switch is closed? Okay. Suddenly now open, closes. What you have initially is this transient circuits, okay? Steady states and transients. Let me tell you the basic theory relevant to this. Solve, write it for an inductor and then for a capacitor. How do I split this? First do for a capacitor. We have okay. In fact, we'll even come to the inductor after finishing this. What is the relationship between voltage and current in a capacitor? Let's wait for even the inductor. How is voltage and current related? If you want even fact, kind of resistance is right. This V is IR. What is the relation for a? What is the equivalent relation? I mean, how is in a capacitor? How is voltage and current related? Voltage and current. How is that related for a capacitor? I is say dV by dt. You can use Q as CV, differentiate both sides, you can arrive at this. dQ by dt is current I, Q is charge, right? Charge in a capacitor is CV. So if you differentiate that, you get this. Current and voltage are related. Again, this is something all of you have seen. I is C dV by dt. Notice this is instantaneous. This is what I refer to as zeroth order. Instantaneous. This is a differential equation. This is transient, time dependent. You have voltage, current as a function of time. There is no time dependency here. Whatever is the voltage, instantaneously, the current is proportional to that, right? But here is VI. This is, I square R. Energy in a capacitor, does anyone know? Energy in a capacitor, half CV square, CV square, CV square. This V could be a function of time. Okay, so energy at any given instant is energy can be a function of time. This is half CV square. And let's also do one more thing. Okay, I have to extend the notes here. But let's kind of extend note, continue it in this page. Now, see, there is something called Laplace transform. You can convert differential equations into algebraic equations, but it's a transform. The way you look at it, transforms, typically you are converting a hard problem into an easy problem. You are moving from an inconvenient coordinate system to a convenient coordinate system. Simply hard to easy problem. So note take Laplace transform here. How are these things later? You will get I of S here. As a Laplace transform of a derivative, C is a constant. You don't have to worry about it. Does anyone know the Laplace transform of derivative? What is dx by dt? What is the Laplace transform of that? Again, I am not asking something like way too difficult. Some of you, one or two of you might know. Yeah, SV, right? So you have SV, C that remains. And typically minus some the initial condition we not, but we'll not worry about it. Okay. It is typically minus initial. Let's not worry about this. Let's not complicate it. This is SVs or SCV. No multiplication of goods. Notice you could also write it over here. V of S is I of S into R. There is a very easy way to go from, there is a very easy way to go from this Laplace transform to one version of Fourier transform. All you have to do is, okay, S equals A omega. And technically notice this is, write it in the same order as we have that equation. We have C and then we have S V of S. What I get is this side is J omega. S is J omega into C. Into V, some function of J omega. Essentially, it's a function of omega. J is a constant. So I'm going to write it as omega. Function of J omega. J is a constant. So I write it as the function of omega. You could also do the same thing here. Notice what I have here is I of omega happens to be. You could write it I of J omega, but that's just a notation. I of J omega, but it's just notation. Typically, we write this as I. It's a function of omega. J is a constant, so you don't explicitly write it. You also need some space. So kind of let me slightly erase this. Let's not give it so much space. Yes, this I substitute. This is J omega. This is this J omega into C to V of omega. If we do the same thing here, I have V of omega as R into I of omega. Just that, see, this will be functions of S. Only if V and I are functions of time by definition in the Laplace transform. Okay. V and I are not functions of time here. So V of S and I of S essentially are constants. V of omega, I of omega are essentially also constants. But the thing is, definition of impedance is this. Notice here, R equals V of omega by I of omega. This is what we refer to as the impedance, ratio of voltage as a function of frequency to current as a function of frequency. What is omega? I'll give you more relatable numbers. Okay, for right now, this is a frequency. Notice this is by definition impedance. It's not. So our resistance for a capacitor and inductor, the name for that is actually impedance. Resistance like thing. Just that we need to account for few other things. Things can be functions of time or functions of frequency. Still, the ratio of voltage to current is impedance. Impedance. See, so now came to our problem. What is impedance of a capacitor? What is V of omega by I of omega here? This. Notice by definition, this is V of omega by I of omega. That happens to be 1 by J omega. Let me also slightly conveniently write it this way. Impedance by definition is V of omega by I of omega. That happens to be. So far, so good. ISC dV by dt, all of you know. Energy in a capacitor is half CV square, all of you know. Basic Laplace transform, and from here to here, okay, basic Laplace transform. And then it so happens in the Laplace transform, if you put S is J omega, you get, frequency dependence. There's no, you can also call that as Fourier transform. And impedance by definition is just the ratio of the function of, V is a function of omega, I is a function of omega, that is, V is a function of frequency, I is a function of frequency. The ratio of the two functions is impedance. Like what? Hey, the ratio of voltage and current in resistor, right? That's an impedance of a resistor, for example. Most of the things that you need, I have made it as simple as possible. If you have, questions, I try to show analogy with the resistance that we know very well. If you have question, raise it, right? If we find space to write, this is time dependent, that is obvious. So I'm going to kind of erase that. This implies something. Capacitor doesn't like something. Can someone spot that? ISC dV by dt. It says capacitor is hesitant to do something. Not just hesitant. Yeah, it is kind of hesitant to do something. Can someone look at that equation? Tell me capacitor doesn't like to do something. Okay. This question is harder. Let me make it slightly easier. This doesn't like sudden change in V. Suddenly changes. dV by dt is infinite. Current is infinite. That is not possible in a realistic circuit. either it's shorting or the wires are melting, something like that happens, circuit gets damaged typically. Capacitor doesn't like, okay, sudden change in voltage. Right? If dV by dt is suddenly changes, it's infinite. I is infinite. Not possible. Just one more thing. Here, resistance is a constant. Doesn't depend on frequency, but this depends on frequency. Notice, in fact, let me write this in even gray. As omega tends to 0, Z tends to infinite. Omega tending to 0, signals are not oscillating. Frequency oscillation, things are not oscillating at all. The name we have for that is at DC, capacitor impedance, capacitor resistance is infinite. Capacitance open circuits. In fact, the most of the things that you want to know for RC circuit about a capacitor, I have it here as far as gate exam is concerned. Notice at DC, again, this is something that we have capacitance open circuits. Recall, okay? IAC dV by dt, all of you know. This says voltage cannot suddenly change. If it does, current is infinite. There is a problem in a physical circuit. Energy is half CV square. Laplace transform or otherwise, you recognize ratio of voltage to current is a function of frequency that happens to be 1 by j omega c. All of us know that. This is referred to as impedance. And looking at the impedance, you can see at DC, that is omega equal to 0, capacitance open circuits. Opens up. There are no current flows. In fact, you can also kind of write this as that is at DC capacitance. We have this common analogy for this. That is, if you put this, right, DC gets blocked, right? And then we have this, just a mnemonic AC current flows. So what is happening is, notice at omega equal to 0, this is DC omega equals 0, Z is infinite. Here Z is 1, 2, 3. This also you can afford to forget. I know this Laplace transform, Fourier transform, fine. But impedance is 1 by j omega c. You know those four things and the consequences of that, you could answer most of the gate questions. Let's look at one. The following circuit. Switch S is open for t less than 0. This is open. And closed for t greater than or equal to 0. What is the steady state voltage across the capacitor when the switch is closed? Concisely, someone tell me how to do this. Please tell me which of the things that I mentioned here we are going to use. This has been open, fine. Now what you do is you close this. Let's say the switch is closed. At steady state, they are saying after a long time. This says after a long, things are not changing. After a long time, how should this capacitor behave? Okay, fine. Even, if you said, there are again slightly too many things to connect here. Some of the box thing, let's say you kind of remember. Okay, I know a couple of things. This is DC source. I know that Z is 1 by j omega c. Okay, at DC capacitor opens. Capacitor opens. Sometimes it takes, it is initially charging. It is certainly after a long time, certainly open. Is what, at DC capacitor opens. That is notice. Here, if you have to see as omega tending to 0, this denominator goes to 0, numerator goes to infinity. We have at DC and opens after long. Resistance become infinite. So what happens to this capacitor? At least now can someone answer? Hope no one has issue understanding what opens means. Right? Resistance become infinite. They are no more connected. After a long time, this capacitor behaves, this point almost opens up. If I have to even draw that, long time, that is steady state, the circuit that you have here is open. This is a circuit that you have. Can you tell me the voltage across this capacitor that happens to be, let's label the points B. The capacitor opens, doesn't allow any current. So I have removed from it. Voltage across a capacitor is essentially voltage across AB in the circuit. Fairly easy to say. Now, this is the resistance problem. This is 10, this is 3, this is 7. Can we tell what is VAB here? Is also, there is closed. If you cooperate, we can, I almost give you, the answer. We are back to a simple resistance circuit. We can answer it. You just need VAB. At least tell me where the issue is. You're not following. I'm confused with this detail. I'm not following this detail. What they're asking me is, let me also know what is the steady state voltage across the capacitor when the switch is closed. So when the switch is closed, the steady state that is after a long time, this is the circuit that we have. Capacitor is not there. It opened up. Its resistance became infinite. Okay, so some of you are doing. So what is the voltage across the capacitor? Essentially, what is VAB? That is what right now they want. Okay? What we want right now is VAB. In fact, let's kind of slightly write it different colors. Voltage across the capacitor is essentially V7. Great. This is 7 volts. How? Notice. Hey, this is open. No current goes here. So I is 0. IR is 0. There is no potential drop across 10 ohm. It's all the same point. IR is 0. Potential drop is 0. For that reason, this point also behaves like A. Why? Current here is 0. I equals 0. There is no current. There is no potential drop. That is essentially 1 point. So after a long time, you have this circuit. Okay. Here, no potential drop, no V drop, no V drop. So this point is same as this point. It should be 3. How is it 3? I is 0. You can apply voltage division. 10 is a fraction of 10. That fraction is 7 by 7 plus 3 into 10. Right? Fraction of 10. No. There is a drop, 3 volt drop across the 3 kilo ohm resistor. 7 volt drop across 7 ohm resistor. Voltage across A to B is same as voltage across A to B. Yeah, that happens to be 7 by 7 plus 3 into 10. There you got your answer. 7 by 7 plus 3. No, the fraction of that. Let me write it here. So the answer 7 volt. That's it. V is IR. Larger the resistor, larger the voltage drop. Right. I is D by R. Larger the resistor, smaller the current. So now larger the other resistance, right? More the current through this one. And voltage and current division, that's why the things change. Okay, there is a simple thing. V is IR, larger the resistance, larger is the voltage drop. So you can easily say, hey, 3 ohm resistor, 3, 0.3 fraction. Here, 0.7 fraction. So let me take a step back and see what we did. Actually, I have space this side or that side unknown that because I was running short of space. Using some of the properties of a capacitor, which property? Essentially, if you know the impedance of a capacitor, you can do this. Impedance of a capacitor 1 by j omega c. It doesn't allow DC at steady state. There can be transients. Capacitor can slowly charge up, but after charging up, it won't allow any current to pass. That is why they say steady state after a long time. Okay. So at DC, capacitor opens up. What happened in the point? The circuit with the capacitor became a circuit with only resistors, which we know this is like home turf. We know how to how to handle that problem. So one simple thing, circuit becomes all of a sudden familiar circuit. Capacitor, resistance capacitor circuit, but the question, one minor detail, hey, is this a resistance circuit? For what they are asking? Many other things in the circuit, but for what they are asking, this is resistor circuit. How to solve. And we made some, this Z is J omega C, this is going to, this is one thing that you really need. It's going to show up again and again. Even if is a capacitor opens or inductor opens, there is a confusion, you can actually quickly deduce that. Hey, what is omega? I'll show it to you. I'll kind of demonstrate or I'll give you simple numbers and illustrative things when we look at AC circuits. Okay, we are still in DC. Now comes the point. I told you how to solve this question, but this year in GATE exam, they may not ask you the same concept, but not voltage across a capacitor at steady state. They can ask you few other things. Towards that, I should also tell you few more things. Erase the given question. I'm going to consider other question. We answered the given question. But what are some related things they can ask? I'm going to answer that. And for that, we need to know what is the voltage is. Voltage is a function of time. We have V capacitor, and then we have voltage capacitor. Interesting. Now this is a function of how should this look? In fact, so we have situation starting from t less than 0, switch is open and all that. T equals 0. After a long time, let's say this goes here. So the switch is open before t equal to 0. There is no current through the capacitor. Current is 0. Nothing is going. It's open. Okay. This is a dangling part of the network. It's not closed. Switch is open less than t equal to 0. So the voltage in the capacitor across the capacitor is 0. And at t equal to 0, you all of a sudden close the switch. You complete the circuit. What should happen? Can someone very in simple English say what should happen? We have this scenario where t less than 0, switch is open. Switch is open. At t equal to 0, we close the switch and keep it that way. What should happen to the voltage across the capacitor? Simple English. Again, this is something that you know. Charging, decharging of a capacitor, you're actually very much used to. And when you're learning something, initially you learn a lot. And after you proceed to something, the amount of things that you learn is smaller and gets smaller and smaller. There is some sort of saturation. And we also, I think, we give some names for it, right? I had a very important special class, the most important topic in GATE biomedical exam. In fact, the most important topic in most GATE exams, okay? Exponential decay saturation. Can someone put this into simple English? How should this voltage across a capacitor change as a function of time in two or three words? Eventually, let's also see what is happening. Eventually, it goes to 7. Eventually, it is at 7. Exponential decay, but as you close the switch, all of a sudden you're applying a voltage. Okay, it saturates at 7, and there is like exponential saturation. Initially, there is a lot of change, then change becomes smaller and smaller and smaller. There's just 1 minus decay, okay? 1 minus exponential decay, saturation. I also want this bit and get it somewhat correct. So there is in shooting, sometimes there are actually two types of shooting. One is called normal shooting. You try to aim, shoot, look at the things and aim, shoot and all that. The other one is your gun is not between your target and your eyesight. You're holding the gun at hip position and you are shooting. Like Keanu Reeves in what is this movie? Latest series of 4 movies, and then there is one more movie coming up. Keanu Reeves, right? There is this ballerina movie coming up based on spin-off from that original thing. Does anyone know this movie that I'm talking about? What was the latest Keanu Reeves movie that was a very big hit? John Wick. Has anyone seen John Wick? Notice John Wick. If you notice the entire movie, they show his expert level by actually a very simple thing. He doesn't put the gun between his eyesight and eyes and the target. He'll keep the gun at position and shoot. Okay. So typically, most people will try to aim and shoot, right? But you could also aim without getting the gun in the line of eyesight. That is known as instinctive shooting. So like that, I have a similar problem. I'm not yet an expert, but I have this Wacom tablet. It is oriented in some way. So if you have to draw a straight line, okay, if I try to look at the tablet and draw, it goes wrong. Okay, I'm trying to get used to directly, looking at the screen and draw, not get this tablet and draw. And also this Wacom tablet position keeps on changing. So I have this simple straight line sometimes that is not so knows. I have some issues drawing. Reasonably looking exponential saturation. Fine, I'm not going to bother. That is not exponential saturation. There you go. And I'm going to cheat a bit to change the saturation value. A value is going like this. I suppose that is far easy. Yeah. Notice you suddenly apply a voltage at t equal to 0. Voltage across a capacitor doesn't suddenly change. Voltage suddenly changes, current becomes infinity. Voltage only gradually changes. So if you look at this point, 1, Vc t minus equals 0. 2, Vc, that is, it's not t minus, sorry, 0 minus. Slightly below 0, voltage is 0. Slightly above 0, voltage is still 0. Why? Cannot suddenly change. No sudden change. V dV by dt is 0 and then current is infinite. The problem that we solved here, this is steady state. After a long time, what happens? Capacitor is fully open. When will that happen? It is totally exhausted. It is totally saturated. It cannot let any more. It cannot hold on to any more charge. It cannot. There is no dq by dt. There is no current. That's it. If the capacitor is eating, it is like rim full. It's like mouth full. Everything is like totally filled, right? Not stomach full. Stomach, esophagus, mouth full. Capacitor cannot eat anymore. There is no space for charge in the capacitor. No current. Nothing can go inside anymore, right? That is steady state. Capacitor is saturated. So the thing is, I was not actually feeling, I was held up with a couple of issues, and I was actually I couldn't think the way I usually do for couple of days. Only after taking the class, okay, for some reason I enjoy it so much that this preferred mode of thinking and thinking actually opens up. It took me actually 2 days. I kind of struggled with the very block, writer's block or a teacher's block. Not a teacher's block, but sort of mental block. Now, as I'm taking this class, it's kind of, I'm getting relaxed. Some of you might be getting tired, but actually, I like the classes that so much that I kind of get relaxed. I get more relaxed as the class proceeds. Okay. What the question that they asked, hey, what is the voltage of the capacitor at D? What else can they ask? They can ask you what is the voltage at 1, what is the voltage at 2, right? What is the voltage at 0 minus, what is the voltage at 0 plus? They can ask you for the voltage. What else can they ask? Come on, quickly. There is a fourth thing that they can ask. So all these are all possible questions they can ask with the same thing. This is essentially VC of infinity. Is all this question. Question 4. Find time constant. Okay. That is, we have space. Actually, that's a very good answer, Yetana. Okay. But before we go to that, hey, why ask voltage at 0, this at 0? Right? Energy of the capacitor at 0 minus energy of the capacitor at 0 plus energy of the capacitor at steady state. They can ask you this. So far, fairly easy. Hey, the capacitor opens up, man. It doesn't have any more room for charge, no current. It saturates. It's a simple resistance problem. We solved it. What is happening all along? It is gradually, exponentially saturating to that steady state value. All these questions we can answer. If you know the voltage, you know half CV square. You can find the energies. You can find the energies. We can find energies. So what is the fifth thing they can ask? Sir, in 4 itself, you put EC0 minus, EC0 plus, EC infinity. They can also ask you one more. Let's say the sixth, suddenly, you'll hold on. That's a surprise, or climax will reveal towards the end. Exponential saturation is a very, very simple curve. There is one constant there, time constant tau. I think Kirtana mentioned. If you know that, voltage as a function of time. That happens to be the saturating voltage 1 minus e power minus t by tau. Notice t tending to infinity. This term goes to 0. E power infinity minus infinity is 0. You have V naught. T equals 0, right? This term is 1. 1 minus 1 is 0. So VC is essentially 0. At this stage, I can notice two things. VC of 0 is V naught into 1 minus 1. That is 0. And here things are continuous, equals. So at this stage, notice, we know the voltage at any time. Not at 0 and steady state. At time 1 second, you know that. Time 5 second, you know that. Give me the time, I will plug into this and find what the voltage is. Give me the time. I can plug that into and find the voltage. Give me the time. Or give me the voltage, I can plug it into that and find you the time. This also happens. It cannot change abruptly. So we have the initial voltage. If you know that, if you know voltage as a function of time, you know energy as a function of time. Substitute the voltage at that time. You know the energy, voltage and energy at any time. Voltage, energy at any. So the last is, sir, but you put this tau. What is the tau? Time constant. Tau is R for the RC circuit. Sir, there is more than one resistance. what do I do at that point? And then see. So for the rest of the circuit, you can find the Thevenin resistance and then Thevenin or the equivalent resistance typically, depending on the problem, but or sometimes it's also or equivalent C. It can be C equivalent also, but do not simplify. It's RC. There are more resistances R Thevenin C. Or even in simple terms, R equivalent. So if you know the time constant, you know this whole function, 2 months of electrical circuits. Okay, done. 8:30 will go till 9, okay? Notice I left a gap for inductor, right? We'll fill up this gap. Perhaps let's read this PYQ and just point B. If this one, which of the 7 couple of simple questions that I mentioned, which of the questions are they asking? Just point that out and we'll wind up. We'll come back tomorrow and then we'll continue with the discussion. And things are functions of time right now. We made one use at DC steady state. Okay, what is it? It opens up. That is the only omega that we used. We have to come back and use 1 by j omega c. But I think by the time we do that, we will also get to second order circuits. You need phasors and impedance as much as possible. I'll try to simplify and solve this. In fact, it so happens that most of the PYQs are actually very, very, very easy if you just understand that impedance. If you know complex number, if you can do complex algebra, you are actually done with this. Complex number algebra, you're actually done with this. Let's recap, and then we go till let's just. And the way I'm going to recap, let's ask quick simple questions. It's okay if you don't answer. I'll just move on to the next student. I'm skipping 2-3 students. I will pause and make it open. Initially, I didn't see some of these names. Arvani. I hope I'm pronouncing your names correct. Okay. You could either correct me now or later on also tell me, sir, you should say my name this way. If perhaps so, Wednesday meetings we should. Hey, sir, my name is this. You are actually not pronouncing it correctly, right? All of that you could. Sharwani, so why doesn't a capacitor like sudden changes in voltage? Why doesn't it like that? Sudden changes in voltage? Simple explanation. Okay. So again, out of some privacy concerns, I'll also try to make it reasonably private. Okay. Jaya, right? Ending with E. So Jaya, sir, Jay will, right? Dr. J, sir, Jay. Jaya ending with E. Darshin, Janvi. Okay, anyone. Why doesn't it like sudden changes in voltage? Short 2-3 word explanation, concise explanation. Anyone? If voltage suddenly changes, what happens? So now some students are like, how can it not suddenly change? I will put a circuit with the DC voltage in the switch. Suddenly change, close the switch. If the capacitor doesn't change voltage suddenly, it will violate Kirchhoff voltage law. Some students are thinking like this, right? I will design a machine that that will violate first law of thermodynamics. I will design a machine that will violate second law of thermodynamics. Perpetual motion machine. I will design a circuit that will violate Kirchhoff voltage law. Things like that doesn't happen. Certainly in our undergraduate linear realm, voltage suddenly changes. Slope is infinite. Current is infinite. dV by dt is infinite. Current is infinite. Okay. So if some of you are trying to use a mic, you could try using chat. Okay. Let's go to the next question. So energy is half C square. Most of you know that. Some Laplace transform, Fourier transform. Okay. The impedances is ratio of voltage and current, which are technically in this case, it's a constant. Technically, this is a constant. Technically, this is a constant. It's not a function of frequency. It's not a function of S. This is B by V of omega by I of omega. Voltage and current both are functions of frequency, right? In a AC circuit, there this ratio is defined as impedance that happens to be 1 by j omega c. Most of you know that. And here you can see that if omega is 0, denominator is 0, this is essentially omega is this. Again, some of your oscillatory circuit, sinusoidals, oscillation frequency is omega. Right? Omega is the frequency of this. This is in radians per second. We'll come to that, but that is omega. If the frequency of oscillation is 0, it is not oscillating at all. It's DC. So eventually it kind of opens, right? With impedances. If there is a mnemonic, DC capacitor doesn't allow, there is a roadblock. AC, this will like go zigzag and pass through the capacitor. For the gate PYQ, it kind of capacitor opened up. Simple resistance circuit. VAB is 7 volts. That is voltage across a capacitor. We looked at the steady state. It remains 0. Doesn't suddenly change, but only gradually change, specifically exponentially saturate to 7 volts. So they can ask you any of these voltages, any of these energies. And if you want to describe this transience, you need the time constant tau. Time constant here is RC. Was RC. The rate at which things are changing depends on this time constant. Okay. Let's head back here. I finished that monologue. How is voltage and current related in an inductor? I is C dV by dt. Inductor is essentially like a solenoid. Current in the solenoid changes, it kind of generates a electric field and associated voltage potential, right? Potential across the terminals. Great. Thank you. So this is fairly simple. Let's write clean. V is L inductance, self-inductance, di by dt. And this says doesn't like sudden changes in time. I write it. Can someone complete it? Sudden changes in Hugo. Got it. So most of you actually knew the answer, but somehow couldn't answer, right? In current, if current suddenly changes, dA by dt is infinite, voltage is infinite. In a physical circuit, infinite potential drop. No, potential is infinite at one place. Something is burning or something is fishy, something in probably the fish is burning, okay, in that case. So doesn't like sudden changes in current. Energy, most of again, energy is a function of time. So, you all of you, any of you is welcome to fill it up before I, complete writing this, okay? My interface is slightly bad. E, N, E, R, G, Y. Technically, this is a function of time. Notice voltage, currents are functions of time. It's a differential equation. This happens to be half. There is also half here. Exactly. I square. The Laplace transform, this is that and all that. We'll kind of shade it out. First is SL. Derivative is with current, right? So SL I of S. If you substitute in S is sigma plus j omega, that is if you don't consider any transients, right? That is if you substitute S is j omega, from Laplace transform you get to Fourier transform. You have, again, let's, gray it out this way, right? I have V of omega is j omega A, j omega L. I have seen it somewhere, right? Some of you are writing Z is j omega L. Yeah, I guessed it. Great. Z is j omega L. Omega is in denominator for a capacitor. Omega is in numerator. There is no denominator, but fairly simple, right? Hey, J, what is that J? Dr. J. You have to, you didn't say what is a J. You said J is a constant. J is this complex number. Technically I have to write it somewhere where I am defining it. J by definition is square root of -1. What if such an entity exists, right? So what if scenario? Like Avengers, what if this exists? Then properties actually are so useful in modeling many physical systems. Medical properties actually so useful to model or describe many physical phenomena that have come across. So that is the J. I also put it up. Let's not confuse it with that initial conditions, or let's put it slightly offset, square root of -1. And then here, what happens? As omega tends to 0, Z tends to 0. Can someone put this in simple English? See, there Z was infinity. This is Z. Omega tends to 0. Your Z tends to 0. Simple English, what does it mean? Impedance. Resistance is 0. It does the opposite of open at DC. Inductor shorts. Technically, I know I should also written one more thing, but at this stage you could go finish this. As omega tending to infinity scenario, perhaps is not what this is not all that interesting. Omega frequency tending to infinity is like, no, this is not a shorts immediately, punctually. That is steady state after a long. It is fairly basic. Okay, let's not kind of warm down. Let's just see what the gate question in the circuit given below. Vs, let's zoom this. Vs is 50 volt. Let the circuit reach steady state for SPDT switch at position 1. Once the circuit is switched to position 2, same thing. Switch was this way, switch is this way. Energy dissipated in the resistors. Can someone describe what happens at position 1, what happens at position 2? Then we'll think about energy dissipated in the resistor. Position 1, it's there for a long time. It is at steady state. Okay, at position 1, when switch is at 1, inductor shorts at steady state. Why? Omega tending to 0, this is a DC circuit. Omega tending to 0, Z tends to 0. It shorts. Great. Hey, the simple resistance circuit. I know the inductor is kind of hidden here, shorted. I can find the current. If I know the current at position 1 in steady state, I know the energy of that inductor. This is, let's make this look like a resistor. Some of you like, there is an ECG signal going on. This is position. Position 2, what happens? LR circuit. Hey, no. Position 2, there is no this and all. That's the inductor. It's a LR circuit. But should we do things as a function of time and all that? No. What they want is energy dissipated in the resistor. And once you find the current, you can write down the answer in one line. Finding the current is one line. Once you find the current, you can actually find the energy dissipated in the resistor, total energy dissipated in the resistor, right? You can write that in one line. How? In fact, we didn't discuss, I didn't put that at all here, but that's fine. There is like 2 words for that. Find it out before we kind of restart this. Okay, I'll recap thing and then we'll solve this. So where we are stopping at is finding the steady state current is fairly easy. Once you know that I, given I, answer is, you can write down the answer. Answer is 1. Like I is 4. 50 by inductor shorted. How is 4? 2. 50 by 25 is 2. So this is I is 2. Okay. I is 2. The initial energy stored in this inductor, okay, notice, current cannot suddenly change. It can only gradually change. All of that is eventually dissipated. That energy is dissipated in the resistor, right? But what is initially stored? What was the initial content of the lunchbox? Eventually get slowly eaten up, right? So initial energy content of the lunchbox or the inductor here is half Li square. That eventually gets eaten up or dissipated by the resistors. You can also write that in. Yeah, you wrote it down. You can calculate that. In fact, we can finish this, but we can redo this tomorrow morning. What is the number that you're getting? Half. Yeah, can we? General is like almost close to this. I have to do that. How much is the inductance here? 0.1 Henry. A Henry, Farad, Henry and Farad. SI units, okay? As far as you stick to Henry, Farad, all your calculations are good, which anyways, when I introduce frequency and all that, I'll make this point again. Perhaps, oh great, we have a empty slide. I'll put this units here, okay? Henry, Farad and all that. So the answer here is 0.5, that is half, into inductor is 0.1 Henry into I square. I square is 2. This is the energy that is what 0 joules and again an energy. This is eventually this. That's the answer. Okay, explain it in more detail. Tomorrow's class, we'll also finish tomorrow's class we'll finish electrical circuits. Okay, you need impedance. This I will also try to. I cannot explain complex number algebra tomorrow. If you can do basic complex algebra, I can actually finish all of this. On the playlist, biomedical signal processing, biomedical filters, short playlist, okay, 5 minute videos. Kind of starts from scratch. How do you add complex numbers, divide complex numbers, multiply complex numbers? How do you do this polar representation, normal representation? Does all of that? How do you find the amplitude? How do you find the phase? Right? And kind of takes you to a reasonable. Whatever you need to handle gate problems, it kind of teaches you that. Okay? That is one. If you have that, we can kind of finish it off tomorrow itself. If you have some prior knowledge on that, even otherwise, I will try to do some just like so. 2 months we kind of condensed in 2 slides, right? 1 or 2 hours. I'll try to do something like that, some justice, okay, in tomorrow's class. I think this is a good time to stop. I'll see you again tomorrow. Okay, have a good one. Take care. The moment I put it this way, most of you started, in fact, notice the capacitor stage, you thought it's like so many things, right? But by the time we came to the inductor stage, we almost you started feeling things easy, right? Kind of like I know this kind of feeling. That is good. And although it is kind of organized, you were filling one side of it yesterday. It looks cluttered right now. There is 2 important on my here. This Z is 1 by j omega c for a capacitor. Impedance. This is essentially the resistance is no more independent of frequency. Resistance is dependent on frequency. Resistance is essentially voltage by current. Here, impedance is essentially voltage by current. Impedance essentially is resistance. Difference being here for a resistor, it acts instantaneously. There is no time dependence. There is no frequency dependence. For a capacitor and an inductor, that is not the case. So for a capacitor, this impedance, the resistance like thing depends on frequency in a complex way. Complex as in there is also this complex number square root of -1. In at the end of the day, it's just V by I, right? So in fact, based on this, we solve this capacitor question. We got to a stage where we can comfortably solve purely resistor-based circuits, resistive circuits. They realized this, they give a RC circuit like this. Many of the questions essentially boils down to a purely resistive circuit. Given circuit as a capacitor, but under steady state condition, initially this, that, and all that, typically it becomes a simple resistor circuit. When the capacitor opens, when the inductor closes, and all that. So we have discussed that. So that is where we stand. And we also know that they could actually ask here, there is a steady state here. Before the switch was closed, there is a steady state here. They could ask things here and there just be, 0 minus and 0 plus. And they asked it after a long time steady state, t tending to infinity. They could technically ask anywhere in between. They can ask you for voltages, they can ask you for energies, right? Any particular time. And once again, tau is RC. RC circuit, tau is RC, right? Once you know that, you can get voltage as a function of time. And once you have that, you can also have energy as a function of time. They can ask any point in this graph. It boils down to here in this question, they asked you this point, the green point. They give an inductor. They give a L over R circuit. Okay. This is referred to as an RC circuit. They give a circuit with an inductor and a resistor. I call this L over R because that happens to be the time constant of this circuit. Again, the text typically suggests they are referring to steady state or initial condition. They are referring to a purely resistive circuit. And then in this case, so is there a switch? Yeah, there is a SVDT switch. So there is an initial steady state current in this inductor. We can easily find it because the inductor shorts. There is this current. So we know the initial energy stored in the inductor. Once you turn that switch, what drives current in the circuit is this initial energy in this inductor that eventually gets dissipated through the resistors. So the energy dissipated in the resistors is essentially the initial energy stored, okay, that you could easily find. The initial current in the inductor, you could find this, right? So this is where we left, and let's continue with this discussion here. At this stage, one thing I want to notice is, so I will solve this problem again. Perhaps I kind of did it too fast. The main reason being like I spent a lot of time with the capacitive circuit. There isn't like a big difference. Once you could understand the resistor capacitive circuit, this last column is fairly easy to fill up, right? I'll do that anyways once again, but the same discussion holds here. He can ask you energy or voltage at any time or current at any time. Even notice. So I mentioned all these things, right? So given voltage, you can find energy, right? Half CV squared is a function of time. You could also do one more thing. You can also find current. How do you find current given voltage? A voltage is this exponential saturating function. And as you know, voltage is a function of things, exponentially saturating curve. How do you find current as a function of time? Hello. Voltage as a function of time. Is there, how is this? How do you find current? You might need some clues. Answer, I suppose, is somewhere in this screen. Let's say, you could technically find it as a function of time. We have V as a function of time, right? Before the switch is closed, after the, before the switches, when the switch is open, when the switch is closed. The entire timeline from -infinity to infinity, roughly we know, right? Voltage. You can technically ask current at any time. Before the switch is closed, current is 0, which is also kind of how we got this voltage to be 0. After the switch closes, how do you find current at any time? Again, let me show you the slide with the answer. Next to write all this formula, right? Another is to actually appreciate what that formula means, right? Students typically make an exhaustive list of all formulas from a book or a reference. That is not useful if you don't know what the formula is. Asked you a question, I am also like trying to get you close to the answer by showing you the answer. It is somewhere in the screen. Where in the screen? You're talking about a capacitor. While we wait for an answer. Okay, let me ask you a question that I already answered. dV by dt. What is dV by dt? See, not. So given voltage as a function of time, you know energy as a function of time. At any time, it's just half CV square. So what is the relation between voltage and current in a capacitor? That is how we started this. ISC dV by dt. If you differentiate the voltage, you get current. And it's that things are functions of time here in a capacitor. That's not so in case of a resistor, right? This is what I meant. Yeah, great. ISC dV by dt. This shows that current depend on the change in time. Because the switch is closed, impedance tends to infinity as DC. So DC is steady state. At point, because switch is closed, impedance tends to infinity. But take derivative of differentiate voltage function, you get current function. Notice you are differentiating with respect to time, right? V is a function of time. When you take derivative, you get a function of time that is current. C is a constant. In fact, let's do that. The discussion doesn't end. I don't tell you that. Brown, green, yellow. Start with this. You can also find the current in the capacitor as a function of time. This happens to be C, D. Take this function, differentiate it with respect to time. Let's do the differentiation. Okay. If you differentiate this function, what do you get? You get a C here. This V naught. Right. Different derivative of that is 1. Then minus into there is also minus t by tau. T is what you're differentiating with. So this 1 by tau into e power minus t by tau. Differentiation derivative of 1 is 1, right? I'm not going to write it down. So this happens to be C V naught minus into minus is a plus by tau e power minus t by tau. Tau is RC. So this essentially is, that's kind of, how much space do we have here? Now I have some time. This happens to be V naught by R e power minus t by tau. What it says is that, right? This happens to be V naught. This value is V naught and that function is VC of t. You take derivative of this function, you get IC of t. C of t. Here it is 0. There is actually, I am only taking the part that is at time greater than 0, but still there is a good mathematical way to deal with that. You have Dirac and Heaviside functions, but without complicating too much. The slope is discontinuous here. So there is a, this function is a slope of this function. This is essentially, find the slope, you get this, right? Because of that, there is a sudden change in the slope. There is this initial value, and then it starts exponential decay. The time constant of this decay, here tau is RC. Here also tau is RC. What is the initial value? Initially, the capacitor behaves as if it lets all current. So this initial value, notice this. When t is 0, this is e power minus 0 is 1. So we have V naught by R. Initially, at the initial point, capacitor actually closes. Eventually in DC, it opens up. This is exponential decay. This is also, let time constant is tau is RC. So the green function is over here. V naught by R e power minus t by tau. And that is your IC of. So yeah, you can find voltage at any time, energy at any time. You can also find current at any time. This is a derivative of this function that I have shown here. There isn't any discontinuity of anything like that. It's just like I try to draw it correctly. It's a simple exponential decay. Why do I call that the most important gate topic, right? Because notice starts showing up. And then I think you should stop at 8, but 9, notice your power is integral of E of t. Power is essentially rate of change of energy. So if you integrate energy, you get, energy is, power is energy per unit time. So given energy, if you integrate it, get power in case you want. Energy is a function of time, energy in the capacitor. If you integrate that, let's say 0 to t, we get power. Power is a function. But, this is kind of like fairly straightforward, but let's not, and just use a definition, but, let's not overemphasize that. But in bioinstrumentation, this can get important. But I will finish this with one important thing. The time constants of energy and voltage are not the same. Time constant here is tau. The time constant here is square of this function. That will be 2 tau. You're squaring it, or instead of calling it 2 tau, this is tau by 2. Okay. Let me also make a note of that here. If V voltage across a capacitor as a time constant of tau, then energy of the capacitor as a time constant of V square e power minus 2t by tau. So this has a time constant of tau by 2. So this is actually going faster. It decays or saturates as a square of voltage, right? It actually does faster. This one detail I think we'll revisit in bioinstrumentation, typically in a defibrillator pacemaker circuit. Sometimes if you're doing energy calculations, this gets important. Defibrillator circuit, essentially, typically this is an RC circuit. You're charging a capacitor, discharging it during defibrillation. Pacemaker, again, typically it's a RC circuit. Your load is typically a resistor, and then there is a capacitor that gets charged and discharged. Okay. So if if you slightly make some changes here, it becomes a bioinstrumentation application. Whatever the 10 points that we discussed applies to that. They can ask you any of this for a defibrillator or a pacemaker. And there the 10th detail gets important. Okay. And we'll look at it when the bioinstrumentation application, actually, when we discuss that, we look at it. But for now, let me just make a mention. Fine. And all the 10 things that we discussed can also be framed for an inductor. Okay. Let's finish this question. So I said, let's do this question once more. Circuits given below, Vs is 50. Once a circuit is switched to position 2, here V is, see, for transient problems, this relation is more useful. For any frequency dependent AC circuits, the impedance is important. Okay. So V is L di by dt. Right? Again, if we have to plot things as a function of time, circuit given below reaches a steady state for SPDT switch at position 1. Look at the current. Okay. I said at steady state, this thing shorts, right? The time point is over here. So you have position 1, then you make that switch, SPDT switch, goes to position 2, you make that change at time t equal to 0. Okay. So what happens is the steady state current in the inductor. This is, what is the value of this current? So let's draw I L of t. Current in the inductor is a function of time. What is the initial at t equal to 0? What is the current here? Let us test it. So the position 1 steady state, notice this is time is starting from somewhere over here, right? It has kind of reached a steady state. What is the value there? Solve that. And this is position 1. This is shortcut. The current is just V by R. The R is 25, V is 2, so I is 2. I happens to be 2. We have to use the same color as this one. I is. At that time, the position switches. What you have here is a circuit without a voltage source, right? That voltage source is removed because the switch moves here. You have essentially a inductor resistor circuit, LR circuit. Quick way to look at it, whatever energy is there in this, initially there is some energy in the inductor, it eventually gets dissipated by the resistors. So initially, say this is like for salaried, people, they get monthly salary. Over the course of the month, expenses kind of eat away all the salary, right? So this initial energy is this current and this inductor. So there is that can drive current here. That can take care of expenses. Eventually, that gets lost, right? So notice what happens to this current as a function of time. It's a LR circuit. It kind of exponentially decays. L over, why do I say this? This is just L over R circuit. The decay happens at tau is L over R. The initial value happens to be 2 amps. I suppose things are an SI. Yeah, ohm and volt, ohm, volt and all that, they give you amp. because inductor resist sudden changes in current. So just before, when you are changing the switch here, position 1, just before turning the switch, right? The current couldn't have been very different. That function is exponential saturation towards this. There is a sudden slope change, but it kind of like exponentially from probably from zero. The inductor initially doesn't allow no current, and eventually kind of saturates towards this. How does that happen? Perhaps this resistance and this resistance are different. So this is position 2 resistance. That would be 50 ohms. Okay. Notice at position 2, you have a 25 and a 25, 25 and a 25, right? Your net R at position 2 happens to be 50 ohms. Okay. And then at position 1, your R1 happens to be just this one resistor, which is 25 ohm. The inductor remains the same. But the point is, these two are happening at different time constants. The time constant here is L over R1. It's actually different time constant. Technically, given current as a function of time, here you could draw voltage as a function of time, derivative of this function. Okay, the derivative you could do it. In fact, I could kind of leave that as an exercise. Find derivative of the function. This is fairly easy. You could draw technically VL as a function of time. Okay, you could do that. So V is L di by dt. But what do they ask? If once the circuit is switched in position 2, the energy dissipated in the resistor. All this energy initially, that is the only energy source in position 2 that needs to be dissipated. So what we have here is this. You have a charge. You have a current in this inductor that happens to be I equals 2 amps. That's initial energy in the capacitor that will be eventually dissipated. Okay. So energy, in fact, we should say technically total energy. Energy is presumed energy dissipated in the resistor, right? At this stage, some of you could wonder, sir, we know current as a function of time, we know voltage as a function of time. So in the resistor, we know current as a function of time, right? Energy, this is like I square R power. You integrate that power, you get the total energy dissipated, right? You could technically take that approach, but that is harder. In fact, this is energy just made a cardinal sense. Let me correct it. Okay. E by dt is T. So you get technically what I should have written as the other way. The ninth point, technically, power by definition is energy per unit time. AE by D. So given energy, you can find the power. That is one thing. And given power, I square R, right, in a resistor, you can integrate that as a power dissipated in a resistor. You can integrate that and get energy. So they want the energy dissipated in the resistors in this position. Initially at T equal to 0, this is what you have. You could do it by two means. You should know both the means, okay? Let me kind of say that. So what is the energy dissipated? This is the question. You can do that with two methods. It's also contrast. Method 1, this is hard method. Technically, I is a function of time. This is an exponentially decaying function. I inductor as a function of time, right? In the circuit, this also happens to be I resistor as a function of time, right? Power in the resistor, power dissipated power in the resistor as a function of time. It's just resistance. There are two resistance, let's say equivalent resistance into I square R of T. I square R. So in fact, notice if this is decaying with a time constant of L by R2, e power minus T by tau 2, right? This power will be square of that. Tau power will be tau current, right? Tau current. They do have very different time constants. Voltage and current have the same time constant, that is tau. But power will have a different time constant. Because of the square, this will be 2. So you technically know power as a function of time. And these are simple functions. Okay, this is essentially this I naught, the initial current, into minus t by tau 2. Okay, and this technically becomes R equivalent I naught square e power minus 2t by tau. Tau 2 is because at position 2 we have a different time constant, right? And then this 2 because we are squaring the current. So this essentially is power as a function of time. Power, you can find energy. Energy in the dissipated energy, total dissipated energy, right? Total energy dissipated in a resistor equals. You can integrate this power functions from 0 to total energy. You have to integrate from 0 to infinity. The area under that exponential curve. This happens to be a curve like this. The total, at any instant, the power as a function of time. If you integrate all of that, this total area, power in the resistor as a function of time, you can get the total energy dissipated. This is method 1. This is hard. What is this? Power as a function of time, and then finding the area under. There is also easy method that we discussed, end of class yesterday. So these are extraneous. Let me erase them. The total energy dissipated in the resistor was initial energy stored in the inductor. Stored in the inductor. Initial energy happens to be half Li square. The initial current. So can we quickly do how much is this? I think you gave an answer yesterday. This is I is to inductance is 0.1, 0.2 joules, right? 0.2. How can we write this? What is this? What is the principle we are applying here? When I say this, the total energy dissipated in the resistor, what is the principle we are applying? This energy equals that energy. I gave a lunchbox analogies, right? Lunchtime, you open the lunchbox. Okay, you and your friends complete that lunchbox. The total amount of food that you and your friends ate is the initial amount of food in the lunchbox. You took some time to eat it. Eventually, the lunchbox got empty, but the initial food in that lunchbox quantity is what everyone eventually ate. Right? For a lunchbox, it's mass conservation. What is this? Not a hard thing. So I am going to wait until we have an answer. Yeah, this principle of energy conservation. Energy conservation. And this method, of course, is homework. You can do this because I did this capacitors. Here, can you do that kind of energy conservation? There is this energy input. One of your friends is continuously buying candies from a nearby store during lunchtime, right? This is this DC source. So when you have that source, you have to account for that. You have to deal with it differently, right? Even if the switch is closed or not, the source is always active. The energy supply is there. You have to deal with that scenario differently. But here, this is a lunchbox scenario. You can, no additional terms. Kind of energy conservation still holds there, but kind of it's much simpler in this scenario. Okay. In position 2, it's much simpler. Great. So the answer is 0.2 joules. Yeah, I already did this. Now we have to move on to AC circuits. So mnemonic L equals lunchbox scenario. So fine. I mean, this probably now this inductor capacitor. See, the reason to actually pull that lunchbox into the picture is to actually give you a mnemonic, but they are asking you for total energy dissipated and all that. Lunchbox can certainly serve as an anchor or a mnemonic. Also, from a perspective of a lunchbox, it's actually fairly straightforward, which is why more relatable, and we could associate with that better. Yeah, if it helps you remember this energy conservation and how it's actually complicated. This is our exponential decay, square of that exponential decay, integration of the square of the exponential decay, right? It takes a lot of time to actually do method 1. Well, if you do this lunchbox thing, yeah, fairly you get the answer in one line. If it helps you, helps as a mnemonic, that's very good. So I have to conclude here. What you really need to know are two things. Having said all this, I'm still sir, too much things. This condensed version is condense the condensed version, right? Genuine concern will also address transient circuit, transient or CMR. Okay. You have a resistor. I have B is IR. This is not transient. This is not this. And then P I square capacitor. All you need to know as far as this transience is concerned, all you need to know is I C dV by dt, and then energy is half C V squared. I have one more thing that I would add. Tau is C. You may have to do a or equivalent or a C equivalent. Now, multiple capacitors, you can do a equivalent capacitor. Multiple resistance, you can do a Thevenin resistance or equivalent, typically equivalent resistance. For an inductor, we have D is L di by dt, J is L I square. Okay, there's a function of time. Function of time. There's a function of time. Okay, there's a function of time. There's energy. There's a function of time. Energy. There's a function of time. So we have voltage as LD VT, energy is half LA square. There's a function of time. 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 And here you have tau is over R. So multiple inductors, multiple resistors, two equivalent here. So rest of it in all of the rest of the things are all essentially consequences of this. Notice, in fact, that is what I wrote down. Then one step down the line, Laplace transform, Fourier transform, do this, and all that. This equations means no sudden change. Then eventually at DC, this thing opens, this thing shorts, and all that. It's all consequences, right? So this is all you need to. Now let's move on to this circuits. Okay. Notice the typical concepts here. What typically happens, switch opens, close. The switch open, closing, it becomes is an resistor circuit. This, you know how to handle. Energy conservation, know how to handle. Now, the transient response, things are functions of time, graph, equation, any particular value. Now, what we have to do was impedance and impedance. Okay. We have to do impedance and impedance. That is what is left. And we'll finish that. Right. Let me just change this file and this is we are 1 hour down the line, 2 hours down the line, have many PYQs. So again, if you know impedance, we can technically do this very fast. But if I have to explain complex numbers and all that, this is going to take time. There is one bit that I want to discuss. There is something called a phasor representation. Okay. So notice here what you had RC and LR circuits. Typically you have a switch, and I said this becomes a resistors, right? You typically have a switch, and there is a steady state that you are displayed. That is one thing we saw. And then time constant tau is RC, or you have tau is L over R. That is something. Then we have the energy conservation. All these three things from a C circuit. You have seen this from a DC circuit perspective. Okay. Now, what you should recognize as, see, when we made this transition, this is familiar ground, familiar, easy, home turf, right? Yeah, you can use many other words. So perhaps it might have been a hard problem, moderate problem, but the moment it's a resistor circuit, it's very familiar and easy. You should acknowledge us in case of AC circuits. We have RC or L or circuit. You know what this reduces to? This again reduces back to a resistor circuit. There is something in this arrow that makes it a resistor circuit. Does anyone know what that arrow is? And the point being that simple change, you are into familiar, easy home turf area. You are into your own, playground, your backyard. You know how to play there. One word fills this arrow. Consider that as a plan. 1 year takes you from a RC or a LR circuit. In fact, I would go C circuit, LR circuit, CLR, RLC circuit. Even second order RLC circuit becomes a resistor circuit. One word. And what I mean here is most of the things that you could do in a resistor circuit, voltage division, current division, KVL, KCL, right? Bridge balance, bridge imbalance, finite bridge, infinite bridge. Most of the things that you discussed in a resistor circuit can be done. And this conversion As even you can put one letter there. You don't even need one word. Can someone guess what that word is? That one letter is Z. If you look at the impedance of any of these elements, you can treat it as resistor. Whatever calculation you did with a resistor, you could do that calculation with an impedance. Only difference being impedance is a complex number. You have to do complex algebra, not normal algebra that you did with a resistor. There is an imaginary part and then there is a real part. There is a magnitude and then there is a phase. So the magic word is impedance. So let me start with the condensed version of that. Okay. You have a resistor, you have a capacitor, inductor will go. You have an inductor. What you need to know here is V is IR. You need to know here is V, complex numbers, I'm going to write it this way, I times C. What is C? V is this complex number. Notice, essentially, again, if I have to be slightly notice, V is IZ. V, now this is a function of frequency. Frequency of the AC source matters. Frequency of this source matters. This impedance, again, is a function of frequency. The Z happens to be, what is this? The impedance of a capacitor? Ratio of voltage to current, 1 by J omega. Now you can start filling up this side. Voltage is I times C. This is of omega A. This is of omega. This is of omega. This. And then you have Z of omega equals J omega. Yeah. What is this J? J is square root of -1. Of course, this is a function of omega. The point is, whatever, most of the things you could do here, V is IR, you can actually do here. What all the basic resistor questions that we did, concepts that we did, are applicable here. But now our task is to understand a couple of things. First, let's stick to this. Let's make sure we get the units correct, okay? SI units. As far as you stick to SI, you don't have to worry about any of that. You have voltage, current, energy, power, right? And then you have capacitance. Then you have omega. This goes by the name angular frequency. Angular frequency. Then you have frequency. Then you have time, okay. Time. Then you have time period. You have T, C, R. Yeah, this is a time, I suppose. You don't have to write that. Perhaps you need to know time constant. Tau, okay. Tau, or in fact, tau, T is there. Here, this is time constant. This is time period. This, of course, is resistance. This is inductance, self-inductance. There is a mutual inductance. How two solenoids interact, that's a mutual inductance. This is self-inductance. There is no mutual capacitance, at least in the linearized version, so we have a capacitance. These are the variables. Then we have the SI units, right? We have SI units. H, volt, amp. What is the energy units for energy and power? SI units for energy and we have joule. We have watt. How is volt, amp, and joule related? Simple. Use, this is VI, right? You can use it. This is actually volt amp. Okay. Energy is essentially is volt, just voltage into current. Energy is notice power is rate of change of energy, dE by dt, energy per unit time. So essentially, you could also write this as joule per second. So there you got watt, volt amp, and then joule second, all connected, right? Volt amp is 1 volt amp is 1 joule per second, that is 1 watt. Let's finish the easy ones, okay? Time period, seconds, resistance is, this symbol ohm, right? And then L is 3, this is farad. Hey, what is this farad and all that? How does it relate to one of the things? You can use a known relation. Energy is half CV square. You kind of know how that is. Farad, how things are related. Tau is RC. Notice, right? You know many things, right? So, tau is RC says, notice, this corresponds to ohm farad. Ohm farad is essentially time. How do I get that? This also corresponds to Henry by tau is RC and tau is L over R. Okay. So these are SI. As far as you stick to them, you are going to get one of the other units. If there is any prescript, that is, if there is a micro or milli, that just gets transferred. Okay, there is a millivolt. Do some calculation, you end up with a milliwatt. But volt gets to a watt. So from SI, you move on to another SI. What is left as this frequency? Time period is also this. What is left as omega f and t. The units for omega is radians second. Yeah, this is, let's say this is the radians per second. Okay. Frequency happens to be number of oscillations per second. Essentially, this is hertz. 1 hertz by definition is per second. You could say oscillation, number of oscillations per second, or you could say number of revolutions, number of beats per second. We have seen many examples of this, right? Number of revolutions per second. 1 by j omega c, it's an impedance at the end of the day. You're getting a ohm resistor like term. So where is this? It's not 1 by RC, right? 1 by j omega has radians per second. Capacitance is, question is 1 by j omega c. Does it correspond to 1 by second? No. Like 1 by RC, then it's 1 by second, but no. And in fact, see, I already told you, if you know complex number, if you know this impedance is essentially any circuit is a resistance circuit, you can solve all of the gate questions. But another huge real trouble here is with the units. Okay, and units, they typically set a trap. No, 1 by j omega c is not 1 over second. Okay, this is incorrect. 1 by RC will be, 1 over second. RC is second, right? I put that here. Notice this is essentially RC. This is L over R. That corresponds to actually second. Okay, this won't be 1 over. You get a clear answer? This essentially has units of ohm resistor. Here, notice things are oscillating as when you're looking at things as a function of time, they're oscillating. What is the time period here? Fairly easy. This is time period. So let's kind of highlight that part. What I have here is one oscillation. One oscillation, essentially one revolution, that is essentially 2 pi. Okay. This is one full circle. You get back where you started. So this corresponds to 2 pi radians. One full circle. One oscillation is one full circle. That's all I say. One full. Omega says how many radians per second. You have speed as distance by time, right? You have omega is essentially speed. The distance it travels is pi radians. Okay, one revolution, 2 pi radians in a time period. This is the relationship between omega and t. I just used distance by time, nothing more there. Perhaps I can emphasize that. All I'm using is notice speed equals distance by time. Angular frequency or angular speed. Okay, you could call this or speed. You could omega, the distance it travels is one revolution, that is 2 pi. One complete circle. The distance it travels, 2 pi, one full rotation, that is 360 degrees or 2 pi radians. How long does it take to do that? One time period. This is one important relation. This is one relation. 1 over t is related to one of the other variables here. Can someone spot it? 1 over t, this time period, actually related to if length of one heartbeat is just how many heartbeats per second, there is, it goes by a number. So can someone spot that? 1 over t is related to one of the variables here in the stream. Just that list, forget energy power, you have omega f tau, t, even forget resistance. Definition 1 over t is frequency. Great. This is again by definition. There is a definition of frequency, number of oscillations per second. And if you use that, you could also write this as 2 pi. That's a somewhat of an important relation there. I kind of omega by 2 pi is 1 by t. That is correct. That is essentially frequency, right? Omega is 2 pi f. Yeah, great. All of you are giving the correct. Okay. And because, okay, general, someone asked, right? Hey, does 1 by j omega, 1 by j omega c, does it have units of 1 by, second? No. I said no, but I learned something here. So time constant is RC. This is L over R. I always say, they are asking you for a frequency. You don't know which frequency. There are three frequencies. Okay? There are three magic. They are asking for some frequency. Last 15 minutes of the exam. Instead of randomly guessing a numerical answer type version, you can actually do some calculation and may enter a more sensible answer. Or if they are asking you for frequency. Okay. And I'm going to refer to that as magic frequency for an RC circuit. That magic, they are asking you for some frequency, lower corner, upper corner, bandwidth. What is the frequency at which, some frequency. Okay. I don't have time to solve the problem, or I don't know how to solve the problem. In that worst case scenario, let me be very clear. Okay. This is worst case scenario. For the last 15 minutes, I don't know how to solve, but I want to give a sensible answer. Worst case guesstimate. Okay. For an RC circuit, that frequency, F, for an RC circuit happens to be 1 by 2 pi C. 1 by 2 pi RC. Let's see if someone can complete this. For a L over R circuit, that is LR circuit. Can someone say what? L over, I like to call it L over R, but you can, LR circuit. What is this magic frequencies? Can someone guess from what you have seen so far? That is, they have given you a circuit, AC circuit, the inductor and resistance. They are asking you for a frequency. A typical best guess is this magic guess that often gets you the right answer. And you can kind of stare at this equation and tell me what it should be. This is in hertz. This will be in hertz. Let me write it down. 1 by 2 pi L over R. If we have to isolate the time constants there, actually the time constants are there. L over R and O. So 1 by 10. Okay. This happens to 1 by 2 pi tau. This happens to be 1 by 2 pi tau. This is a relation between parameters in the transient circuit and parameters in the DC circuit and AC circuit. This, the transient circuit is a time constant. In the AC circuit, it's going to be the frequencies. Okay. But here you could actually, so this suggests, in fact, Janil asked a question, right? Note, omega will be 1 by 2 pi F is omega. That happens to be 1 by RC. Omega again is 1 by, right? This 2 pi F happens to be 1 by RC. 2 pi F is omega, so that's what I'm making. F 1 by RC. That tells you omega is 1 by tau. That is, if there is a relation between given time constant, you know the angular frequency. And angular frequency is different from frequency. One has units of radians per second, another has units of hertz. This is a very, very, very typical trap. Let me complete notice. Angular frequency is radians per second. This is hertz. This is the biggest, most common trap in the gate exam. They give you a frequency based on the units. You have to decide whether they are referring to angular frequency and frequency. Right? Even if you are trying to calculate something like time period, notice. Given frequency in hertz, time period calculation is 1 by that. Given frequency in radians per second, time period calculation is 2 pi by omega. You can easily enter an incorrect answer. So be careful about it. And I just now showed that there is also a relation between that omega and tau. Okay. And okay, this trap here has to do with the units. Okay. Omega happens to be 1 by tau. I just, if you know tau, you can calculate the angular frequency of a circuit, RC circuit, LR circuit. And there is a final magic frequency. This is for a RLC circuit. Does anyone know what this magic frequency is at least? RLC circuit, they are asking you for a frequency. You don't have time. What is your best guess? I'll show you, examples from this is all formula units and all that, right? Quickly start showing you examples. Gate exam, 1 by 2 pi. Can someone complete this? Complete third magic frequency. This is for a second order circuit. For a second order circuit, they are asking you for a frequency. That is, you are looking at a circuit with a resistor, capacitor, and an inductor. All three are there. They are suddenly asking you for what frequency. Worst case scenario, my guess is case scenario. But we'll also start looking at some best case scenarios. Okay, the time delay between peaks of the voltage signal V1 of t to cos 6t. Technically, there is this is conventionally this notation is used, but there is a problem here. I'll tell you what the problem is. But there are many problems with this particular gate question. One is the answer key is incorrect answer key. Official answer. They make a lot of mistakes actually. Okay. I thought they were trying to set a trap. No, they have made a mistake. I'll show you what that mistake is. One, and this is notation. This is actually poor notation. This is in degrees. Typically, this is in radians. One part is in radians, one part is in degree. We're adding them. You need this is in radians typically. This is in notice degrees. So you're adding the two. It's conventionally used. Understanding is that here the phases I am representing by degrees. It essentially by 60 degrees I can convert that to radians, right? If I am plotting a function, I am doing that conversion and do this addition. Okay. There is some, this is typically inconsistent notation, but we'll have to live with it. Consistent notation. Okay. Unfortunately, this is convention. Inconsistent conventional notation. Top of this, they set a trap. And here they fell it. They fell into their own trap. So inconsistent conventional notation. So there are many things stopping you from getting a marks in this part of circuits question. Okay. One of them being units. But my suggestion is, as far as you stick to SI, you are doing good. Understand what basic omega is, basic Fs, basic time period is. You can derive all of this. You don't have to memorize them. Okay. All I did is just do speed, distance by time, and one definition, that is 1 by TSF, right? You can pretty much get all of that. So trust in SI unit to deal with, know what the SI units are, hold on to them. Okay. That will help you deal with the SI unit problem. 10 minutes, you don't know. They're asking you for some frequency. You don't know what that frequency is. The best case is this. Best case, worst case, best guess. You don't know the answer, but you want to guess. You want to guess, sensibly guess. That is the worst case, best guess scenario. The three numbers that I have given you. Any frequency they are asking. Based on the circuit, plug in one of these three numbers. Sorry. That is the suggestion. Okay. Now I'm going to answer this question. Time delay between 2 cos 60 plus 60 degrees and minus 360. You can answer this in two ways by knowing some convention. But, for now, I am going to actually plot these functions to make sure you see what is what and all that. Okay. I'm going to plot and answer these questions. Can someone type these two things in the chat window so that I have access to that? 2 cos 60 plus 60 degree. Can someone type that? Can someone else type minus 3 sin 60? We'll find the time delay by plotting, and then we'll come back here and see what the answer is. And while that happens, can someone also hey, pi is approximately 3.14. How much is this? How much is this? How much is this? How much is this? 300 pi by 360. Can we get all those numbers? Okay, thanks. So one curve is minus 3 sin 60. Someone else just type in this 2 cos 60 plus 60 degree, because I'm going to get out of this file. I still want access to those details. And can you also have this numbers? Type in 300 pi by 360 equals this. 10 pi by 360 equals this. 50 pi by 360 equals this. 200 pi by 360 equals this. Okay, thanks. So 2 cos 60 plus 60 degree. Now, most of you are picking 300 pi by 360. Some of you just go down the line because, redundant work. Just fill in these four numbers so that we can verify what we're saying. And at this stage, so this is in radians. Supposed to be whatever you put inside that box should supposed to be in radians. So notice you can read the omega to be 6 radians per second. So when you multiply that time, you get this number is radians. This number is degree. Let's also calculate that. I'll put 60 degrees happens to be how many radians? That calculation I can do. 60 divided by 360 into 2 pi. I suppose this is 1.3 0.046 radians. Can someone also type this? Okay, 60 degrees. This. Let me at least write down all the numbers. Type that. 60 equals degrees equals 1.046 radians. 300 into 3.14 divided by 360 happens to be 2.616. Okay. Answer supposed to be in seconds. Okay. So this is in seconds. 10 into 3.14 divided by 360 is 0.8, 0.872, approximately 0.87. Okay. Then we have t into 3.14 divided by 360. This is 0.436. Then you have 200 into 3.14 divided by 360. That is 1.744 seconds. Seconds. Okay, some of you are answering answer D, answer K, but this is incorrect. This is the correct answer. I can also tell you that right answer. We can verify that. Professors are also humans. I think gate committee is also humans. Perhaps there is a committee, they could have avoided it, but does happen. But the real problem is, they don't acknowledge or accept that they have made a mistake. Okay, even in objective scenarios like this, they accept to, they stick with their mistakes. I don't know where that is, how scientific or how rational that is. Hey, I have typed in. Can someone just type this? 60 degrees is 1.046. This is this because I'm going to shift this, right? I need this reference. 300 pi by 360 equals this. Can someone just have that in the chat? None of you want to do that? Okay, thanks. 60 degrees is that. Oh, Kirtana kind of typed all of it. Thank you. So I think she saved all of our types. Okay, so let me just open a browser. Okay, let's plot and see. Hey, technically we can answer that question in 30 seconds, but notice the committee has made a mistake, right? You can get the correct answer in 30 seconds using some simple convention, but given that the committee has made a mistake, okay, this is like often not understood correctly. The numbers and terms here are not often understood correctly, which is why at least if you are seeing some number in the question, what is that number, right? I want you to make better sense out of it. And most of the place where the students really gain or lose marks is subtle differences between what is angular frequency, time period, and all. That's where most of the marks is lost. Conceptually, things are not hard. They don't test you very hard conceptual things. Impedance, you are good. Okay. For that reason, I'm going to spend time while discussing PYQs. I'm going to spend time plotting all this. Let's go to keep. Okay, great. Let's see this. Cos x. Cos x is this. Compared to this, how should cos 6x behave? Frequency smaller, that is more oscillations or lesser oscillations? Simple question. X is this. What would cos 6x more oscillations? Six more oscillations per second. This is 1 radians per second. This is 6 radians per second. The blue curve oscillates 6 times more compared to this. Let's even count that. Where here is one full wave. How many oscillations are there? 1, 2, 3, 4, 5. If you're kind of careful, I think you'll get 4, 5, 6 complete oscillations. Yeah, if you're careful, you get 6 complete oscillations. And to make things easy, let's also make this step size in terms of pi. The cos curve, if you look at it, in 2 pi seconds, this axis in seconds. Whatever you're putting in is second. 1 second. Make it actually more convenient. Let's make it t. Then let me do t. Let's make it cos of an angle. Let's make sure we agree with the units of x, okay? Because many of the differences we are going to read it from here. This is fine. Yeah. Is there a way for me to add text? X axis is in time. What we are looking at is a function that oscillates as a function of time. If you look at cos x, when time equals 2 pi, okay, it finishes one full cycle. That is, the time period is 2 pi. for cos x. One full cycle from 1 to 1, the amount of time it takes, the time period for repetition is 2 pi seconds. You can calculate it. So in 2 pi, essentially 2 into 3.14, it will be 6.28 seconds. Okay. This time period is. If you were to look at cos 6x, 6 is in radians per second, x is in second. So both of them multiplying each other, you get, now the input here is of course it's an angle that goes into cos. It oscillates 6 times faster. If you look at from 0 to 2 pi where there was one full wave, the red wave, there is one full wave. Now we have till here 1, 2, 3, 4, 5, 6. 6 full waves. So the frequency of this is one red curve is 1 oscillation per second. Frequency of this is 6 oscillation per second. Or the oscillation, this oscillates 6 times more. Okay. Time period of the red curve is 2 pi. Time period of the blue curve, can we quickly tell that? It's 2 pi by 6. That is essentially pi by 3. Agree? It is 6 times, oscillates 6 times faster. So the length of one full wave is 2 pi by 6. That is pi by 3. You also, let me write down all of this. So, yeah. Cos x time period is pi seconds. Cos 6x time period is 2 pi by 6. It's 6 times faster. This is pi by 3. Cos 6x is 6 times faster compared to cos x. It's relatively 6 times faster. 6 times faster. Let me ask one more question and then I'll move. Okay. Frequency of cos x is dash hertz. Can someone just complete the dash so that we can move on to the way to say this? Time period I put, can you just calculate frequency? That is, 2 pi is essentially approximately 6.8 seconds. Can someone calculate the frequency of cos x? Time period, frequency, right? Fairly simple. Why is there a value like rate? General says 0.159. That's what I also had. This is 0.15. 0.1. That's great. So most of you, 0.159, 0.15, 0.16, fairly good. Most of you can see that, right? So you understand this. Right now, notice. You understand this angular frequency of cos 6x is 6 rad per second. So when your x is time, you put in there, you get a radian, you get a degree, and then function. Get this. For simple calculations, time period, frequency, angular frequency calculations, I suppose you all could do. And at this stage, I have shown you all the relations, right? I'm going to presume you can move back and forth from one to the other. Great. Let me turn off this red curve. Let's get to this blue curve. 4 oscillations per second, right? It's oscillating faster. Frequency is higher. That we can fairly see. This is oscillating for where it's doing 1 oscillation. This is doing 6 oscillations at the place of 1 oscillation. Let's look at that. Okay. So question here, if we put add a phase. In fact, let's kind of compare this. 6x plus a. Let's also kind of, at the stage zoom in. Let's see what that phase is doing. Compared to the blue curve, let's, initially set the phase at 0. Phase is also in radians. So you're adding radians and radians, right? When you say cos 6x plus a is a, phase a is in radians. Okay. So when you add a phase, when there is no phase, both the curve lie on top of each other. When the phase is positive, how should this blue curve move? If A is positive, should it move to the left or right? In fact, let's see that, okay? Phase is positive. This curve is moving to the left. It's appearing faster compared to the blue curve. At t equal to 0, the blue curve has a peak. Green curve has a peak slightly before that. It has a head start. This number is positive, it has a head start. This curve is moving to the left. If it is negative, it is slowed down. It is moving to the right. But when the phase is, one complete frequency, it's a complete circle, you are going to get back at this. After some time, say minus 6.3, We made that calculation, right? 6.28. After one time period, phase corresponding to 2 pi, right? Or like one complete, phase difference is 2 pi, it's a full circle. Cos theta plus 360. You got back where you started. Notice minus 6.3, right, is 2 pi. One complete delay is one complete oscillation. So phase is moving it left and right, and how it moves, this negative and positive phase that we have seen. Right. Now, the two curves in the question, we have cos 60 plus 60. So at this stage, notice changing the amplitude is not going to change the phase. I can change the amplitude, but the relation between the phase difference between time delay between the two curves remains the same. So I'm not going to bother about the amplitudes given in the question. Okay. I'm only going to consider this. But if there is a sign change, I'll have to account for that. Okay. So one of the curves given in the question is cos 2 cos 60 cos versus 6x plus 60. 6x. And I suppose 60, we calculated that to be 1.06. Okay. And the amplitude doesn't matter. For that reason, I am taking off the 2. The sign will not. Again, things are cluttered. Let's turn this off. Let's turn this off. This is one of the curves given in the question. 2 times that, I'm not going to follow. Other curve is sine 6. Yes. Notice sine 6x and minus the sign really matters. That is minus sine 6x out of phase by 180 degrees. Okay? They are out of phase. This is essentially this is 6x, so they are out of phase by 180 by 6. That is pi by 6. Okay. So this curve is given. This curve is given. The sign matters. The amplitude doesn't matter, but the sign matters. So I have the curve with this sign. So these are the red curve and the green curve are given in the question. Do you all agree? So what is the time difference between the two curves? There itself, the peaks are here. We can see, the positive peaks are at the top, the negative peaks are at the bottom. Let's say they are referring to positive peaks. The question is a time delay between the green and red peak. There is a different time delay between the red and green peak. This is different. This is different. Is there anything in the question that says minimum time delay, maximum time delay, any of that? No. But let's find the time delay between these two. What this x is 0.872. Okay. Minus this, how much is it? Pi by 4. Can someone differentiate these two and tell me? The time where this peak reaches is 0.8728. The time where this reaches the peak is pi by 4. Can you calculate the delay? 0.87. This is pi by. Amplitude is 1. Peak happens. If you just multiply it, okay, the peak, this axis will remain the same. If it just any of you like questioning that, I can also show that quickly. Can you find the difference between 0.8728 and pi by 4? Reaches a peak at this time, this reaches a peak at pi by 4. What is the difference between them? Any of you are wondering, sir, what is given is 2 cos, right? Just to show that if the peaks happen at the same location, I'm going to go thus 6 plus 1.046. Okay, just to show that the peaks are at the same location. The amplitude doesn't matter. Peak is occurring at 0.87, the peak 1, okay, 0.87. Okay. This peak 2 is occurring at 0.87. The peak location doesn't change. Okay. 0.87 roughly, that's where the peaks are happening. So did anyone calculate the difference? Again, let me leave the number. The peak here happens at 0.872. This peak here happens at 0, pi by 4. A difference between the delta t here. Why is there a confusion, or why is there a surprising amount of delay? Show you, sir, in a gate exam, how do you plot Desmos and all that? How do you find the peak? Some of you are wondering about that. Hold on to that. I will show you how to find this in a gate exam. But here, is there anything wrong with the connection? Extremely good. Is the question not clear for any reason? Find the time delay between the two peaks. I'm showing you where the first peak is happening, where the second peak is happening. What is the time delay between? How long? What is the time difference between the two peaks? Internet is on. Numbers not visible. Is that the case here? I don't know. In fact, I'm surprised. One number is pi by 4. Other number is actually slightly above pi by 4. Pi is at 3.14. 0.8728 is like slightly above pi by 4. In fact, if you're wondering Pi by 4 happens to be 3.14 divided by 4 happens to be 0.785. I'm asking the difference between 0.785 and 0.872864. Okay, roughly 0.09, 0.08. We made some calculations earlier. Do you see which of the options this actually corresponds to? Thanks actually Ayush for, generally responding after a long time. Which of the numbers in the question it actually matches to? 10 pi by 360, right? It's there in the chat. 10 pi by 360 happens to be 0.08. They said is a correct answer, and I just showed you by plotting things. And here itself, I pointed out one issue, that is time delay between peaks. There are actually two different time delays between this. There is a small time delay, and there is a large time delay. And if you consider positive and negative peaks, there is a time delay between this red peak and green peak in between, and all that. There are other time delays, right? If the question is ambiguous, but okay, let's give some credit to them. They are referring to the positive peaks. Answer is 0.087. That happens to be 10 pi by 360. What they have given, I will also show that. What I have plotted here is cos 6x plus 1.046 and sin 3x. This is sin 6x, the blue curve. Okay. Notice sin 6x and minus 6x, the peaks are happening at very different, positive peaks are happening at very different locations. Okay. So this is a very different curve. I take sin 6x, but if you scale it, the peak remains at the same location. Okay, if you multiply by 3, it remains at the same location. This is cos 6x. Now let's look at the difference between the peaks. Now again, there are two differences. There is this large difference, then there is a small difference. Let's actually find the small difference. We'll highlight the two numbers. The first peak is happening at 1.037. Okay, that is 5 pi by 12, I suppose. The second, okay, roughly approximately this. Okay. Okay. I got the exact number. Yeah, this is that 0.87 we initially had it. This peak. Oh, I got 1.037, the 5 pi by 12. Yeah, these are two numbers. What is the difference, time difference between these two? 5 pi by 12. You can convert the, find the seconds. This second, what is the difference to that? And in fact, check which of the options. Many of you made that calculation, so I'm going to, let's finish it in 30 seconds or something. This is 0.4355436. That is option C. That is the official answer. They are not asking for the time delay between cos 6x and sin 6x. They are asking for a time delay between cos 6x and minus sin 6x. That happens to be this. Notice if I scale it, okay, this location is not going to change. 0.786 is not going to change if you multiply it by 3. Some of you have said, there is that 3 factor of 3, where is it going? Because where the peak happens, that doesn't change it. Notice if I multiply by 3, that peak happens at the same point. 0.78, right? We have seen this. Pi by 4. Okay, the peak location doesn't change by multiplying by scaling by a positive number. But if you change the sign, the peak location changes. This is still at pi by 4. Okay. But the reason to spend so much time is not really to say, hey, there is a gate mistake. One is the correct answer is different. And I wanted to show that point number 1. But the real thing is most of the marks are lost or gained in the simple things that I mentioned. Difference between angular frequency and frequency, time period. Simple calculations is where most of the marks is lost. Do you see, can you make all this simple calculations right now? That is my only question. And if you have any question with the time difference that I showed, raise it, okay? I'll also go back and show how to do that in a gate exam. 30 seconds without Desmos, how to do that, I'll show you. In 30 second, 1 minute calculation you can do. But this requires some prior knowledge. Let me also share this graph so that we have a copy of that. Someone put this in the WhatsApp group so that I can later make use of it. So the correct answer is B. Answer K is this. That happens to be actually technically, and I'm presuming this is positive peaks, min delay between positive peaks, because there is also another solution there. Min delay between positive peaks. The question should have been clear. It is not. And their answer essentially is min delay between positive peaks of cos 60 plus 60 degree, and mine, it's not minus, it's plus 3 sine 60. Okay, they have made two simple mistakes. Question is not clear, answer is incorrect, but the real blunder is they didn't accept any challenges. Okay, not fair. I hope someone challenge. I asked students to challenge it. Perhaps no one challenged, so they didn't really make a blunder, but it's a mistake. Okay, how would you do this in the GATE exam? Add your playlist. It is publicly available. I gave it to you a few weeks back, asking you to hey, watch this one playlist. It's extremely useful, both for impedance, phasor thinking. There is something called phase, where you don't really worry about what this frequency is. Okay, that is all these oscillations and all that you're not bothered. All these oscillations you start looking at in a circle. Okay, this is things are going round and round in a circle, and your phases are different locations in the circle. Then you have also draw the circle slightly smaller. The cos corresponds to x-axis of the circle. Okay, this is your two. This corresponds to cos axis. Theta is a circle, right? Goes on and on oscillating. So this corresponds to cos axis. Okay, the angles are measured positively this way in the circle. Theta, positive theta is thus convention. Note as, so this is cos theta. Where is sin theta here? Cos theta minus 90. If we take cos theta minus 90 happens to be sin theta. That is, if you backtrack from cos, you end up with sin. This happens to be sin theta. Sin theta is at this point in the circle. Cos theta is in that point in the circle. This is known as a phasor representation. Phasor. So now what is given as 2 cos 60 plus 60 degree. Let's plot that one. Okay. This is, so what I have here is cos theta. This arrow corresponds to 2 cos 60 plus 60 degree. So this angle is 60 degree. And someone tell me, where is this arrow? Minus 3 sine 60. Forget even, the 3. Where is minus sine 60? 6 really is immaterial. Okay? In a phasor representation, let's say the 6 is immaterial. Can someone tell me where that? So minus sine is at 180 degree phase difference from sine, right? Great. Okay. I mean, negative x-axis, actually, Madhurima, we're very, very close. That is opposite of sine theta. I suppose you wanted to say x-axis, cos theta has taken it. Negative y-axis, sin theta has taken it. Notice this. I think you're correct. Yeah, you meant to say that. Actually, it's the y-axis. Negative y-axis, sin theta took it, right? We already saw this. Notice in the notation, you can easily write down trigonometric relations. Hey, sin theta, you add 90, you get cos theta, right? All of those reactions you can easily get. Yeah. I kind of got what you are saying. So this is where minus sine 60, the time delay between them. So the yellow is rotating, oscillating the circle. The rose is oscillating the circle. Okay. The delay between them is, this is the time delay. Time taken for yellow to traverse. This is the time taken for yellow to traverse. This is the delay. Required time delay. Okay. Is time taken. Traverse or move. Traverse. What is that angle? 30 degrees. Traverse 30 degrees. How much time it has? Notice. 60 degrees corresponds to t. This says time taken for, so to traverse 360 degrees, it takes one time period. To traverse 30 degrees, it's a fraction of one time period. What fraction? Just someone plug in the time period here and tell me which of the options it is. So given omega is 6 radians per second, okay, we're getting omega is 6 radians per second. What is the time period? And you can just plug that over there and tell me the final answer. So this implies your time period is, you all said this formula, right? And this is how much? Pi by 6. And just plug that in over there. So that corresponds to a fraction of the time period, that is 30 by 360. And the time period happens to be 2 pi by 6. So which of the four options, if you plug in t as 2 pi by 6, what do you get? If you want me to simplify this English, make it more clear, 360 degrees take t, 60 degrees take t seconds, therefore 30 degrees take the fraction of, small part, take fraction of t, that fraction is 360. Just plug in T, you should get one of those 4 options. Yeah, 30 by 60 is 0.83. You had to calculate it, but okay, let me also complete that step. Therefore, 30 degrees take 30, this fraction of T, that is 30 by 360 into 2 pi by 6. That is 3 into 2, 6 cancel. You have 10 pi by 360. And that happens to be 10 into 3.14 divided by 360. This is approximately 0.087 we saw in that decimal speed. The answer key is this. That is actually referring to this. Answer key is referring to this time delay. That is not. And when I discuss solutions for this, I kind of say, I'm not sure they're referring to positive and positive peaks, negative peaks. And I thought they were trying to be smart and set a trap and all that. No, they have made a mistake. Hey, are you getting B? Any of you? Sir, what is this? Cos theta is here, sin theta is here. Then plot, it's just the time taken to traverse the circle. Require time delay is time taken to traverse. You have doubts on what this convention is, face the convention that you have to, some prior knowledge you have to. I try to introduce it, x-axis is cos theta, negative y-axis is sin theta. See, you get the trigonometric relations. Time delays correspond to calculating this, time taken to traverse all these angles. It's hard to be more concise and also more correct. Most of them are fairly straightforward. All you have to do is stick to SI units. You're good. Yeah, because sine and minus sine have 180-degree phase difference. Sine is negative y-axis, minus sine is positive y. Good question. Convention is x-axis is, let me also explicitly write that. Phasor convention. What color do we use? Blue is not used. Phasor convention. Your cos theta is x-axis. Your sin theta, this is minus y. Sir, y minus y-axis in the convention? Because that's when we can get correct trigonometric identities. Point number 1. Notice cos, that is cos theta minus 90 is sin theta. It's not cos theta plus 90. Plus 90 is not sin theta. Plus 90 will be minus sin theta. Okay. This convention will get you correct trigonometric relations. And there is, of course, one more thing in that convention. And you have counterclockwise theta is positive. That is the convention, Phasor convention. So in this convention, minus sin theta is on the y-axis. Fair question. Okay. Now, how much time? 4:12, right? I have. Let's go till 4:30. I have stick to conventions. Okay. Know what the standard units are. Many of these details doesn't matter. You should be able to calculate omega f tau t. Understand the difference between omega and f. One is in radians per second, another one is hertz. Understand the difference. How to calculate going one from the other. I showed you what these numbers are. We did some calculation just now, right? Omega is 6 radians per second. What is the time period? 2 pi by 6. Right? Did that. Omega is 2 pi by 6. T is 2 pi by omega. What is that? Essentially, it's speed is distance by time relation. So you can calculate one given the other. In fact, you can also calculate time constant, right? You can do all this. I showed an example, and then so if you stick to SI, you are also good with all this, right? Ohm, Henry, Farad. You don't have to worry about units. That is one thing that I tried to tell you. So stick to SI. That or just be aware of what omega f tau t is, and then typically traps are set there. There is the Phasor convention. Let's summarize that. We should technically warm down. I kind of know the discussion was kind of like intense, right? One question, I also had some digressions on magic frequency and all that. One question, but it's a problematic question, and all the things that you need to know are there. So discussion was intense. We are supposed to warm down, but let me see if we can hit a home run soon after we warm down. Okay, so stick to SI units. Point number 1. You are good. All confusions with the this ohm, Farad, Henry, Joule, watt, all of that. You should be safe from all of those. Stick to SI. But if there is a milli or a micro, keep that milli or a micro in the calculation. Your need should be, the set should be easily traversable. Omega f t easily traversable. Be that is given one of this, you should find the rest of that should be easily traversable. One, you should find the others. That is another thing that we learned is there is a phasor convention. Okay, and this digression magic frequency. Magic frequency is the worst case scenario, best guess solution to this min-max problem, right? They get exam. So magic frequency. The point of all that is impedance is impedance. I didn't get time to explain this, but I mentioned impedance is resistance for AC circuits. So whatever you treat it as a resistance circuit, whatever you could do with impedance. If you know complex algebra, impedance is resistance for AC circuits. This is what you kind of need to know for first order, second order, any frequency dependent analysis. What I have mentioned here, if you know that, you're good. What I spent time on is I tabulated all the SI units. We made what is this omega of t tau. We are able to do that on that. I did this. So tomorrow I'll try to find examples from the tomorrow next class. Impedance is the resistance of AC circuit. In fact, if you know that, you can answer most of the other gate questions. And then magic frequency, let's see if there is a need for a worst case guess. If we need to guess, but typically we can answer. Okay, that will do. But let's look at these questions. This is, I think there is an ambiguous question. There is a mistake in the question. I'm not going to solve that. I'll give you some pointers. So from the frequency response side, what we really need is there is resonance power factor and all that. But notice that's not complicated. I'll just tell you what is what. Perhaps the solutions are already available, right? You could come prepared before the next class, but notice circuit shown below. It's observed that the amplitude of voltage across a resistor is same as the amplitude of the voltage source. So voltage across, amplitude here is essentially the amplitude here. Okay. In simple English, the impedances of that happens when impedances of these two cancel each other. 1 by j omega c happens to be j omega L. When that happens, this amplitude voltage will be this amplitude voltage for this circuit. You can easily find it. Notice, and 1 by j omega c equals j omega L will tell you actually omega square is 1 by square root of LC. You got the magic frequency. Even if you did not know anything, if you a LCR circuit, magic frequency is 1 by 2 pi square root of LC, you can get that answer correct. This is frequency in frequency in hertz. Question is asking you frequency in radians per second. Okay, so that will be 1 by square root of LC. If you get that, you could answer this question. I told you the two answers. What the question, the condition stated in the question means the impedance are the same. You could answer. Fine. First guess scenario, what can I guess? Magic frequency, guess the magic frequency, you can get the correct answer. Okay. Let's look at this question. Let's put it in. For the circuit given below, choose an angular frequency omega naught at which the voltage across the capacitor has maximum amplitude. If there is a resistor, there is a capacitor and all that. What do you know? You know voltage division. You know impedance of a capacitor. Apply voltage division. Answer is 2 lines down the line. It's 2 steps down the line. 2 steps away from it. Is just question in voltage division. Let me traverse further. A series RLC circuit 220 volt 50 hertz supply for a fixed value of R. Inductor is varied to a maximum current. This value is this. Corresponding potential drop across a capacitor is. Inductor is varied to deliver maximum current. The maximum current happens when the resistance is the least. The impedances of capacitance and inductance cancel each other. When will that happen? The magic frequency. Omega square is 1 by square root of LC. You have one piece of information. And then to find that omega, you have another capacitance or that, you have another piece of information. Capacitor is, potential drop across a capacitor is this. To use the impedance, you can do this. So it's a combination of magic frequency and voltage division using impedance. Let's go here. Series RLC circuit consumes power. Value of L is changed such that circuit consumes same power but operates with a lagging power factor. So here you need to know what is power factor, but at the end of the day, there is a simple sign change in impedance. Plus 10J is becoming minus 10J. So the difference is 20. That is what they are stating here. Initially, it is some XJ. It becoming minus XJ. What is the difference? 2XJ. Okay. It boils down to the simple impedance calculation. So the power factor and all that, that is what it boils down to. You can answer this question. And notice power factor is a favorite topic of that, we'll have to deal with it on its own. Again, there is a kilovolt amp and AC supply. It's a lagging power factor, right? This is some theory. There is a 5-10 minute video that I have put up and that explains this concept of power factor. If you watch that, that suffices to answer this. Okay. And that brings us to some miscellaneous questions, some BJT MOSFET approximations or models. We have dependent current source. The current here is 100 IB is this, right? The KVL, KCL, you should actually solve this. There are some miscellaneous questions. So by now, we are actually done with circuits. We'll come back, we'll spend one more class and we'll finish. Okay. So most of the questions in electrical circuits, you can answer with this. Impedance is resistance for AC circuits. Stick to SI units. You don't have to, there is no headache of units. You should be able to convert a given F, find omega, given omega, find T, given tau, find omega, make that simple calculations. And typically traps are set in the units of that. Omega is in radians per second, other one is hertz. Phasor convention that I explained today. This is all the convention. Cos theta is x-axis, sin theta is minus y-axis. Why? All trigonometric relations holds good. You can calculate the time taken to traverse given angles. That is the Phasor convention. And then magic frequency, worst case, best case scenario. RC circuit this, LR circuit this, RLC circuit this. I already showed you an example. Notice what they are using for is 1 by square root of LC. Okay. Perhaps we all need a break. So let's take that break. It would really help if you watch the impedance playlist, biomedical signal processing or biomedical filters playlist. Short videos. It would really help if you come prepared. It will also help if you watch that 5-10 minute video on power factor. I also put up that. So if you come prepared, we can just, there is no more theory here, okay? Whatever I wanted to tell you, we couldn't solve a lot of problems, but whatever I wanted to tell you, I told you. The theory is here, okay? We'll quickly solve all the gate examples and we'll wind up with circuits, okay? So 2 actionable items, ball is in your code, 2 actionable items, short playlist, given a couple of weeks back, 1 video, 5-10 minute video, then we are finished with circuits. Okay. Beyond this, we are already getting 80% of circuits questions. So beyond that, doesn't really make sense. Okay. So this is a good place to stop, and we'll finish the circuits next class. Okay. Part 1, 2, 3 is already available. What I'm going to do now is this part 4. We did the steady state of this. The steady state, this capacitor opens up, and then we found the voltage across the capacitor. Did we solve this problem in this class? I suppose yes. RC circuit we did. Okay, I have done that. In the recorded videos, what are the typical modifications and questions? What else can they ask? I have addressed that issue. Yeah, okay. Did we do this inductor problem? So what are the question as? So they are changing this SPDT switch. Essentially, there is this position 1 when there is a circuit with the voltage source. Position 2, there is a circuit without the voltage source, right? Once the circuit is in position 1, the circuit is in steady state. Then they change the switch. The energy dissipated in position 2 is. Did we do this problem? So position 1 circuit is essentially you have a voltage source with, 1 resistance. What happens in even position 1 is concerning steady state, right? So this inductor is essentially shorted. Okay, the inductor is shorted, and then there is just a voltage resistor circuit. You can find the current in it. The steady state current of position 1, right? That is the initial current in the inductor can be obtained. That happens to be 2. This is a simple circuit, right? Voltage is 15, this resistance is 25, current will be 50 by 25, that is 2. What they are asking is, now we change the switch to position 2. It's a LR circuit. There are 2 resistances, 25, 25 and an inductor, right? And then what is the energy dissipated in the resistors? Total energy dissipated in the resistors. You could do this by 2 means, okay? Find current as a function of time. The initial current in the inductor. Then it will be exponentially decay. You can find that current as a function of time. And then find, based on the current, the power, right? You can integrate the power to find the energy. This is going to be slightly harder. But there is a very simple way to do it, okay? The idea is,
the total energy dissipated in the resistors should be equal to the initial energy stored in the inductor. The analogy I gave, which many students liked, is the initial energy stored in the inductor, right, due to a current of 2 amps, that corresponds to the, your full tiffin box that you take to college for lunch, right? That full tiffin box eventually get distributed to your friends and yourself, right? Couple of resistors, right? So the initial content of the tiffin box eventually get distributed to you and your friends. You and your friends are like resistors. The initial content of the tiffin box is like this inductor. So total amount of food consumed by you and your friends together from this tiffin box is the initial content of the tiffin box. So instead of finding, how much you eat as a function of time, hey, what is the initial content, total amount of food available, or the total initial energy available? If you know the current in an inductor, you can find that, right? I is 2, energy of that inductor is half Li square, right? Even L is given, and half Li square, you can easily find the initial energy in that inductor to be 0.2 joules. Eventually, all of that energy get dissipated in the resistors. So energy dissipated in the resistors is also 0.2 joules. Fine. So the second method is fairly easy. Total energy dissipated equals initial energy stored in the tiffin box is essentially a statement on mass conservation. This is a statement on energy conservation. Okay. And of course, I have discussed few other things in the recorded video. You could take a look at. So the bare minimal things you need to know here is, V is IR, okay, this power is I square R. For a capacitor, I is C dV by dt, we discussed this. Energy is half CV square. Voltage is LdA by dt, and then energy is half La square. If you look at first order transients, exponential decay, if you know the time constant, you pretty much know everything about the curve. We have a very separate video on this, right? The most important topic for gate exam or gate biomedical exam. So you know the time constant, that is RC. Here the time constant is L over R. So if you know the initial current, you know how it decays as a function of time. You can find the current at any point in time. Again, if you know the current in any point in time, actually you can calculate the energy in the inductor at any other point in time, right? The initial energy is one thing, half Li square. You could also do that calculation for any other time. So all this discussion I have already put up in the recorded video. Do you have questions on this solution? 0.2 joules. So this is 1 by 2 into 0.1 into 2 square. Okay. Inductance is 0.1 Henry. Okay. Now we are going to look at, so this is a time response, time dependent response, right? Things are functions of time. Now in today's class, we are going to look at frequency response. Things are functions of frequency. Again, I asked you to come prepared with the recorded video, but I'll give you a quick overview. Okay, here if you know this much, it suffices, right? That's what I said. Here, if you know this much, this is the most important thing that you need to know. Okay, for a capacitor and inductor, the ratio of voltage and current, these are functions of frequency. That ratio is known as resistance in case of a resistor. V by I is R, right? Here V by I, we call that as impedance. Impedance of a capacitor is 1 by J omega C. Impedance of an inductor, right, that is ratio of voltage to current, is J omega L, where J is this complex number square root of -1. This is that one thing you really need to know to proceed further. And if I remember, okay, I have given you the list of parameters involved here and all the parameters and the definitions, SI units and all that. Okay, you can go over this. Yeah, what I am actually go do today is, if you know how to solve resistance circuits with resistors, if you know complex arithmetic, if you can add and subtract complex numbers, if you can multiply and divide complex numbers, you can do all of those analysis even for AC circuits. Point number 1. Okay, I'll try to show examples through PYQs. All the SI units are discussed here, listed here. Okay, stick to SI units, you will actually avoid a lot of headaches. The bare minimal parameters that you should be very clear on: angular frequency, time period, time constant. Okay, given one, you should be easily able to find the other. All the relations are again given here. Okay, time period by definition is inverse of frequency. 1 by time period is frequency. Okay, and angular frequency is the time it takes to traverse 2 pi radians. That is one full cycle that happens in one time period. So this is angular speed essentially. If you take the angular distance divided by the time taken, you get the angular speed. So 2 pi by t is a relation, is essentially gives you angular frequency. And I just mentioned by definition 1 over t is frequency, so you also have it as 2 pi f that is mentioned over here. And quickly you will realize last 15 minutes, 30 minutes, you have solved most of the questions that you know. Okay, I have listed 3 things here as magic frequencies. This is when you don't know, they are asking you for some frequency and you don't know the answer, or you don't know how to solve that exam. Okay, you don't know how to solve that, some scenario like that, last 15-30 minutes, and you have time and you are trying to get a couple of more marks. Okay, one reasonable guess in that worst case scenario is like, if it's an RC circuit, calculate this as the frequency. Of course, this is in hertz. If it's an LR circuit, calculate this as the frequency. If it's an RLC circuit, calculate this as the frequency. I'll show you examples today based on PYQs. Okay. Notice what we have here is essentially 1 by 2 pi time constant RC. This is also 1 by 2 pi time constant L over R. This happens to be 1 by 2 pi square root of it. Okay. And because we know that 2 pi f is essentially omega, we can also see that omega happens to be 1 over tau. We also can see one more relation over here. Again, I have written that relation in this question. So in fact, I'll start with this question. Okay, today I'll show you examples of very, very simple use of Phasor convention and your applications of Phasor. Some PYQs using magic frequency that I mentioned. And then I am going to treat most of the PYQs, right, as a resistance circuit, because I know how to do calculations with impedance. I'll show many examples. Okay, that is we are discussing electrical circuits, PYQs from BM paper, and this is actually part 4 of the 4-part series. This is going to be the last video series. Okay, so I want to see again, the core idea behind the series is that approximately 80% of questions from roughly 20% of concepts in the whole syllabus. Our idea is to know this 20% of the concepts in and out. We have done most of those concepts. So what has left us? The couple of things. Okay, Phasor example, or I'll actually show you Phasor example. Very, very simple thing. Okay, I kind of in part 3 have explained this elaborately, but basic Phasor example I will show you. So AC circuits, with you can start doing the calculations that you already know. You know how to handle resistor circuits, right? You can treat it as resistor-like circuits. You can start applying voltage division, current division, typical things that you need to do. You can do series, parallel, all of those things. So you can treat it as a simple resistor-like circuits. AC circuits can have capacitors and inductors and resistors. But even given capacitor and inductors, you can treat it like resistor-like circuits. You can apply most of these principles if you use this thing called impedance. I'll show you a couple of examples of this. And you need to know complex arithmetic here. Okay, you need to know complex number multiplication division at a bare minimum. Okay, complex arithmetic. This is a must in order to do that. Again, actually, I have shared a playlist, biomedical signal processing, or analog filters playlist, where I also explain this from scratch and show you simple examples on how to do this. If you already don't know this complex arithmetic, I have also explained that in a very short playlist. Okay, this is one thing. And then the worst case scenario, they are asking you for some frequency, you don't know how to answer that. The best guesses in that case is what I refer to as magic frequencies. I'll show you a couple of examples from PYQs. Okay, that's the objective for today. Let's get started. Okay, so this question I have kind of elaborately explained. I have also kind of reasonably explained the Phasor convention, but what they are asking for us, I'll put this in simple English so that you can fill the answer and we can quickly move on. Okay, also I noticed the answer key, official answer key is incorrect, right? So, but I think the correct answer is different. Okay, I'll in fact show let's find out the answer and then I'll explain that. Let's say we have the idea boils down to cosines and sinusoids are oscillating things, right? So you can actually look at circular motion and start describing cosines and sines. Okay, let's say a particle is traversing this in the counterclockwise direction. Okay, let's look at the x component and the y component. Okay, this x component, if this is a complex plane, notice this will be your real axis and this will be your imaginary axis in the complex plane. Okay, notice if the current location of a vector or a complex number is over here, okay, if this is at an angle theta, okay, you have the x component to be cos theta. If you make this unit circle, okay, for simplicity, the x component will be cos theta, okay, and the y component will be sin theta. What we mean by that is when the arrow is along here, it's, the x component is a maximum. Then as the arrow traverses a circle, it kind of keeps on decreasing. The length of the x component decreases, becomes 0. So if you were to plot the component as a function of time, what you would be getting is, notice, essentially cos omega t. Initially, the x component is maximum. Okay, as it traverses, x component keeps on decreasing. Okay, notice as if here it decreases, as it goes here, it further decreases, right? It kind of becomes to 0. When the arrow is at this point, and then as it goes further, the x component becomes negative and reaches a maximum over here, and then the component reaches a maximum, becomes -1 and then becomes 0 again, and then as it gets back to the starting position, it completes a full cycle, and what we have here is essentially cos theta. Notice what we have here is cos omega t. The omega tells you how fast this arrow is rotating. So again, if you look at this component, if you look at the vertical component, you will be getting a sine curve. Okay, but to solve this question, what you need to know is the Phasor convention. What they are asking for us, what is the time delay between peaks of the voltage signal V1 and V2? So we have 2 cos 60 plus 60 degrees, and then V2 is -3 sin 60 degrees. I'm going to use Phasor convention, and what we have here is essentially x-axis or the real direction cos theta, and negative y-axis. Okay, it's not y-axis, it's negative y-axis. Okay, that is sin theta. So in this convention, this direction is chosen to be cos theta. So with respect to the note that typically angles are measured this way, your positive angle is measured counterclockwise. Okay, that arrow direction is important, how you measure that angle. And if you measure it counterclockwise, okay, notice if you take sin theta, if you add 90 degrees to it, you get cos theta. And of course, if you take sin theta, if you add 180 degrees to it, it's the other way around, you are in the negative sin theta. You can start getting simple trigonometric identities in the simple Phasor convention. Actual Phasor convention actually boils down to representing this cos omega t as just a complex number. But let's just look at where is cos theta, where is sin theta for now. So the given two vectors, one is 2 cos 60 plus 60 degree. Omega doesn't matter in Phasor convention. All you're looking at is where the arrow is with respect to the other arrows. Okay, so 2 cos 60 is over here. That is vector 1. Notice this is cos theta along x-axis plus 60 degrees, right? This angle is 60 degrees. That's the first vector. You have v1 of, okay, and then the second vector happens to be v2 of t is -3 sin 60. That is this vector. This is v2 of t, where I have drawn it opposite to sin theta direction, minus sin theta direction, 180 degree opposite. And the answer that we are asking for us, this is the time taken for this vector to traverse this angle is the time delay between the two peaks. Okay, what is the time delay between the peaks of the voltage signal? The peak of this happens here, the peak of this happens here. So the time taken for this rose vector to traverse this angle is the time delay. Okay, in simple words, 1 at What is the time period here? Notice omega happens to be 6. I am getting this from here, right? Notice we are only comparing signals with the same omega. We cannot compare signals with different omega on a phasor. This is notice this is omega is 6 rads per second. Okay, the time period will be 2 pi by omega. That corresponds to how many seconds? So notice. So I am moving from omega to time period calculation, right? Okay. Some of you are saying the final answer, but okay, fine. This right now happens to be 2 pi by 6. So by definition, to traverse 360 degrees, it takes 2 pi by 6 seconds. So to traverse this angle, notice this angle is essentially total is this 90 degree and this is 60 degrees. So this angle is 60 degree. To traverse 30 degrees, it takes a fraction of the time period. Okay, it's going to be a fraction of the time period. So time period, a small fraction of it. What fraction? It's going to be 30 by 360 seconds. And this happens to be, time period is 2 pi by 6, that is pi by 3. And this fraction is, take that pi by 3, multiply that by 30 by 360. I suppose this is 10 pi by 360. And that is our answer. Okay. And notice the gate key is this, that is incorrect. I have plotted all the signals and I have showed it. Okay, this is gate key, official gate key, but that is incorrect. So this is, notice at the end of the day, so this is the phasor convention. Instead of looking at signals as a function of time, you are looking at how things are moving in a, doing the circular motion, and you are essentially comparing one arrow, relative motion of one arrow with respect to other arrows. Okay. Okay. Now, so AC circuits, if you know this impedance, we can do this resistor-like circuits, right? And then I also said magic frequency. Let's look at the next PYQ. The energy stored in the inductor is 6 joules. So we have a simple AC source inductor circuit. Energy stored is this much. The value of maximum power delivered in the inductor is. See, the energy stored in the inductor at which instance is not clearly mentioned, okay? That makes it very ambiguous. And this is somewhat poorly framed. So I'm going to skip this. Let's not add fuel to the confusion. Let's skip this and move on to this question. Okay, what we seem to have is a RLC circuit, right? Let's zoom this. You can also zoom this slightly further. In the circuit shown below, it is observed that the amplitude of the voltage across a resistor is the same as the amplitude of the source voltage. The amplitude across the resistor is the same as the amplitude across the source voltage. What is the angular frequency? Omega naught in radians. Notice it's actually a second order circuit. You have a resistor, you have an inductor, you have a capacitor. But this is fairly easy to answer. Okay. Imagine if there were 3 resistors here. Finding the voltage across the resistor is fairly easy. You could apply voltage division. What seems to be complicating this is the presence of this inductor and capacitor, which is where the statement I made on impedance matters. Any AC circuit essentially becomes like a resistor-like circuit if you use impedance. I'll show this, and I also mentioned 3 magic frequencies, right? I think here we can, let's see if the magic frequency works here. Okay, let me write down a couple of things. The bare minimal thing that you need to know for you have a resistor. Let's look at the element here. You have a resistor and you have a capacitor, you have an inductor, and we have this ratio of voltage over I. Some of them perhaps technically can be a function of frequency. Sometimes that function is a constant, as in the case of resistor. So notice here we have, let's call this ZR, let's call this ZC, let's call this ZL. Okay, this we know as the resistance R. Okay, this we know as 1 by j omega L, which is very important. So I'm going to write this as 1 by j omega C, and this is j omega L. Okay, and if omega is in radians per second, you're technically fine. Notice, without complicating this a lot, omega is in rads per second. That is one thing, the bare minimal thing that you need to know. Second is I mentioned 3 magic frequencies. Right? Let's do again, there is an RC circuit. There is an LR circuit. I refer to that as L over R circuit. And then sometimes there are RLC circuit, series parallel. Okay. And the magic frequencies, let's write this in frequency in hertz. Okay. So frequency in hertz, this is, you have 1 by 2 pi time constant RC. Here you have 1 by 2 pi time constant, that is L by R. This R goes to the numerator. And here you have 1 by 2 pi square root of LC. And just in case, there are a few other things. If frequency in case of in rad per second, often mistakes are done with this confusion between hertz and radians per second. Even traps are set there. So let me be explicit here. Okay. This is 1 by RC. Okay. This is R by L. This is 1 by square root of TLC. Just to remind you, notice this omega happens to be 1 over tau, where tau is a time constant in seconds. Again, notice for a RC circuit, this is RC. L over R circuit, this is L over R. And time constant, there are many time constants here. No, let's not fill this. So the first thing is, I'll show you how to solve that using impedance. I'll also show you how to solve that using magic frequency, or rather, let's use a magic frequency and guess if it works. Let's see if that actually we're also getting the right answer. So this is a RLC circuit. They are asking for angular frequency when the voltage across the resistor is same as the voltage across the source. At which frequency that happens, we actually technically don't know. Let's pretend, okay? Let's say method 1. Last 15 minutes of the exam, you're trying to grab a couple of more marks. And let's pretend you don't know how to solve this, okay? Let's see if we can magically guess the correct frequency. Magically guess correct frequency. And you want the frequency in radians per second. This is an RLC circuit, okay? So you have an RLC circuit. Okay. Let us guess. Is omega not? Okay, we are only guessing. Okay, but let's find that number. In radians per second, this is 1 by square root of LC. If you stick to SI units, you are safe. Okay, Henry is in SI, Farad is in SI, Ohm is in SI. Just make sure you retain all the milli, micro, kilo and things like that. So the actual calculation that you have to do here is 1 by square root of 10 millihenry. So that is 10 into 10 power minus 3 into capacitance. That is 1 microfarad. That is 1 into 10 power minus 6. This is in SI. This is in SI. Your answer should be in SI. That is in radians per second. Can you calculate this and tell me what this is? And we don't know, we are just guessing. We are pretending we don't know how to solve and we are guessing, okay? We'll solve this and see if it actually works out. We'll do that in the method too. But can we find out what this number is? I suppose we have a square root of 1 by 10 power minus 8. So 1 by 10 power minus 4. I suppose we are getting 10 power 10,000. Okay. So right now I'm just guessing that. Okay. That's not the final answer. And the point of this being, just in case you don't know it, okay, there are many places where the magic frequency is useful, not just for this. Let me again point that one out. RC circuits, LR circuit, RLC circuits. This shows up in many other places. In bioinstrumentation, sometimes models for PZT, good model for PZT is a RC circuit. Good model for a cell membrane is a RC circuit. Okay, and then you have low pass filters, high pass filters in signal processing, right? Even circuits involving op amps, analog circuits, active filters. Okay, there are many other places where this resistor and capacitor element shows up, perhaps along with some other element. Okay, like an op amp. It turns out many a times this magic frequency, this lower corner frequency, upper corner frequency, right, actually does work in many of those problems, not just in RC electrical circuits and LR electrical circuits. So they are asking for your frequency. The best guess would be this, just in case you don't know. If you know, you can solve it. Okay, I'm not stopping you, but just in case you don't know, try this. Okay, so this is an example. So for example, the given PYQ is an RLC circuit. We guessed this. Okay, answer was in radians per second, so we did 1 by square root of LC. And let's now actually solve this, which is where I'm going to highlight this. And in fact, notice this is part 4 of 4, right? In part 3 of 3, I also made a statement, stick to SI. You are safe. I stick to SI to be safe. I'm also doing some explicit calculations on that. Okay, let's do this. If you use impedance, how does this becomes like a resistor? Recall, okay, we have impedance of capacitor 1 by j omega c. This is j omega L, right? Let's go. Now, what we have here is ZR, ZL, ZC. Okay, voltage across a resistor. It's a fraction of the total voltage drop here. That is the 100. Voltage division. Let's see if we can apply voltage division with this resistor-like circuits. Okay, so I'm going to use voltage division. And what I say is voltage across a resistor is a fraction of voltage across, no, the input voltage is a fraction of the input voltage. This fraction happens to be ZR by the total impedance, ZR plus ZL plus ZC. The three, this is almost like resistors, they are in series. The three impedances add up. One is ZL, this is ZC. Okay, but the difference is this is a complex number, this is a complex number, this is a complex number. Let's also explicitly write that. Okay, now notice your VR by VI equals ZR is R, ZR is R, and ZL is J omega L, ZC is 1 by J omega C. What we are saying is the amplitude, notice these are all complex numbers, they have an amplitude and a phase. Okay, there is a real part and there is an imaginary part. So what is mentioned is the amplitude of this are the same. So these two voltages are the same amplitude. So what it essentially says is this equals 1. Okay, let's also color code it so that this equals the ratio of the amplitude is 1. This is the same as the amplitude. That's why I'm getting that. At this stage, okay, we need to know some basic complex algebra. Notice this happens to be, if you know multiply and divide by j in the numerator and denominator, you get minus j by omega c, because j square is minus 1. Okay, you get this. And some of you are also wondering some basic things, right? Some very basic complex numbers I will do. Okay, if z is this complex number a plus j b, okay, you can write this in a slightly different form. This is amplitude angle form. Okay, this if you take a look at a circle, take components, you can easily get it. Okay, let me also say that over here. Just notice your given complex number is over here. Now this is the complex plane. So this is the real part, this is the imaginary part, and the complex number that you have here is a plus jb. The real part is a, okay, real part is a, okay, the imaginary part is b, and the length happens to be r. How do you find the r? R happens to be square root of a square plus b square. This is your amplitude, and the phase is this theta. How do you find theta? That is also fairly simple. Theta happens to be tan inverse of b by a. So given a and b, you can find r, and given theta, given r and theta also, you can find this. So you can take components, this given r and theta, I will also write those relations. Notice given a and b, you can find r, given a and b, find you can theta. The other way around, notice a is just r cos theta, b is r sin theta. So given r and theta, you can find a. That is something. Sometimes we also write it as in a different form. This is actually in Euler's form, polar form. This is e power j theta. Notice the phasor convention, the shortcut for r into e power j theta is actually, the shortcut is this. Write the amplitude and write that angle or the phase over here. Angle next to it. Okay. So, and we have the one important element, the conjugate. This is often z bar or z star. This is essentially the a minus jb. Okay, the conjugate is here. The angle phase is negative. Okay, x component is the same. Y component, the imaginary part is negative, minus b. Okay, often that conjugate is useful. And so notice we got the amplitude here, we got the phase here, and then we also got the conjugate here. So this amplitude happens to be equal to amplitude of numerator by amplitude of denominator. Amplitude of numerator is this. Amplitude of denominator is a square plus b square. R square plus, notice this is j omega L minus j by omega c. So the amplitude of that will be omega L minus 1 by omega c whole square. Okay. What I have done is to use this relation. Notice I said 1 by j omega c is minus j by omega c. I made that substitution and then took the amplitude. It's square root of a square plus b square. Now the question is, what we have is a real number. We are only looking at amplitude. When is this equal to 1? Can you stare at this and tell me at what frequency this becomes? The numerator and denominator cancel each other. Yeah, one is to say that resonance frequency. Another one is to say that, notice, if this term is 0, when this term goes to 0, numerator and denominator cancel each other. So that happens when your omega L equals 1 by omega c. And this implies the omega of interest, right? Omega naught square is 1 by LC. And this happens to be 1 by square root of LC. And stick to SI, you're going to get an answer in radians per second. If you calculate this, what should you get? Yeah, what you get is 10 power 4. See, notice, there was a reason we guess magic frequency, right? That happens to be the resonant frequency here. That happens to be the frequency at which the impedance is minimum. Current flow is maximum. Total impedance is ZR plus ZL plus ZC. When is that a minimum, right? Again, that minimum happens when omega L equals 1 by omega C, right? So notice, here we kind of smartly guessed. Try to smartly guess magic frequency. Does it magically work? In this case, it worked. Okay. Here we kind of solved it. Our guess happened to be correct. Will it always be the case? Not necessarily. Here it turns out to be correct. Okay, point number 1. And notice, for RLC circuit, let's just say circuits. Okay, this omega naught equals 1 by square root of LC. Okay, this is what I refer to this as the magic frequency. Magically gets you the answer. If you go search Wikipedia for magic frequency, will you find magic frequency? No, this is just a mnemonic. Okay, magic guess. Magic frequency in rads per second. That is also important. So this is a rad per second. This also happens to be the resonant frequency. What is the frequency at which there is resonance between input and the network? Okay, so also resonant frequency, but for both series parallel. This also happens to be the frequency at which impedance is minimum. Frequency at which net total Z is minimum. And that also implies this is also the frequency at which total current drawn from the source. Okay? Total current is maximum. Actually. And when I say minimum, this is amplitude, total amplitude of current. Okay, this is when the resistance is the least, current flow is the highest, right? So current is best. So it shows up in many places. And this is both series parallel, and there are many interesting details associated with it. We already see this, right? Notice amplitude of the impedance is this square root of r square plus omega L minus 1 by omega C, right? This will be a minimum when this term is 0. That is a square term, right? End of the day, it's going to add some value to this r square. If that is 0, that is when this whole thing is a minimum, right? So impedance is minimum, and the impedance amplitude that is minimum, you have the maximum current. So this magic frequency corresponds to so many interesting situations in the circuit. That is why, it is ubiquitously shows up. That is the reason, probably this is the frequency they are asking for. Having said that, if they are modifiers here, use common sense to retain the modifiers. For example, if this is a microfarad, when calculating, we retain the micro. Farad is in SI, we retain the micro, right? Henry is in SI, milli, we retain that milli, right? We did that calculation. If they are modifiers here, what is 1/10 of the angular frequency, right? So your magic frequency is 10 power 4. 1/10 of that is answer B, 10 power 3. So if there are modifiers in the question, retain the modifiers. Okay. Find the magic frequency. Whatever additional trap is added there, it is what is twice the angular frequency, what is half of the angular frequency, what is angular frequency plus 2, something like that. Whatever modifier is there, typically set as a trap, retain that modifier. In this case, no modifiers, just the angular frequency, directly your guess. In case they are asking you 1/5 of the angular frequency or 1/10 of the angular frequency, notice if they are asking for 1/10 of the angular frequency, I would have calculated 10 power 4 and then did 1/10, that would be 10 power 3. So my guess would have been B. Okay. So retain modifiers. Now, so at this stage, we have seen two things. In fact, we have seen three things. AC circuits kind of become like a simple resistor-like circuits if you use impedance. Only complication there is it involves complex arithmetic. We have seen use of magic frequency. Then, stick to SI to be on the safe side, right? We have also seen calculations. Let's go to this PYQ. For the circuit below, choose the angular frequency omega naught at which the voltage across a capacitor has maximum amplitude. Okay, let's also do the magic frequency. I think this is an example where the magic frequency guess doesn't work. But okay, but let's try it. Okay, method 1, magic guess. Our circuit is RC circuit. So the frequency that I am going to guess is 1 by RC. And if I have to calculate this, notice this, if you put, this is 1 into 10 power 3, and that is 100 into 10 power minus 6. Where answer should be in radians per second. Can we calculate this? What do we get here? I suppose this is 10 power 5 and this is 10 power minus 6. I suppose this is 10 rads per second, 0.1. 1 by 0.1, that is 10 rads per second. The answer notice is not there. So probably, this is an instance where the magic guesses doesn't work, okay? I'm not saying it works everywhere. It doesn't work in this case. So let's try to solve this. Method 2, where we solve. Okay. Voltage across a capacitor. How do you do that? If you use impedances, you can do voltage division. So what I'm going to do is voltage division with impedance. So notice the voltage across the capacitor is a fraction of the input voltage. This happens to be 100. And notice this is cos. So this is along the real axis. Okay. Or it has a phase of 0. I'm not writing that. Okay. This is going to be ZC. It's a fraction of that 100. What fraction? ZC by total. ZR plus ZC. Okay. So at this stage, notice VC happens to be 1 by, or let's write it this way, 1 by J omega C by R plus 1 by J omega C into 100. And if you have to take the amplitude, notice the amplitude of technically there is a 0 degree phase. If you take the amplitude, it is exactly 100. Okay, length of that is 100. Again, let me do this calculation once. You have 1 by J omega C, and what you have here is J omega CR or RC plus 1. Okay, by J, the whole thing by J omega C. I just added the denominator, J omega C. If I take the J omega C to the numerator, this thing cancels. What you are left with is this into 100. So what we want is the frequency at which amplitude of the voltage across the capacitor is 1 by, amplitude of the numerator is 1, amplitude of the denominator is square root of the real part 1 square plus square of the imaginary part, omega square r square c square. And that into, of course, I have to retain that half. So when is, at what frequency is this thing maximum? When is this term maximum? Now the question boils down to, when is this maximum? When is this max? Equivalently, that happens when is the denominator minimum? When is the denominator minimum? At what frequency is the denominator minimum? This says denominator will be a minimum when omega is 0. So this is denominator is minimum. That happens when omega is 0. So your answer by solving here is D0. And this is an example where, of course, the magic frequency that we calculated doesn't work. Fortunately, notice, okay, they didn't put the trap. If I were the examiner, I would have put 10. There are cases, many, roughly 8 out of 10 questions, magic frequency works. Many complicated analog filter circuits and all, it works. There are around 1 or 2 examples where it doesn't also work. This is one such example. And notice if we use impedances, I just applied voltage division, right? There are 2 impedances. There's a ZR and ZC. There is a ZR and ZC. And I simply solved. Hey, when is this maximum? You're not going to solve this. Take the first derivative, set it to 0 and all that. Okay? Again, that is a step that I might have taken for granted, but you need to get used to it. This comes with practice. Notice. Hey, when is this term maximum? When the denominator is, this is a function of frequency. At what frequency is this maximum? Hey, this is 1 divided by denominator. The smaller the denominator, the bigger that resulting number is, right? The smaller the denominator, the smaller the number you divide 1 with, bigger the number you get. You have 1 cake. Now you have to split it between people. The smaller the number you divide it with, the more cake you get. There are 10 people, of course, you are going to get 1/10 of a cake. If there are only 2 people, you are going to get half the cake, right? If there is only you are going to get the whole of the cake, right? So the smaller the denominator, the smaller the thing that you are dividing with, the bigger is the resulting thing. So this whole term, this ratio is maximum when the denominator is minimum. Yeah. Again, so this tiffin box, lunchbox dabba, and then this cake, these examples or analogies are always more relatable, I suppose. So it's also easier to explain. But actually, that's a fair question, which is what I was also mentioning. I took this for granted, right? I didn't do, this ratio is a function of frequency. I'm trying to find the frequency at which this function is a maximum. The typical way of doing it is, calculus way of doing it is, take derivative, first derivative, set it to 0. Hopefully the second derivative test is like fine and all that, right? But we are also seeing like simple English, right? And this will save you a lot of time. And we also need to be careful while doing it. And typically that comes with practice, okay? This is one example where I did it. I also actually did it the previous question. When is this thing 1? In fact, even in this question, notice, 1 is to say, when is this ratio 1? There we can, if this term, 2 things get cancelled, right? We get a 1. That is to say one thing. Equivalently, they could have asked, when is the current in the circuit maximum? Current in the circuit is maximum when the total impedance is minimum. The total impedance is this denominator. That happens when this thing, you are adding a square term to r square. You are adding a positive term to r square, right? If the square or your term you are adding a 0, that is the minimum that you can get, right? So when we did the same step here, right, we took it for granted, but equivalently they could have stated this as, when is the impedance, total impedance of this is a minimum. Notice, I already put that over here, right? Frequency at which total impedance is minimum, or equivalently frequency at which total current in the circuit is maximum. Current drawn from the source. Okay, great question and a fair question, okay? And that's the answer. Let's move on. Say from now on, it's mostly Kirchhoff's law, I suppose. Yeah, I solved this problem recently. It looks like a lengthy problem, but I'll do this, okay? Series RLC circuit is connected for a fixed value of R and C. Inductor is varied to deliver maximum current. This value is 0.4 amps. So notice, you are fixing, it's an RLC circuit, you are fixing R and C. You are varying L. If you vary L, you are changing the resonant frequency of the circuit. As you change L, it's a different circuit. It has a different resonant frequency. You keep on varying it until this circuit's resonant frequency hits this input frequency, 50 Hertz. That is when you get the maximum current. Okay. And that maximum current happens to be 0.4. So at minimum impedance, you have maximum current 0.4. And the potential drop across the capacitor, I suppose they are referring to the amplitude. The amplitude of the potential drop is 330 volt. The value of the inductor is, okay, this is, if you are kinda not careful, this can take a lot of time. Okay, so anyways, let me do this. You have a inductor, capacitor, or I'm varying this. Let's just, you could draw this in whichever order you want. It doesn't matter. Series RLC, right? You have a series. So I draw a series circuit. You have R, okay, and you have ZC as 1 by J omega C, and then there is a variable inductor. This is variable. You keep on changing this. So as you change L, you change the resonant frequency and of the circuit. So this ZL is J omega L, and this is at 220 at 50 Hertz. So the first point that I'm going to focus on is maximum current, max current. Let's say the current I, okay, max current. This implies minimum impedance. That is R plus J omega L minus J by omega C. The magnitude of this is minimum. When does this happen? Your omega square is 1 by LC. Okay, so you are keeping on varying the inductance so that the circuit's resonant frequency becomes this input frequency 50. Right now, omega, you don't know the capacitance. The capacitance, you can find that. For that, I suppose one more thing is given, right? And notice in this scenario, when omega L equals is minimum, let me also write it slightly more elaborately. Okay, notice that is R plus J omega L minus 1 by omega C. This is a minimum. Okay, that is when omega L equals 1 by omega C. This is what we refer to as the reactance. The imaginary part here is referred to as reactance. They cancel each other. Or when omega square or omega happens to be, omega square is LC, omega happens to be 1 by square root of LC. Okay? So essentially these two are cancelling. Right? That tells us the max current I max happens to be input V, okay, divided by Z min. Z minimum is just R when these two cancel each other. Okay, this is Z min. I'm going to write that as Z min. Okay, and Z min is just notice if that cancels, it's just R. So you have 220 by R. That is R is given, but R is not, max current is given. So this is R. Right. Notice this happens to be 0.4. So you can find R from here and you'll get that in ohms. Can we quickly get the R value here somehow? And then we have to find the capacitance value, and then we have to find the inductance value. Again, the same thing, right? The impedance here is going to be Dinesh. We have current is maximum and impedance is minimum. Impedance is amplitude of the impedance is this amplitude of this complex number, complex function. Okay. So it's going to be square root of R square plus this imaginary term. Imaginary term is that frequency dependent term. When the frequency dependent term is 0, you have the, see, if Z is A plus JB, magnitude of this is A square plus B square, square root of that, right? Typically this imaginary part happens to be function of omega, right? And so often Z minimum, it's a sum of two positive terms, this square plus this square. You get this minimum when if B square omega can be 0, that is when you have the minimum, right? This happens to be A when that this function is 0. B omega is 0. D square omega or B omega is 0. Or that imaginary part or D omega is 0. That is, the imaginary part is 0. Okay. So this is the same thing that I have been doing for a long time now, actually. It again boils down to the magic frequency. Hey, when is this amplitude maximum? That happens to be when this denominator is minimum. That is when that imaginary part is 0. Notice I already said that, right? Actually, that corresponds to Z minimum, I maximum. And if I have to isolate that detail, it is here. Typically, this only this capacitance and impedance, inductance, that has this function of frequency. For the resistor, it's not a function of frequency. So the real part resistance is typically, there is no omega term here. So omega at which you get Z minimum, this is when, the omega when this imaginary part is there. Is it clear, Dinesh? Fair question. But it's the same thing that I have been, in 2-3 problems, the same thing that we have been looking at. Yeah, when is this current maximum minimum impedance that happens when this imaginary term is 0? Okay, yeah, this is where we have great. Fair question. In fact, I am happy that some of you are stopping me and asking these questions because it's better to clarify. At the end of the day, it's a simple question, but and then now we have to find the capacitance and then only we can find the inductance, right? We also don't know the C. For that, one more piece of information is given. The potential drop across the capacitor is 330 volts. So VC is fraction of the voltage across the capacitor is essentially ZC by total Z. ZR plus ZC plus ZL. I'm applying voltage division. All this is of the input. Okay. And technically we are looking at I presume, they are talking about the amplitudes. Okay. This is presumably amplitude. It's not explicitly stated, but that's a fair presumption. Okay. Presumably amplitude. Okay, so what we have here is, this is 330 happens to be 1 by j omega c by r. Hey, we are already talking about this. At 50 we know this is cancelling, so that is 0. Okay, we know this is getting cancelled. The same frequency, or we have changed the inductance so that frequency is where this cancels, right? So we don't have to worry about this term either. The amplitude of this into 220. This is also actually notice fairly simple. This is just 1 by omega CR. Amplitude of J is just 1. So this is 220. I suppose we know omega, we know R. Can we find C? We find C, then we can go plug in and find L here. Okay, here there is a trap. So let's just find C and then I'll tell you where the trap is. C is 220 by 330 into 1 by omega R. And you should technically get this in farads. So I'm asking you to do the calculation because there is a trap. See, at this stage, I am also recognizing something. Okay, I need to make a comment on that. Great. The current answer is supposed to be 3.86 microfarad. Okay, 10 power minus 6 farad. You won't get this if you put omega is 50. Okay, F is 50 hertz. Omega is 2 pi into 50. That is 100 pi rad per second. Is a typical mistake that happens. Yeah, just plug in all these numbers, you'll get this. Okay, but if you plug in 50, you won't get that. Okay, this is 220 by 330. There is only a calculation. There is nothing to explain. This is 2 pi f. That is 100 pi into 550. That should give you. Are you referring to this step? I put this J0 again. So no, there is a nice connecting word here. See, I said there is a poorly framed question, right? Notice the current is maximum. That maximum value is 0.4, and corresponding to that, the potential drop across a capacitor. So the potential drop when that ZC and ZL cancel each other, that is when the current is maximum, right? That is when this term is not really there, right? It is 330. So 330 is, this into 220. And notice this fraction, some of you might be wondering, so how come, we have input is 220, this fraction is 330, something only across capacitor it's 330. higher than what we apply, because we also need to account for phases, and there is an inductive element. Okay, the capacitive phase and inductive phase kind of cancel each other and all that. Because of that, voltage across the capacitor or the inductor can be higher than the input voltage. What is happening is parts of that are getting cancelled, at least the phases are getting cancelled. Okay, so I am essentially reusing the same thing. Maximum current happens when the imaginary part is 0. I'm just reusing that part. I don't have to worry about that. So the amplitude is just R. And if you want to be slightly more clear here, all I am doing is, this is amplitude of 1 by j omega c. Okay, yeah, amplitude of 1 by j omega c is 1 by omega c. 1 by omega c. And then amplitude of R is R. So this happens to be 1 by omega RC into 2. Okay, there is a 220 there. Okay, 1 by omega RC into, and again I have underlined the detail that I have kind of used it. Maximum current, the corresponding potential drop. The corresponding is a connecting word. That is the important word. Okay, so it boils down to, the maximum happens at the same condition when this net impedance is essentially purely resistive. And this is a typical mistake that students do. Be careful about this. So this is 3.86, and I think we can find what this is, right? Now your L is finally, hey, at this stage, notice for me, I am quite generous on how I am using the space, right? But typically when I cross 2 pages, that's typically it's a that's a quick rule of thumb for me to actually, in the real exam, that's a rule of thumb to suggest I am possibly wasting time in one question. Okay, the most important time management tip is limit the amount of time you spend on any one question. Most important time, the exam time management tip. This is the most important. Okay, most important exam time management tip. Okay, that is, limit the amount of time you spent in any one question. Limit total time spent in, max time spent in any one question. Max time spent in any question, and this is approximately, let's say, 9 minutes. So should I keep on checking the watch? No. Okay, your rough work, you are given a rough note to actually do all this calculations, derivations and all that. Your rough work, it's approximately, and let me write it. Okay, approximately more than 1 page. Certainly more than 2 page, you are wasting time. You are spoiling, because of one question, you are spoiling your entire examination performance. So by the time your rough sheet is full, that's a sign that you are possibly wasting time. However favorite topic it is, how much ever preparation you have put into that one topic, how much ever confidence you have on solving that question, how much ever interest you have on that concept, whatever, irrespective of all that 1 or 2 marks is not worth it. Okay, you can keep your interest, curiosity, determination, all of that aside for that one question that takes more than 1 page. Okay, this specifically applies at the beginning of the examination. You have some excuse at the last 15 minutes, half an hour, when you think you are done with most of the questions. But limit the maximum amount of time spent in any one question. No question is worth your time, worth more than 10 minutes. Your confidence gets affected. Hey, what I'm not able to solve this, I'm somewhat getting stuck. You're losing your momentum. Okay, and the time you waste, you say you didn't keep track of your clock, or you didn't keep track of your rough work. All of a sudden 30 minutes is gone, 45 minutes is gone in one simple magic frequency question. That's it, right? Consider the impact of that. You don't want that happening. Okay, so any question you shouldn't be spending more than approximately 9 minutes. Okay, be very careful about it. In fact, in the lecture I kind of hit that border when I cross 2 pages. Your exam rough sheet, your font size is different. Okay, you will have to kind of fine tune it, but based on my font size, the lecture space that I use, roughly when I'm hitting 2 pages, I know, hey, this is taking a long time. But because I'm not solving the examination, I'm explaining this, I went ahead. Okay, so finally your L happens to be 1 by omega square C. Again, if you stick to SI, you should get the answer properly. This should be in Henry. What is that? Can someone do me the favor of calculating this. You know omega, you just found out C 2.6. I suppose, yeah, that's there in the answer Q range. 2 point. Yesterday I saw on this, I got 2.63. Okay, to that. Again, stick to SI, beware, 1S, beware. Another thing, stick to SI, you are safe. Stick to SI units to be safe. Approximately 2.63, okay, around that number. Based on your approximation for pi, sometimes, there is a change. Also notice you are not doing the calculation on one go. You're not doing, you're finding resistance, you're finding capacitance, and then you're finding inductance, right? Some of the, this errors in the decimals can propagate. And they give some room in the answer key to actually accommodate that, so you don't have to worry about it. But fair questions, and in fact, very great participation. And fortunately, slightly, but by this time I kind of knew. I almost got the answer. Okay, and also I am explaining this, so I went ahead and solved it fully. In the real exam, at this stage, I would have wondered, and often I would have actually went to the next question. Hey, I put 10 minutes in that question already, right? Waste of time. Fine, let the 10 minutes go to waste. Let me save it elsewhere. Okay, fine. 8. A series RLC circuit with. Hey, so some of you said second order circuits is problematic, right? But notice the number of second order circuits that we have been solving. This is a second order circuit. Okay, this is a first order circuit. This is a second order circuit. The idea is, if you use impedance, there is no distinction between first order and second order. AC circuits kind of become like resistor like circuit. You are not worried about seeing like 4 resistors. You are not bothered about it, right? 3 resistors. Same thing happens with second order circuit. If you know that complex algebra, you can easily deal with second order circuits. Okay, so by now you should actually gain confidence regarding that. Okay, there are, I think, two more PYQ. Okay, I think given time constraints, I will solve one. Okay, I will solve this PYQ, and I will also explain some basic theory pertaining to this. Notice again, this is an RLC circuit. It consumes power P. Value of L is changed such that this circuit consumes same power P but operates with a lagging power factor. We have a new term, lagging leading, right? I haven't explained that. That needs some theory, so I'll explain minimal theory. I'll solve this problem. And this power factor question is also a very, very important topic. Notice there is one more question, I think in 2021 showed up. Okay, this question actually it's actually a very easy question. Easy if you understand terminology. And I have put up a video, 5-minute video kind of explaining this terminology, and with a solution to this 5-10 minute video. Okay, what I will do is, in fact, if I make this video public, I will add that video here in this video so that you don't have to go search for that. This is if you understand terminology. Okay, it boils down to actually finding calculations with sides of a triangle, calculations adding and subtracting sides of a right triangle. Calculations involving sides of right triangles. Okay, this is actually fairly easy. Okay, just calculations of involving sides of a right triangle. I'll share that video. Okay, I'll in fact add solution discussion here. Okay, but this question is answerable with impedance. Okay, whatever impedance that we have been talking about. So regarding that, we have this mnemonic. Let me start with this mnemonic. Okay, what is leading, lagging, and all that? Leading and lagging show up in the context of, notice, voltage and current are not in phase. Both are complex numbers. If you look at, say, voltage phasor, the current phasor is not along that whenever there is frequency dependence. This is elsewhere. So there is a phase difference between current and voltage. Okay, and then is the current ahead of the voltage or behind the voltage is where this phase leading and lagging show. If the current leads the voltage, okay, you have a leading power factor or leading power consumption and all that. In this case, if let's say the voltage somewhere over here in the circle, at that point the current is lagging, right? This is often referred to, current is lagging behind voltage. With respect to voltage, is the current leading or lagging? That is the question. So with respect to V, notice this is phasor, is I leading or lagging. In purely capacitive circuits, this angle is often 90 degrees. Purely inductive circuits, this angle is often 90 degrees. But in a combination with a capacitive RLC circuit, this angle need not be 90 degrees. Okay, and so is it capacitive or is it inductive? Is a leading circuit capacitive or inductive? The question, right, often shows up, and we have very simple mnemonic for that. We have C I V I L. In a capacitor, current shows up before voltage. Okay, so current I is leading voltage. Current is leading voltage. In an inductor, L for inductor. Sir, I for inductor. What is this here? L for inductor. Inductance, right? Your current is actually lagging behind voltage. So civil is the mnemonic that we use. And what is shown here is almost it's the same power. The impedances are the same, magnitudes are the same, but there is a change in the dominance. Is it more? Notice if it is lagging, say if it is like capacitor is dominating, now the inductor is dominating. Okay. Again, what do we mean by that? Let's just give more example. Let's calculate. Notice right now we know all the traps. Your F is 50 hertz. So your omega is 100 pi rad per second. Quickly, can we have ZR is 10? Okay. ZC, this is 1 by J omega C. Can we have a calculation here? Okay. At the end of it, they should have units of resistance, okay, magnitude of that, and then ZL, J omega L. Can we calculate the number? Magnitudes will be in ohms. Okay. I suppose this is going to be minus J into some number. This is going to be J into some number. Capacitance is given 100 microfarad. So omega into omega C. So how much is this? I have 100 into 3.14. That is pi into 100 into 10 power minus 6. 1 divided that. I have 31.85. ZL is 100 into 3.14 into L is 50 milli, 15.7. So what they are saying is Z initially this is 10, okay, minus J into 31.85 plus J into 15.7. This is, notice, 10 minus 31.85, right? This is J into 16.15. This is your Z initial. And notice this is actually minus J. This is capacitor is dominating. This is actually leading. C is dominating. There are both capacitor and inductance, but C is dominating. That is why you have a minus J on a net. Now this is being, the value of L is changed such that consumes the same power. Let's also highlight consumes the same power. Okay, that what that says is magnitude of Z in it equals magnitude of Z change, Z new. Impedances are the same, so power consumption is the same. Okay, but operates with a lagging power factor. So your Z new is lagging. Your inductor is dominating. Same power consumption. So magnitude is the same. So this is essentially plus J into 16.15. Notice this is lagging and now L is dominating. So you have to increase the inductance so that this becomes L is starting to dominate. How much should you increase? The new value of L is. That is what they are asking. The new value of L should be much higher than the old value. Okay. L is dominating. What is the L new that will give this? Okay. And that boils down to, notice, J omega L new minus, you don't change the capacitor, that happens to be J into 31.85. This should be equal to J into 16.1, right? So Z new is giving this is giving this term. Okay, here we are changing Z. Here L is changed. In fact, we can actually see that L needs to be increased. What is L? The J's and all that will get cancelled. Perhaps if you're kind of wondering, all I'm writing is Z init is Z new, okay? The Z new is this. So you can also have technically R on both sides. Sir, where is that R went, right? You can also have that R that is also getting cancelled. So I'm not bothered about that. So the new change, right? If you put this, your capacitor remains the same. The net is plus 16.15. You can find L new. What is the value of L new? Be careful. My L new happens to be solving. So it is 16.15 plus 31.85 divided by omega. Let me be explicit. This is 16.15 plus 31.85 divided by omega, that is 100 pi. I suppose this is 0.15. Let's do that calculation. Okay. 0.15 plus 31.85 divided by 100 divided by 2.14. 1.053, and they want the answer in millihenry. So that is 153 into 10 power minus 3 Henry. Notice this is in Henry, SI, right? That essentially is millihenry. In fact, if you want to retain a couple of decimals, I got 158, right? So like this is 152.8. 8 or 9, okay? Yeah. Be careful. The answer is in millihenry. Simple traps, they said. A very simple question. So consumes the same power, says the impedances are the same, but initially it is leading, capacitor is dominating. You are increasing the impedance. Notice 50 became 152. You have increased the impedance so that it became a inductor dominating circuit, or it became a lagging power factor circuit. Inductor dominating is referred to as lagging power. Okay, so this is close to our scheduled time. As I already said, okay, this question actually calculations involving sides of right triangle. Notice this power factor question keeps showing again and again. Okay, so I'll add the already discussed solution to this video before uploading it.
Two loads are connected to AC supply mains as depicted in the figure. One load draws 10 kilowatts, whereas the other load of 10 kilovolt ampere is operated at 0.6 power factor lagging. To achieve an overall power factor of 0.9544 lagging, the nearest kVAR rating of the capacitor band needed to be connected across the supply mains is equal to. Okay, so essentially we have a AC supply. There are two loads. Okay, let me explain what this is in a moment, but we want to add another capacitor to this so that we end up with the overall power factor of this being 0.9544. These circuits, the voltage is not in phase with the current, right? So just the product of voltage and current, that's known as the apparent power. Okay, but if you look at the component that's where the voltage and current are in phase, VI cos phi, right? That's called the active or real or true power. Okay, and the component that's not in phase, where the voltage and current is not in phase, that's called the reactive power. Units for this is volt ampere, watts, and volt ampere reactive. Okay, and the power factor here is essentially the ratio of true power by apparent power. That's a power factor. Okay, so for given any loads, it's a good idea to just draw the power triangle. The nice thing is you can add and subtract sides because they satisfy complex arithmetic. Okay, for example, so let me explain what you mean by that. So 10 kilowatts. So the power triangle corresponding to this load 1, is just a single line because all of it is active power. There is no reactive component. Okay, that's also equal to the apparent power. So this is a triangle with zero height. This thing. So 10 kilovolt ampere is the apparent power. Okay, power factor lagging. Lagging means this triangle is facing upward. Leading means triangle is facing downward. So power factor is 0.6. So ratio of this by this is 0.6. So this is 6. Okay. So this is 6. This is 6. This is a right triangle. So this should be 8. Okay. Now they satisfy. You can add and subtract size, base and height. So if you add these two, the net triangle for this is 10 plus 6, which is 16. That's the base of this. The height of this is 8. So this is where we are currently, the black triangle. We want to end up at a red triangle whose power factor is 0.95. Okay. So 16 divided by 0.95. Okay. That should be the length of this. That's the definition of power factor. So that turns out to be 16.76. Corresponding to that, the height over here is 5 kVAR. Okay. If 8 has to become 5, we need to add a capacitor that has a leading downward triangle. This is a triangle with just no base, just the height. Okay. We need to add a triangle of, we need to bring it down by 3 kVAR. So this is the effect of the capacitor. There is no active true power in a capacitor. Just all of it is reactive power. The value we want is 3 because that will bring 8 down to 5. So the answer here is option E, which is 3.
And that brings us to the end of it. Okay, what is there is there are a couple of more miscellaneous things. There are like simple BJT MOSFET models, right? For this is, for example, current gain in the circuit below. There is a dependent current source, but this can be simply again analyzed using the same tools that we already know. Okay, so the current here is going to depend on the current here. And finding the current here, notice current division, you can find the current here. So this is 100 times that current. Once you know this is 100 times that current, and notice these two are not separated. That is, what happens in this circuit doesn't affect what happens in this circuit, right? There is no net flow of, this is not a closed circuit. So find the current here, and then again current division, you can solve this. Okay, fairly 2 current divisions, you get the answer. But this involves this new concept called, there is a dependent source, but fairly easy. Okay, if you look at 2022 discussion, you can find the solution for that, and then that's it. So at this stage, these are questions from measurement, I suppose. What is, it looks a circuit is given, but hey, which is accurate, which is precise is a measurement question. So, but it's a good place to stop. Our objective certainly is met by now. 80% of questions show up from 20% of concepts. You need to know the 20% of concepts in and out, all the things that discussed in this 4-part video. If possible, I'll make it one video. All the 4 parts I will combine into one video. I'll put it hopefully before the GATE 2025 exam. Okay, if you know that in and out, electrical circuits about 10 marks is showing up every year. You can you can score a lot in that part. Okay, conclusions. So today we looked at AC circuits. Hey, this is the same old resistor circuit using impedance. Catch, you need to know complex arithmetic. First case, we are asking you for some frequency. You don't understand the question otherwise. Other than the word frequency, you don't understand. Try guessing magic frequency, worst case scenario. And certainly if it's a NAT question, right? No negative marks. Stick to SI, okay? You don't have to worry about units. And the most important takeaway, not just for circuit, for every other subject, entire GATE exam, the most important tip is beware of the time you spend on any one question. Shouldn't exceed 10 minutes, okay? Your amount of rough work you do is an indicator of that. You don't have to necessarily keep staring at your watch. Wasting time staring at your watch, right? Panicking staring at your watch. Fine, beware of the time you spend on any one question, okay? So that's the last thing that I have to say. And this, we conclude this 4-part series, okay? I hope this will be useful not just for biomedical students. If you are, electrical circuits is there in many other papers, right? Instrumentation paper, electrical engineering, electronics and communications, EC paper, EE paper, IN paper, DM paper, all the students, right? Many of the students are trying to clear the cutoff. I am sure this 4-part videos series should be of immense help to all those students. Even otherwise, I know this is a good starting place to actually get started with circuits. There are more advanced things, right? There is 80% of concepts left, but most of the scoring can be done here. And with the way we discussed, and if you know all those things in and out, you can do very well in electrical circuits, okay? You can easily score more than 80% of the questions from electrical circuits. And our objective is met. With that, no other questions impending, I think this is a good place to stop.